to deep dive into how to build a system that can handle 500 million daily active users, serve billions of images per day, and maintain sub-second response times globally. This isn't just theory. Everything you'll see reflects actual architectural decisions used in large-scale production systems. First, we'll design a complete end-to-end architecture that's truly production-ready. We'll show you exactly how each component works and why. We'll design the exact database schema with the concrete sharding strategy. You will see actual SQL definitions with column names, data types, and indexes. We'll explain how each index works, how it optimizes the query times, and how it speeds up each of the queries that are part of the system. We'll also create a complete API design with all the needed RESTful API endpoints and implementing things like authentication, pagination, and rate limiting strategies. We'll tackle also the feed generation algorithm, which is one of the most important parts of the system design question. So we'll break it down into understandable pieces and concrete algorithms and data structures. And we'll also solve media storage problem at Instagram scales, handling billions of images, and you'll understand how to essentially use object storage, for example, CDNs and async processing pipelines to deliver images globally at every part of the world at the same time with very low latency. And after that, we'll also cover scaling patterns for over 500 million daily active users. You learn to see how we can scale every tier of the system independently based on its specific bottlenecks. Now, beyond the specific technical content, we'll also cover interview success strategies. You'll learn how to structure a 45-minute system design interview and what interviewers look for each stage, common mistakes, and how to avoid them. Also, as part of this video and course, we will also be providing bonus materials, which includes a PDF cheat sheet that is a one-page solution summary of exactly to the point how you would need to solve this problem in a 45-minute interview, as well as all the architecture diagrams that we will be referencing in this video. So now let's talk about why this framework works. So in our assessment, let me explain to you how this is different from other existing system design solutions. So this solution draws from three distinct areas. First, it is production experience. These are architectural patterns from building systems at scale in real companies. These are trade-offs that I have encountered in my career in real-world scenarios where you're balancing cost, performance, complexity, and time to market. These are performance optimization techniques actually used in production systems, and also not just production systems all across the world, but at the same time while you're serving different business customers for both end users as well as enterprise users. And the second reason is the academic foundation. So we'll apply the computer science fundamentals from distributed system research. We'll use algorithmic analysis and complexity theory to reason about performance. And we'll also take a formal approach to system design problems, breaking them down systematically rather than just straight them jumping into solutions on whiteboards. The third reason is interview success patterns. This structured framework has been defined through actual interview preparation with engineers. I've incorporated feedback from engineers who have passed tech companies' interviews using this approach, and I've also identified patterns that resonate with interviewers across different companies. So now let's talk about interview framework. So as part of the interview framework, we need to first start with step one, which is critically important and where many candidates actually fail. Always start with requirements. And why does this matter so much? It demonstrates structural thinking and a systematic problem-solving approach. It prevents you from building the wrong solution, and I've seen candidates spend 30 minutes designing an amazing architecture for a problem. Unfortunately, the interviewer didn't even ask. So starting with requirements shows you that you understand the real-world constraints, and the production systems aren't also built in vacuum. You have budgets, you have timelines, you have competing priorities, and it also allows the interviewers to guide your scope appropriately. If you're going too broad or too narrow, they can essentially correct you early, which will save you from failing the interview as well. So the most common mistake candidates make is jumping straight to drawing architecture diagrams without understanding fully what they are building and what problem they need to solve. Other mistakes including making assumptions about scope without clarification and designing for features that were not requested. I've seen candidates spend half the interview designing, let's say, for example, Instagram stories when the interviewer only wanted the main feed. So here's the correct approach. Spend 5 to 7 minutes gathering requirements and ask clarifying questions about features and constraints. Confirm scope explicitly before proceeding to design. Take notes on what's in scope and what's out of scope so you can reference them later. And what are interviewers looking for during this phase? Right? They want to see your ability to ask relevant questions. They're evaluating your understanding of edge cases and constraints. They're assessing your communication skills and whether you can clearly articulate assumptions. And they want you to confirm understanding before you proceed to the design. I'll say again, never assume and always ask. In a 45-minute interview, allocate 5 to 7 minutes to requirements gathering. This might feel like a lot, but it's time well spent and it's very important. The rest of your interview will be much more smoother if you get this foundation right. Now let's talk about function requirements. Let's define what Instagram does from a functional perspective. These are the features users directly interact with, and these are the core features that we'll first start designing for. First, users can upload photos and videos. Second, users can follow each other to see their content. Third, users should be able to see a personalized feed showing posts from people they follow. Fourth, users can like posts. Fifth, users can comment on posts. Sixth, user can view user profiles. And seventh, user can search for the users. So these are very core Instagram features that you work with your interviewer to be able to figure out, okay, these are the function requirements that I'll be working on. Is this okay? And when they say, okay, yeah, these are the core set of function requirements that you are working with, and that's great. Now, here the critical question you should also ask your interviewer. Should we support Instagram stories and reels? Or should we focus on the main feed? Do we need to include direct messaging functionality? Should we design the explore or discovery page? Are we supporting both videos or photos or just photos, for example? Do we need to handle video streaming and encoding? So these are a few questions that it shows that you're thinking a lot about the problem as well, but at the same time you're aware of the constraints that you should keep your interview within. These questions demonstrate that you understand Instagram is much larger than the basic feed functionality. You're showing awareness of the product while you're also managing scope. So here's the key insight about scope management. Instagram has over 100 features in production. A 45-minute interview round cannot cover everything. So you need to focus on the core photo and video feed functionality, and you must explicitly state what's out of scope. Here's my interview tip for this phase. Always confirm the scope with the interviewer before proceeding. Say something like, okay, based on our discussion, I'll design the core photo feed functionality with upload, follow, and common features. Stories, reels, and DMs are out of the scope. Does that sound right? Wait for the confirmation. This creates a contract between you and the interviewer, preventing misalignment later, so that both of you are on the same page. Now let's discuss how Instagram performs, not just what it does. Right? So these are the non-functional requirements that will drive your architectural decisions. For scale requirements, let's start with monthly active users. We are targeting roughly 2 billion monthly active users for Instagram, and this is actual scale as of 2024, so it's a very realistic number for the interview. Daily active users will be actually 500 million, and the monthly active will be 2 billion, and daily active will be 500 million. This represents about a 25% daily engagement rate, which is typical for social media platforms. Not everyone who has an account uses Instagram every single day, but we still need to account for all the monthly active users. Photos and videos posted daily will be roughly 95 million. This is based on industry data from 2024. It might seem like a lot, but when you have 500 monthly daily active users, that's not a very huge number. And this number makes sense. Even though you know the number from the top of the head, which is totally not expected out of you, just make a reasonable guess that, okay, out of 500 million people, roughly 20% daily will be posting photos. And when you make a good educated guess, then that's all the interviewer is actually asking for. Now, average post viewed per person per user per day is roughly, let's go with 20 posts. This represents typical user engagement. Some users scroll for hours and they see hundreds of posts. Others open the app briefly and they just close it right away. So 20 is a reasonable number to go with. So as long as you can justify it with a good educated guess in front of the interviewer, that's what they're asking for. They're not really asking for specific exact correct numbers. For performance requirements, we need to define specific latency targets. Feed load time should be averaged under 300 milliseconds, with the 95th percentile under 500 milliseconds and a 99th percentile under 1000 milliseconds. These are aggressive targets that provide a smooth user experience, but that is expected out of a big platform like Instagram. Image upload time should be average around under 1 second, with 95% for 5 percentile under 2 seconds and a 99 percentile under 3 seconds. Users will tolerate slightly longer upload times and viewing times, but we still need to be very fast on that. Now, the API response time should be average around 100 milliseconds. P95 should be less than 200 milliseconds, and the P99 should be roughly less than 500 milliseconds. These are internal service to service call times, and these are not end to end user latency. Now let's talk about the non-functional requirements for especially the reliability part. For availability and reliability, system uptime must be 99.99%, which is roughly 4 nines, which allows for maximum of 52 minutes of downtime per year. This is standard for consumer-facing applications, and you can go for more nines, but let's start with 4. The data durability, however, must be 11 nines. So that means that we absolutely cannot lose user photos. If we lose user photos, they are gone forever, which is highly unacceptable. For disaster recovery, we are targeting a recovery time objective of under 10 minutes, which is called the metric RTO. If an entire data center goes down, we should be able to fail over to another region within 10 minutes. And that's what the RTO essentially, at least for the context of the interview should mean. Our consistency model uses eventual consistency for feeds, and if it's acceptable for up to 1 second of delay before a post appears in someone else's feed. So let's talk about the eventual consistency in these platforms. So essentially how it works is that once you upload something, since it's a microservices architecture, not everything will be available right away. Let's say if I upload a photo, it won't be right away available to someone. Let's say I have a friend in Japan and it'll be on their phone. So it'll be slightly delayed because we do replication and other microservices patterns that we'll cover just in a bit. So that's why we go with eventual consistency in architecture like this. However, we do need strong consistency for critical operations like it follows. If you like a post, that action must be immediately visible to prevent double liking. An important trade-off is that a user may not see their own post in their feed immediately after posting. This is an acceptable trade-off for better performance and availability. Now in the next slide, let's talk about system characteristics. In this, let's talk about how Instagram is a read-heavy system. So with approximately, a safe guess for Instagram would be 100 to 1 read to write ratio. What does that mean? So for every one photo uploaded, that photo is viewed roughly 100 times. This characteristic will heavily influence how our caching strategy and database configuration will work down the road. While reads dominate overall traffic, we still very write heavy on uploads with 100 million posts per day that we just discussed a bit earlier. This is a massive write volume that requires careful design. Global distribution is required because users are essentially worldwide for a platform like Instagram. We can't serve users in Tokyo from a data center in Virginia because that will be huge latency. We'll need a CDN and potentially multiple geographical regions for that. Now let's talk about a very important thing, which is like what is autoscope for this interview, so that we've cleared with our interviewer as well. And specifically what our design won't be able to cover given the limited time we have, 45 minutes. And this is just as important as stating what we will design. So this is very important part you should cover in your interview. So features that are not included in the design are direct messaging and chat functionality, Instagram stories and reels, video encoding and streaming infrastructure, live video functionality, shopping, e-commerce features, the advertising platform, content moderation, and machine learning models. So I just want to clarify that these are safe bets to assume because all of these features are very huge amount of scope in itself. Like for example, just video encoding and streaming infrastructure could be a separate interview question itself. So what I'm trying to say is that once you clarify with the interviewer doubles down and be like, oh, okay, please cover that part, let's say stories and reels as well. So then you do have to modify your approach. But the main point is that you have to specifically tell them that, okay, This is what I'm going to cover in my design, and this is what I'm not. We in my assessment and as a candidate assessment, we won't be able to cover in the 45 minutes. If the interviewer does push back, or they actually tells you, actually, you know what, let's leave that part. Let's leave the following functionality. Let's double down on stories and reels. So you would need to pivot to that. But this is the more established based on. So you make the decision criteria behind this is that you decide based on what are the features that a normal candidate, a regular everyone like a candidate can be able to cover in 45 minutes, and what features cannot be covered in 45 minutes. So that's why these specific features we had, like I decided to be out of scope. If I was doing this interview, for example, for any company, I won't be building this as part of the 45-minute interview. There'll be too much scope to cover. Yeah. So it does show prioritization skills as well as, which is important for senior engineers. It prevents scope creep where you design everything and end up designing nothing. It allows depth over breadth. So these are the reasons that you should be prioritizing all of this. I would rather have you deeply understand feed generation than superficially understand like 20 features. So as a senior engineer, as an experienced engineer going for these interviews, you need to show depth as well as balancing breadth. But at the same time, you cannot just talk about 20 features. So now let's talk about here's how to communicate this in the interview. All right. So ideally you should say something like, okay, for today's interview, I'm going to focus on these core feed functionality, uploading photos and following users, viewing as a personalized feed, and social interaction like likes and comments. More complex features like stories, messaging, and video streaming would require separate deep dives. And then you can ask the interviewer that is this the right scope for our discussion? So just confirm with them. And this is the interview best practice. Always explicitly state what you are not designing and check with the interviewer. Interviewers appreciate when candidates clearly define boundaries and demonstrate focus. It shows maturity and real world experience where you can't solve every problem at once, which will be a very big part of your daily life as an engineer. Now let's talk about the requirement summary. So let me summarize our requirements to clear a clear contract with the interviewer. In scope for our core functionality, we are building photo and video upload with storage, user follow and unfollow relationships, personalized feed generation and display, like and unlike posts, comment in posts, user profile viewing, and basic user search. For scale targets, daily active users are assumed to be 500 million, posts created daily are 95 to 100 million, feed load latency at the 95th percentile is under 500 milliseconds, system availability is at 4 nines, and data durability is at 11 nines. Okay, our key constraint is that an eventually consistent system is acceptable. We are building a read heavy workload with a 100 to 1 read to write ratio, and we have a global user base that we need to serve, requiring low latency worldwide. Before proceeding, you should ask, before I proceed to capacity estimation architecture design, do the requirements align with you or what you're looking for? So this is something like you should clearly mention to your interviewers and then ask them, do you want me to prioritize something else before I move to capacity estimation architecture, or are you good with this? And this is a very critical interview tip. Always get explicit confirmation from an interviewer that requirements are correct before proceeding. This creates a contract and prevents misalignment later. If the interviewer wants you to add or remove something, better to know that right now in the early stages of your interview rather than when you have spent 20 minutes designing the wrong system. Now let's talk about why capacity estimation matters so much. It's one of the very important things as part of an interview. Many candidates skip this or just hand wave through it, which is a very bad thing. Please don't do that. So why do interviewers ask for capacity estimation? It tests multiple scales simultaneously. It shows your ability to reason about scale and magnitude. It demonstrates back or envelope calculation skills, which senior engineers use constantly. It shows your understanding of how scales impact architecture. And it reveals practical engineering judgment. Capacity estimation informs architecture decision in concrete ways. Storage requirements determine database sharding needs. If you need 100 terabytes of data, you can't use a single database. Queries per second determines the number of server needs. If you have 100 QPS, each server handles, let's say, 1000 QPS, and you need at least 100 servers. Bandwidth requirements determine whether a CDN is necessary or optional. Cache size requirements gathering determines Redis cluster sizing. So here's what you need to estimate. For storage, calculate total data storage needs for both photos and metadata. For bandwidth, calculate network ingress for uploads and egress for views. For QPS, calculate both read and write queries per second. And for cache, determine the Redis cache size for hot data. Here's the interview approach. You don't need exact numbers, however, rounding generously is also acceptable. For example, 86,400 seconds in a day can be approximated to 100,000, and that's totally fine. Sure, calculation process early and clearly so that the interviewer can follow your logic. Explain the assumptions explicitly so if they disagree with the assumption, they can correct you and then you can adjust accordingly. The most common mistake is skipping capacity estimation entirely or hand waving with, okay, we'll scale it horizontally. That doesn't really give any specifics, which interviewers are actually looking for. Interviewers want to see you can reason about your numbers instead of just saying you don't have real time data or things may have changed since your knowledge cut off. Show them that you can calculate current estimates based on the requirements you just agreed on. Let's calculate traffic in QPS with some basic assumptions here. Daily active users are 500 million. This is given in our requirements, so we don't need to derive it. Average post viewed per user, we came up with 20 posts per day, which represents a typical user engagement. Average post created per user is 0.2 posts per day. That means not everyone is posting daily. Only about 1 in 5 users posts on any given day, which is more realistic. Now let's talk about the read traffic. For calculating the read traffic, let's total daily views is equal to 500 million users times 20 million posts per day, which equals to 10 billion views per day. That's 10 billion times someone loads an image from our system. To convert this query per second, we divide 10 billion by 86,400 seconds in a day. Rounding that number to 100,000 for simplicity, we get 10 billion divided by 100,000, which equals to 100,000 QPS. For peak traffic, we'll assume 3 times the average, which is typical for a social media platform that has user spikes in weekends and evenings and special holidays. So the peak traffic for this problem is 300k QPS. This is a critical number. 100,000 queries per second for reads mean we absolutely cannot serve all requests from a single database or a single server. We definitely need horizontal scaling, caching, and most likely a CDN as well. Now let's talk about the write traffic. So for write traffic for photo uploads, total daily uploads, we came up with 500 million users times 0.2 posts per day, which equals 100 million posts per day. Notice that this is a much smaller than the 10 billion views, which confirms our read-heavy assumption. Converting to QPS, 100 million divided by 86,400 seconds approximately comes down to 100 million divided by 100,000, which is equal to 1000 QPS. Now peak drive traffic at 3 times average for this would be 300 QPS for writes. Now let's talk about the read-write ratio here. So as part of the read-write ratio, we can calculate that read QPS is 100k, write QPS is 1000. The ratio is 100,000 to 1000, which simplifies to 100 to 1. This is a very heavily focused. It's a very heavy read system, which is like 100 to 1. For every one write, we have 100 reads. This has huge implications for our architecture. Read optimization become critical. We'll need caching, we'll need CDNs, and we'll need read replicas. The write path can be simpler, sure, because the volume is lower, but at the same time, our database should definitely be optimized for reads and not necessarily for writes. Now let's talk about storage estimates for photo storage specifically. So as you can see here, so our assumption was 100 million posts per day, which is average photo size of 2 megabytes, let's say, after compression, and average video size of, let's say, 10 megabytes through, though we'll focus primarily on photos for the sake of the interview. The daily photo storage equals 100 million posts times 2 megabytes, which is equal to 200 terabytes per day. That's 200 gigabytes of new photos every single day. Annual photo storage equals 200 times 365 days, which equals to 73k terabytes per year, which is 73 petabytes per year. This is absolutely massive. To put in perspective, 73 petabytes is 73 million gigabytes. This is more data that you can fit on millions of laptops. This scale makes certain architecture choices mandatory, like using object storage and CDN that we will be actually covering in this interview. Now let's talk about the metadata storage. In addition to the storage we have already talked about, metadata storing is also super important. This is separate from the actual photo files. Our assumption our post metadata is about 1 kilobyte per post, including the text caption, the IDs, the timestamps, and other fields. User metadata is about 2 kilobytes per user. Follow relationships are about, let's say, 16 bytes per relationship and just 2 user IDs. So let's say go with 16 bytes per and comment average for 500 bytes per comment. So these are all the assumptions that we have made. You don't always have to come with the exact number, but this is something like a rough estimate has to be given to interviewer. And just to recap again, the interviewer is not necessarily asking for the correct number or like you need to memorize all of these things. Absolutely not. But you just need to have a good estimate on things. For example, a bigger text block will require more storage, and images will require more storage than text, and videos will require more storage than images, like things like that. But a rough ballpark numbers like just we just show in this slide over here is also super important. So just have some numbers ready, and since you'll be preparing most of the common interview questions, let's say in designing Instagram, designing Amazon, designing Uber, so just try to keep those things in mind as well. So now the daily data growth is also calculated as follows: 100 million post times 1 kilobyte from post metadata plus 100 million post times 10 likes per post on average times 16 bytes for likes plus 100 million post times 2 comments per post on average times 15 for 500 bytes for comments. This totals approximately 100 gigabytes per day, which is just for metadata growth. This is approximately 36 terabytes per year. So now compare this to 73 terabytes per year for media files. This is still a huge number in itself, but not relatively that big compared to the photos. But we still need to care about the metadata here as well. So if we do a direct comparison with the storage requirements, media storage for photos and videos is 73 petabytes per year, representing 99.95% of total storage. Metadata storage in our database is 36 terabytes per year, representing only 0.05% of the total storage. So here's the key insight. The media storage completely dominates. This means the architecture must optimize for media delivery. A CDN is absolutely non-negotiable at this scale, given the numbers here. Meanwhile, a data storage is negotiable in comparison. 36 terabytes per year is manageable with proper sharding. Now let's calculate network bandwidth requirements, starting with ingress for uploads. So daily uploads are 100 million posts times 2 megabytes, which equals to 200 terabytes per day. Bandwidth equal 200 terabytes divided by 86,400 seconds in a day, which we can route about 200,000 seconds. We get 200 terabytes divided by 100k seconds, which is equals approximately 2 gigabytes per second ingress. So we need to handle about 2 gigabytes per second upload bandwidth. This is manageable, but it definitely requires careful network design. Now let's calculate the egress bandwidth for image views. This is where things get interesting. Daily views per are 10 billion views times 2 megabytes per image, which equals to 220,000 terabytes per day. That's 20 petabytes of data transferred per day. Bandwidth equal roughly 20,000 terabytes divided by 86,400 seconds in a day, which comes down to be roughly equals to 231 gigabytes per second egress. Let me repeat that. That's we need to sustain 231 gigabytes per second of output bandwidth. That's over 100 times of our inbound bandwidth. So here's a critical insight. Let's look at our bandwidth comparison. Ingress for upload is 2.3 gigabytes per second and egress for views is 231 gigabytes per second. The ratio is again 100 to 1. Egress is 100 times larger than ingress. So here's a critical insight. This makes a CDN or a content delivery network absolutely mandatory. Sure, you could have said that in the beginning of interview. Oh, sure, Instagram is such a big platform; it has huge scale, and we definitely need a CDN. But the thing is, you need to take the interview through the process, which we just did, through mathematical operations, through the back envelope calculations, to prove it to interviewer that behind your architecture decisions, there is a reason, there is a thought process. That's why it's super important to show these calculations. So coming back to it, CDN is super important. Our origin servers cannot handle 231 gigabytes per second of egress. It's physically impossible and economically it's very bad. So now let's apply the 80-20 rule for cache requirements. We'll assume 20% of content receives 80% of the views. This is well-established pattern in social media. Hot content to cache equals to 20% of 73 petabytes annual storage, which equals to about 14.6 petabytes of hot content. However, the active cache size we need is typically recent content for approximately the last 7 days. That's 200 terabytes per day times 7 days, which is equal to 1.4 petabytes actively being cached. So now let's talk about the implications. The implication is pretty clear actually. A CDN is not optional at this scale. Aggressive caching can reduce origin server load by over 80%, and the cost of not using a CDN will be very bad, likely millions of dollars per month in excess bandwidth charges. About the high-level architecture overview now. And this is a 10,000-foot view where we show all the components and how they fit together. At the client layer, we have mobile applications for iOS and Android and web browsers, and there are also how users interact with Instagram. So there are different clients for iOS, for Android, and for web applications. At the edge layer, we have a load balancer providing layer 7 HTTP load balancing. This distributes incoming requests across our application servers. We also have a CDN, which could be CloudFront or Azure CDN for delivering media files globally. At the application layer, we have an API gateway that handles authentication, rate limiting, and routing. Then we have specialized microservices. The user service handles profiles and authentication. The post service handles creating and deleting posts. The feed service generates personalized feeds. And the media service handles uploads and processing of the images. At the data layer, we have user database, which is shared PostgreSQL. We have the post database and also shared PostgreSQL. We have a feed cache using a Redis cluster. And we have object storage using S3 or Azure Blob, for example, you can use for media files. So the flow works like this. Mobile and web clients connect through the load balancer. The load balancer routes to the API gateway. The API gateway authenticates and routes to the appropriate service. Service interact with their respective databases and caches. The media service stores files and object storage is fronted by the CDN. The CDN serves images directly to the clients, bypassing the application layer entirely for the media delivery. So now let's talk about the principles for the high-level architecture. Our architecture follows several key principles here. So the first one is separation of concerns. Each service has a single, well-defined responsibility. Services own their data, meaning no shared databases between services. And we enable independent scaling per service as well. We organize our architecture in layers. Layer 1 is the client layer with mobile apps and web browsers. Layer 2 is the edge layer with load balancing and CDN for media delivery. Layer 3 is the application layer with microservices handling the business logic. And layer 4 is the data layer with databases, caches, and object storage. Now let's highlight a few key design decisions that we have taken over here. So we are using a microservices-based architecture, not a monolith. We have a separate media delivery path through the CDN, not through the application servers. We have a centralized API gateway for cross-cutting concerns like authentication and rate limiting, and we have a dedicated caching layer for feed performance. Now let's talk about each of the components, the core components one by one, starting off with the API gateway. The API gateway has several responsibilities. It's a single entry point for all client requests. It handles authentication and authorization through JWT token validation. It implements the rate limiting per user and per IP address. It routes the request to the appropriate microservice based on the endpoint, and it supports API versioning. For technology, we could use tools that in the market like Kong, AWS API Gateway, or Azure API Management. All of these are production proven solutions for high scale systems. Now, let's talk about the user service. The user service has its own set of responsibilities. It handles user registration and authentication. It manages user profiles, including bio, profile picture, and other metadata. It manages follow and unfollow relationships. It also provides a user search functionality, and friend suggestion would be part of the service, though there would be, for now, it would be part of the MVP scope, which is the scope we are going with the interview. The data owned by this user service includes user profiles and follow graphs, which tracks, for example, who follows whom. Now let's talk about the post service, which is responsible for anything related to post-related operations. So this creates new posts, coordinating with the media service for image upload. It deletes posts when requested. It retrieves the post by the user. It manages post metadata like captions, location tags, and timestamps, and it handles the unlike functionality as well. It also manages comment creation, deletion, and retrieval. The data owned by the post service includes post metadata, likes, and comments. Now let's talk about the feed service. The feed service is the most complex service in our system. Its responsibilities include generating personalized feeds for each user. It ranks and sort posts by relevance using a ranking algorithm. It handles paginations when users scroll through their feed. It caches feed results to avoid regenerating feeds on every request. This is the most complex service because feed generation involves querying multiple data sources, applying ranking algorithms, and the caching strategies as well. The data owned by the feed service is the feed cache, which contains pre-computed feeds. Now let's talk about the media service. The media service handles everything related to our images and videos. It handles images and videos uploaded from the clients. It generates multiple thumbnail sizes for different use cases. It stores media in object storage like S3 or Azure Blob storage. It coordinates with the CDN for efficient delivery. And it performs image compression and optimization to reduce file sizes as well, which is very important in the real world production scenarios. The data owned by the media service is references to the media and object storage. You can use Azure Blob storage or AWS S3 depending on the cloud storage your team is using. Note that it doesn't own the actual files which live in the object storage, but this service is actually just owns the metadata about where those files are located. An important principle is service independence. Each service can be developed, deployed, and scaled independently by separate teams. This is a key benefit of the microservices architecture. Now let's talk about the justification and the benefits of microservices architecture compared to architectures like a monolith architecture. This is a common interview discussion point. The benefits of microservices for Instagram include independent scaling. We can scale services based on specific load. For example, the feed service needs 100 times more instances than the post service because the feed generation is so expensive. Team autonomy is another benefit. Different teams can own different services. The feed team can deploy changes without coordinating with the media team. Each team can move at their own pace. Now let's talk about more benefits here. So for example, the first one is the fault isolation. As part of this, if one service fails, it doesn't crash the entire system. If the media service goes down, users can still view their feed with cached images. Technological flexibility means each service can use the optimal tech stack. The feed service might use Java for its mature ecosystem, while the media services could use Go for better performance and image processing. Deployment flexibility allows us also to deploy services independently. We can fix bugs in the user service without redeploying everything. This reduces risk and also enables faster iteration. However, there are definitely some trade-offs with going with the microservices architecture. For example, one of the first trade-offs is that overhead between the services is definitely a drawback. Services communicate over the network instead of in-process function calls, but we can mitigate this by using efficient protocols like gRPC or co-locating related services. Distributed transaction challenges are another issue. It's harder to maintain consistency across services. We mitigate this by using eventual consistency where acceptable and where it's possible, and the saga pattern for complex transactions. Now, operation complexity also increases. We need sophisticated monitoring, logging, and distributed tracing as part of microservices. And we can mitigate these concerns by investing in proper tooling actually from the start. More complex deployment is definitely a challenge. We need container orchestration, like, for example, Kubernetes to manage hundreds of service instances. But this investment is definitely worth it if we are operating at the scale of Instagram. Now, let's talk about a possible alternative monolith, which might make some sense in some architectures, in some use cases, might not be for Instagram, but for the business scenarios. A monolith makes sense for an early stage startup with a small team, for example. When you have an unclear product market fit, you want to iterate quickly, and microservices just add complexity that just slows you down at that stage. Debugging is also comparatively simpler in monolith compared to microservices, and the deployment is simpler, and that's why it's a good starting point. However, for Instagram, microservices are the right choice. Scale requirements exceed single service capacity, multiple teams need to work independently, different components have different scaling needs. At Instagram's scale of 500 million daily active users, the benefits of microservices outweigh the complexity costs. In production system handling billions of requests, independent scaling and fault isolation are critical. You can't afford for one component's failure to bring down the entire system. Now let's talk about the data flow diagram for the upload path. Let's walk through these actual data flows, starting with when a user uploads a photo. The client sends a post request to the upload endpoint with the image file, caption, and location. The API gateway validates the authentication token. The API gateway then forwarded the upload request to the media service. The media service immediately increases the processing job in a queue. Critically, the media service returns a 202 accepted response to the client with a job ID. The user sees uploading, but the API has already responded. Meanwhile, in the background, a worker picks up the job from the queue. The worker compresses the image, reduces it from perhaps 5 megabytes to 2 megabytes. The worker generates the thumbnails in three sizes: small, medium, and large. And then the worker stores the worker microservice or worker Azure function, for example, stores the original plus all the thumbnails in the object store like AWS S3 or Azure Blob storage, and then S3, for example, returns the URL for all these files. The worker then calls the post service to create the post metadata, passing the image URLs, and the post service inserts the records in the post table with all the metadata. The database returns in the post ID. Both the post service may trigger CDN cache and validation if needed, though usually we use lazy loading. Finally, the post service sends a WebSocket notification to the client saying post has been created successfully. Now let's deep dive a bit more about in the upload path steps as mentioned here. Now, as you can see here, the step 1 is when the client initiates the upload. This takes roughly 1 to 2 seconds total. The user selects a photo in the app. The app sends a post request with the image file, caption, and location, and the API gateway validates the authentication token. Step 2 is when async processing begins. The media service receives the upload. It immediately enqueues the job in the processing queue. It returns status 202 accepted, meaning the job has been accepted and will be processed asynchronously. The client shows an uploading indicator, and the entire step completes in milliseconds. Now, step 3 is when a background worker processes the images. This typically takes, let's say, 5 to 10 seconds. A worker picks the job from the queue. It compresses the original image from, let's say, 5 megabytes to 2 megabytes, JPEG quality 85, and then this balances file size with visual quality. It generates three thumbnail sizes. The small thumbnail is 150 by 150 pixels for profile views. The medium thumbnail is 640 by 640 pixels for feed display on the mobile. And the large thumbnail is 1080 by 1080 pixels for detailed view for the desktop. Step 4 is storage and metadata creation. The worker stores 4 files in S3, the original plus the 3 thumbnails. It creates the post metadata in the post service database, and it associates the image URLs with the post record. Now let's talk about the step 5. Step 5 is client notification. A website notification is sent to the client. The client UI updates to show the posts are successfully created. And let's talk about why do we need async processing here. First, the user doesn't wait 10 seconds for upload to complete. Second, the image processing is CPU intensive. We don't want to unblock the API service doing compression and thumbnail generation. And third, async processing handles traffic spikes better. The query buffer requests and preventing the system from being overwhelmed. Now let's talk about the feed load path, data flow, and starting with the diagram here. This is basically when a user loads their feed and how that data flow will typically work. The client will send a GET request to the feed endpoint with a limit parameter, and the API gateway will validate the authentication token and extract the user ID from the token, and the API gateway then forward the request to the feed service. The feed service first checks the Redis cache using a key, let's say feed.12345, where 12345 is the user ID, for example. Now we have two possible paths. In the cache hit path, which happens, let's say 80% of the time, Redis returns the cache list of post IDs. The feed service knows the feed is already cached, so it skips the generation step entirely. In the cache miss path, which happens roughly 20% of the time, Redis returns nil, meaning the feed is not cached. The feed service queries the user database to get all the users followed by the user, and the user database returns a list of user IDs. The feed service then queries a post database to get the recent post from those users, and the post database returns the post ID with the metadata. The feed service then ranks these posts using a ranking algorithm and then store the results in the Redis cache with the, let's say, a 5 minutes TTL. Both paths converge at hydration. The feed service queries the post database to get the full post objects for the list of the post IDs, and the post database returns the complete post data for it. The feed service then queries the user database to get user information from each of the posts offered. The user database returns the user profiles in. The feed service constructs the final feed response as JSON and returns it to the API gateway, and the API gateway then returns the status 200 OK response to the client. Finally, the client requests images in parallel from the CDN, and the CDN serves images, which are cached at the edge locations worldwide. Now let's talk about the feed load path as part of our data flow diagrams. Step 1 is the request initiation. The client sends a GET feed request. The API gateway validates the authentication. It extracts the user ID from the JWT token. The step 2 is the cache check, which is critical for the performance. The feed service checks the Redis for the pre-computed feed. The cache key follows the pattern feed user ID. The cache TTL is 5 minutes. We expect an 80% cache hit rate based on our typical usage patterns. And then the third part, the part is the cache hit path, which is fast, taking only 50 to 100 milliseconds in total. The feed service retrieves the cache list of post IDs from Redis. It skips feed generation entirely, saving hundreds of milliseconds. It proceeds directly to the hydration part after that. Now let's talk about the cache miss path. Step 3b is the cache miss path, which is slower, taking 300 to 500 milliseconds in total. The feed service queries the user database, asking who does user 12345 follow. The feed service then queries the post database, asking what are the recent posts from all those users. It applies a ranking algorithm to sort posts by relevance and using factors like recency and engagement. Finally, stores the results into the Redis cache with 5-minute ETL for future requests. Now let's talk about the hydration and response part. Step 4 is hydration, which happens for both cache hit and cache miss paths actually. The feed service converts the post IDs to full post objects by querying the database. It fetches the user's information from each of the post order. It calculates the aggregated counts like number of likes and comments, and it checks if the current user has liked each post, which is important for showing the UI correctly. Step 5 is the response. The feed service returns JSON data to the client. The client then requests images in parallel from the CDN. The CDN serves images that are cached at the edge locations worldwide. Now let's talk about the performance actually. Let's break it down the performance by each of the steps here. For a cache hit scenario, the cache check roughly takes 10 milliseconds. The feed hydration takes 0 milliseconds because we completely skip it. And the hydration takes 50 milliseconds, and total latency comes down to 60 to 100 milliseconds. For a cache miss scenario, the cache check takes 10 seconds. The feed generation now takes actually 200 to 300 milliseconds. The hydration takes 550 milliseconds, and the total latency takes up to roughly 260 to 360 milliseconds. This shows that why caching is so critical. Cache hits are 3 to 5 times faster essentially than the cache misses. Now, let's summarize the architecture that we have covered so far and the key takeaways from a high level architecture. Number one, so to recap, we have 5 architecture patterns. The first is the microservices architecture with independent services for user, post, feed, and media management. Each service scales independently. Services communicate via REST APIs, or you can use message queues as part of the async communication. Second is the separation of media from the metadata. Media files are stored in the object store like S3 or Azure Blob storage, and metadata is actually stored in the relational databases, let's say for example PostgreSQL. This separation is critical for scale as well because you can't efficiently store petabytes of binary data in a relational database. Third is the multi-layer caching. So we use CDN for media files with over 80% hit rate. We use Redis for feed and user data with 5 minutes TTL, and we use database query cache as well. Fourth is the async processing. Image processing happens asynchronously so the users don't have to wait, and the feed generation can also be pre-computed. The user experience is essentially non-blocking here. Fifth is the read optimized design. We use read replicas for the database. We have aggressive caching at all layers, and we use CDN to handle 100 times read traffic compared to the write traffic. And what should we emphasize in the interview? Let's talk about that. First, explain why we should choose microservices in this architecture. The reasons are essentially independent scaling, fault isolation, and team autonomy. Second, you should explain why CDN was mandatory in this scenario. For example, at 231 gigabytes per second ingress bandwidth, there is no other alternative. Third, you should explain to the interviewer that why Redis caching is critical. Feed generation is expensive, involving database queries and ranking algorithms. That's why caching is absolutely not optional here, and that's why we need to do caching using Redis here. Fourth, explain why object storage is the right choice here. It's designed for the petabyte scale media storage with high durability. Like for example, the 11 nines we need for durability. That's why we definitely need to store in the object storage instead of storing images in databases, which is absolutely not ideal. And fifth is explaining to the interviewer that why async processing improves the user experience, because users now they don't have to wait for the thumbnail generation, which can take several seconds, and that is definitely not a good optimal UI experience. Next, we'll dive into the database design, which is the foundation of a metadata storage. So now let's talk about the database design overview and the database schema for our system that we are designing. This is where many candidates struggle because they hand wave with vague statements. Okay, we'll use a database and we'll use database for these certain, for example, users or posts, but they don't really deep dive that much into the actual schema. So we'll design 5 core tables: users table for user profiles and authentication, posts table for post metadata but not the actual media files, follows table for user to user relationship representing the social graph, likes table as a junction table tracking who liked what, and comments table for the post comments. Let me outline our design considerations now. For database type, we're using SQL, specifically PostgreSQL. And why? Because we essentially have relational data for, and we need asset and transactions, and we need complex joins. So for normalization, we'll use a third nominal form to reduce redundancy and maintain integrity. For sharding strategy, we'll use horizontal strategy sharding by user ID to distribute load and co-locate the related user data. For indexing, we'll create composite indexes based on the query patterns to optimize the read performance. Interview expectations for this section are pretty high, and we need to prepare for this section pretty well actually. You need to show actual table schema with column names and data types and explain foreign key relationships early. And you have to also justify the indexing decisions based on the query patterns and discuss your sharding strategy in detail. Common mistakes include handwaving with, okay, we'll use the database without showing many details about it. Storing media files in the database is definitely wrong, and we need to use object storage instead. Not considering indexes will also make queries extremely slow, and using arrays in SQL columns doesn't scale well and is hard to query efficiently. So now let's look at the user table schema. We'll create a table called users, and the user ID column is a begin primary key with auto increment. The begin supports up to 9 quintillion values, which is far more than we'll ever need. Username is a varchar 30 unique and not null. Instagram actual limit is 30 characters. Email is varchar 255, which is unique and not null, and this is the standard maximal email length as well. Password hash is also varchar 255, not null, and we never store plain text passwords, only the hashes. Full name is varchar 100, and bio is text type for variable content length. Profile pic URL is varchar 500, storing the URL to the image in S3, not the image itself in the database. Follower count is integer with default 0. Following count is integer with default 0. Post count is integer with default 0. Created at is a timestamp with the default current timestamp. Updated at is also a timestamp with the default current timestamp and updates automatically on any row modification. For indexes, we have created an index on the username because it's used for login and search. We created an index on the email because it's also used for login. And we have created an index on created at in descending order for queries like newest users. Now, let's talk about the column explanations. So we'll cover the three key columns here in the users table a bit more in detail. The user ID as a begin support billions of users. The user maximum value is 2 to the 63rd power, which is over 9 quintillion. Even with aggressive growth, Instagram will never exceed this. Username as varchar 30 matches Instagram's actual 30 character limit. The unique constraint prevents duplicate usernames. Email as varchar 255 is the standard maximum email length. We also make this unique. Password hash as varchar 255 stores bcrypt or argon2 hashes, never plain text passwords. This is a security fundamental practice, and thus we should all follow. Full name as varchar 100 can differ from username. Many users have a display name separate from their handle. Bio as a text allows variable length up to Instagram's actual limit of 150 characters. We use text instead of varchar because the length can vary significantly. Profile pic as varchar 500 stores a URL pointing to S3, not the actual image data. Storing binary image data in relationship database is an anti-pattern. Follower count, following count, and post count are denormalized. Instead of running the count queries every time we pre-compute these values, they are updated via database triggers or async jobs. Now let's talk about the indexing decisions. The index on the username is used for logging queries. Select all from users where username is equal to. It's also used for user search. The unique constraint enforces username uniqueness at the database level. The index on email is used for login when users provide email instead of username. It is also used for account recovery flows. The unique constraint prevents multiple accounts with the same email at the database level. The index on created at is in the descending order is used for queries like newest users or users who have joined in the last week. The the descending keyword means that index is stored in the newest first. Now let's talk about the denormalization rationale. So why do we need to denormalize counts instead of calculating them dynamically? Running count on millions of rows is very expensive. If a user has 10 million followers, counting them on every profile view would be very slow. Counts can be updated synchronously through database triggers or background jobs. Eventual consistency is definitely acceptable here. If someone follows you and the count updates 1 second later, users won't notice, and it's not a deal breaker for us. The trade-off is however clear. We trade storage space for query performance. The few extra bytes per row are worth avoiding expensive count queries. Now let's talk about the post table schema. As you can see, we have created the table for posts. Post ID is a big primary key with auto increment. User ID is a big non-null with a foreign key referencing to our users table that we just covered. Image URL is varchar 500 not null, pointing to the full resolution image in the object store in S3. And we have three thumbnail URLs, each varchar 500 for small, medium, and large sizes. Caption is text for post description. Location is varchar 100 for the geographic location tag. Like count is integer default 0 denormalized for performance. Comment count is integer default 0 and also denormalized. Created at is a timestamp, default current timestamp, critical for sorting posts chronologically. We have a foreign key from user ID to users table and user ID with on deleted cascade. This means if a user is deleted, all their posts are automatically deleted too. For indexes, we have a composite index on user ID and created at in descending order. This is critical for the query. For example, get users post newest first. We also have an index on created at alone for general chronological queries. Now let's explain few of the columns and our decision for like why did we come up with these columns for the post database. Post ID as big-int is a primary key and unique identifier for each post. User ID as big-int is a foreign key identifying who created the post. Image URL points to the full resolution image in the object store, AWS S3 or Azure Blob Storage. The three thumbnail URLs point to the pre-generated sizes. Small is 150 by 150 pixels for profile grid views. Medium is 640 by 640 for mobile feed. Large is 180 by 180 for desktop detail view. Caption X text allows us to 2,200 characters, matching Instagram's actual limit, and location as varchar stores pre-users provided location data. The like count and comment count are denormalized to avoid expensive count queries. Created at is crucial for feed generation, which sorts by time. Now, the composite index on the user ID and the created at descending is absolutely critical. Sorry. The index supports the common queries. Select all from users from posts where user ID is let's say 1, 2, 3, 4, 5, ordered by created at descending limit 20. This is a query for get users post newest first. How does this index work? The index was filtered by the user ID, narrowing down to a single user's post. Then the index is already sorted by created at in the descending order. The database can seek directly to correct rows without scanning or sorting. Now let's talk about the index importance. Without this index, the performance would be terrible. The database would scan the entire post table looking for rows matching the user ID, and then it would sort all matching results by created at, which is super expensive. At billions of posts, this would be very slow, taking seconds or even minutes to instead of milliseconds, which is expected out of us. The foreign key with Cascade is important. If a user is deleted, their posts are automatically deleted too. The maintain referential integrity and prevents orphan. So this approach essentially maintains integrity and prevents the orphan post that belongs to non-existent users. Now let's talk about the follows table schema, which essentially represents the social graph of who follows whom. We created a table called follows. Follower ID is a big N, not null. Followee ID is a big N, not null. Created at is a timestamp default, current timestamp recording when the follow actually happened. The primary key is a composite of follower ID and the followee ID. This prevents the duplicates follows and uniquely identifies each relationship. We have foreign keys from follower ID to users table and from followee ID to users table, both with on delete cascade. For indexes, we create an index on follower ID alone, we create an index on followee ID alone, and we create an index on created at descending. Now, let's talk about the follows table, the purpose and structure. The table's purpose is to represent the who follows whom relationship. It's a junction table implementing a many-to-many relationship. A user A can follow user B and vice versa, though the relationship isn't necessarily bidirectional. Let me explain the columns. Follower ID represents the user who is following someone. For example, user 12345 follows a follow ID represents the user being followed. For example, user 12345 follows 6785890. Created at records when the follow happened, like for example 2025 15 January at certain time. Now let's talk about the primary key and indexes. The composite primary key on follower ID and follower ID has several benefits. It prevents duplicate follows. You can't follow the same person twice. It uniquely identifies each follow relationship, and it automatically creates an index on the combination of follower ID and followee ID. Our indexing strategy supports two common queries. The index on follower ID supports the query who does user 12345 follow with select follow ID from followers where follow ID is equal to, let's say, 12345. The index on followee ID supports the query who follows users 67890 with select follower IDs from follows where followee ID is equal to 67890. Both queries are common, so we need indexes supporting both access patterns. So you might wonder, why don't we store follows as an array in the users table? Let me explain why that's not a good idea actually. The wrong approach would be adding a followers or column to the users table as a JSON array. For example, user 12345 has followers like an array of 99, 123, 456, 89, like all the user IDs essentially as an array. And the thing is, it has serious problems. You cannot efficiently index array elements. The query find all posts from users I follow would be extremely slow. Array size is unbounded. Celebrities have millions of followers, so this array would be enormous and very big. You cannot easily query for mutual followers or do any graph analysis. The correct approach is a separate junction table with proper indexes. This enables fast bidirectional queries and scales to millions of relationships per user. Now let's talk about the likes table schema. As part of this, we create a table called likes. User ID is big N, not null. Post ID is big N, null. Created at is a timestamp, default, current timestamp. The primary key is a composite of user ID and post ID. This prevents double liking the same post. Foreign keys actually references both the users table and the post table, both with on delete cascade. For indexes, we created an index on post ID. We created an index on created added descending as well. The design rationale is that the composite primary key on user ID and post ID prevents double liking. The index on the post ID enables fast queries for things like who liked this post. And cascade delete ensures that if a post is deleted, then all its likes are deleted as well, so that we don't have any orphan likes in our database. Now let's talk about the comments table schema. The comments table schema is slightly different. We created a table called comments. Comment ID is a begin primary key with auto increment. User ID is a begin non null. Post ID is a begin non null. Text is text not null for the comment content. Created at is a timestamp default current timestamp. Foreign keys references users and post tables both with on delete cascade. For indexes, we have a composite index on post ID and created at a descending. The design differs from likes. We use comment ID auto increment as a primary key because the users can comment multiple times on the same post. The composite index on post ID and created at suppose the query is get comments for posts newest first. Text type allows us for comments to up to 200 characters. Now let me show you the common query patterns for the tables that we have just covered. To get all the comments for post newest first, we can say that select all from comments where post ID is, let's say, 78946, ordered by created at a descending limit 50. This is served by the composite index on post ID and created at. To check if a user has liked a post, select one from likes where user ID is, let's say, 12345 and post ID is, let's say, equal to 789456. This is served by the primary key lookup, which is pretty instant. Why does likes use a composite primary key while comments use auto increment? Because each user can like a post exactly once, enforced by the primary key, but users can comment multiple times, so we need a unique ID per comment. So now let's talk about the entity relationship diagram. Users have one-to-many relationship with the post table, and as you can see that one user can create many posts. Users can have one-to-many relationship with follows as a follower. One user can follow many. Users have a one-to-many relationship with the followers as the followee, and one user can be followed by many. Users can have one-to-many relationship with likes. One user can like many posts. User can have one-to-many relationship with the comments. One user can write many comments. And posts have a one-to-many relationship with the likes. One post can have many likes. So posts have a one-to-many relationship with the comments, and one post can have many comments, for example. Now, let's dive deep out into the relationship we have over here. So users to post is one to many. One user creates many posts. User to follow as a follower is one to many. One user can follow many. Users to follow as a followee is one to many. One user can follow many users. And so users like is one to many as well. One user can like many posts. Users comment is one to many. One user can write multiple comments. Post to like is one to many. One post can have many likes. And post to comment is one to many as well, because one post can have many comments. Now let's talk about the constraints and normalization. So all foreign key users use on delete cascade. If a user is deleted, their posts, follows, likes, and comments are all also automatically deleted. If a post is deleted, the likes and comments on that post are also deleted. This maintains the referential integrity automatically without requiring application cleanup logic, which honestly you should also do just to be safe, but at the same time we need to do these measures at the database level. This schema is in third nominal form. There are no repeating groups. All values are atomic. All non-key attributes are fully dependent on the primary key. There are no transitive dependencies where non-key attribute depends on another non-key attribute. However, we have introduced denormalization for performance. So follower count, following count, and the post count in the users table are denormalized. Like, and the trade-off here is the consistency for performance. These counts are updated asynchronously, so they might be slightly stale and a bit older, but that's acceptable for better query performance. Now let's talk about the SQL versus NoSQL decision, which is pretty common discussion topic in interviews. So let's talk about why we are prioritizing SQL over here over NoSQL, specifically for this scale. So this is a very critical design decision. For data structure, SQL like post for database store actually for SQL like PostgreSQL provides a well-defined schema and relational model. So NoSQL databases, let's say Cassandra and MongoDB provides flexible schema and document wide column storage. Now, however, for relationships, SQL has a strong support with foreign keys and joins. NoSQL has limited support requiring denormalization. For asset transactions, SQL provides full asset guarantees. NoSQL typically provide limited transactions or eventual consistency. For query flexibility, SQL support complex joins and aggregations. NoSQL primarily supports key value lookups. For consistency model, SQL offers strong consistency. NoSQL typically offers eventual consistency and is limited to that actually. For maturity and tooling, actually, SQL has decades of tools, ORM, expertise, a lot of educational content like books and courses online. NoSQL is much more newer with less tooling available. However, the ecosystem is growing aggressively in the last few years. So now let's talk about Instagram characteristics when it comes to SQL versus NoSQL. So Instagram data has inherently relational characteristics. Users follow users, which is a graph relationship. Posts belong to users, which is a one to many. Likes and comments references both users and posts. Complex joins are needed for feed aggregation, like joining posts with follows to find posts from followed users. We need transactions. Liking a post must be atomic. You can't double. Following a user must update both follower and followee records consistently. Asset guarantees prevent data inconsistencies that would harm user experience. Now, let's talk about a query example. Here's an example query that is natural in SQL but will be super complex in NoSQL. Select post from post, join follows on post.user_id equal to follows.follower_id where follows.follower_id is, let's say, equal to 1 2 3 4 5 ordered by post.created descending limit by 20. This query gets a user's feed by joining posts with their follows. This is straightforward in SQL. In NoSQL, you would need to denormalize heavily, likely storing the entire field pre-computed, which works but is much more complex to maintain. So now let's talk about why, when, and what scenarios does NoSQL make sense. So NoSQL would make sense for different use cases. For logging, metrics, and time series data, Cassandra or InfluxDB would be better. For unstructured data like JSON documents, MongoDB would be appropriate. For key value cache, Redis or Memcache are designed for this. For search functionality, Elasticsearch is the right tool. Instagram actual technology evolution is interesting. They originally used PostgreSQL. Later, they migrated some of their workloads to Cassandra while keeping PostgreSQL for others. The lesson is always start with SQL, migrate to NoSQL only when specific use cases demand it. Don't prematurely optimize. In an interview, this is how I would personally explain this choice if some interview asks me about why would you choose SQL versus NoSQL and how would you do it. So I would say something like, okay, I'm choosing PostgreSQL because Instagram data is inherently relational with complex relationship between users, posts, follows, and likes. SQL provides strong consistency guarantees for critical operations like liking a post, and it supports complex joins needed for feed generation. While NoSQL can scale horizontally more easily, modern PostgreSQL with sharding can handle Instagram sale. And the relation model matches the problem domain better as well. The tooling and the team expertise around SQL are also pretty mature. Now let's talk about the database sharding problem, which is how essentially we will be scaling the database beyond a single instance. The problem is that a single database instance has limits. Storage capacity is limited to the single machine's disk size, the CPU capacity is limited to the single machine cores, and the network capacity is limited to a single network interface card's bandwidth. At Instagram scales with billions of rows, a single instance is definitely not going to make it and is definitely insufficient. The solution is horizontal sharding, also called as data partitioning. Sorry. So we split data across multiple database instances. So what is the strategy over here? So our sharding key is, well, let's go with user ID and let me explain why. Most queries are user centric. Examples include my feed, my post, users I follow. All these queries involve a specific user ID. Sharding by user ID co-locates related data on the same shard. A user and their post live together. This enables single shard queries, which are typically fast, and user IDs are roughly uniformly distributed, so the load is balanced across shards. Our sharding algorithm is modulo based hashing. The formula is shard ID equal to user ID modulo by number of shards. For example, with 1000 shards, user 12345 goes to shard 345, which is 12345 modulo 1000. User 67890 will goes to shard 890, and user 999999 goes to shard 999. So now let's visualize how do we plan to do database sharding here. And let's describe the routing a bit more visually over here. A query arrives with the user ID equal to 12345. The shard router calculates the 12345 modulo 1000, which is 345. It routes the query to shard 345. Meanwhile, shard 0 and shard 99 and all other shards are not accessed for this query. Shard 345 contains about 2 million users, which is 2 billion total users divided by 1000 shards. Now let's talk about the data distribution. How is exactly data distributed across the shards? The user data table is sharded by user ID directly. User 12345 lives on shard 345. The post table is sharded by user ID, specifically the post owner's user ID, not the post ID. A post created by user 12345 lives on the shard 345. This enables co-location. The user and their post live on the same shard. The follows table is sharded by follower ID. The record user 12345 follows user 67990 lives on the shard 345. This enables fast lookup of who does user 12345 follow. Likes and comments are sharded. Tables are sharded by the post owners per user ID. A like on the post by user, let's say 12345, lives on the shard 345. This co-locates the likes with the post metadata. Now let's talk about the configuration. Our shard configuration uses 1000 shards. For each shard contains approximately 2 million users, which is 2 billion users divided by the 1000 shards. The shard growth rate is about 100k users per shard per year. A resharding trigger is when a shard exceeds 5 million users. Now let's talk about the cross-shard queries. Cross-shard queries are pretty challenging. As we consider this query, for example, select all from follows where following ID is equal to 67890. This asks who follows user 67890. The problem is that followers could be on any shard. We must query all 1000 shards and merge the results. The solution for this is to avoid cross-shard queries as much as possible. Denormalize the data if needed, trading storage for query performance, and use caching heavily. Redis can cache cross-shard aggregation. Now let's talk about an important topic, resharding. Eventually, you will need to reshard as you grow, especially Instagram scale. It's a very important and pretty common scenario when because they're growing like hundreds of billions so far every few years. So when should you reshard? When individual shards exceed capacity, either storage or QPS, typically this happens every 2 to 3 years as the user base grows. So how exactly do you reshard? Double the number of shards from 1000 to 2000. Migrate data where necessary. Some users stay on the same shard. For example, users with ID 0, 2000, 4000 all map to shard 0 under both schemas. Other users move to new shards. Use consistent hashing for smoother migration, though that's a pretty advanced topic and we'll cover that in a separate video. Now let's talk about the API design overview. In this at this part of the course, we'll talk about how we can design the RESTful APIs for this specific problem. Our design principles include resource-based URLs. We use paths like users and post and not get users or, for example, create posts. HTTP methods follow REST conventions, get for read, post for create, put for update, and delete for delete. The API is stateless with no server-side session state. We use JWT tokens for authentication. APIs are versioned like v1 post, allowing backward compatible changes. Operations are independent when possible. Multiple analytical requests produce the same exact result, and we use cursor-based pagination for large result sets. Now let's talk about the categories. Our API falls into 4 categories. So the first one is user management APIs, which handle registration, authentication, and profile management. Post APIs handle creating, retrieving, and deleting posts. Feed APIs retrieve the personalized feed, which is the most critical endpoint. Social and interaction APIs handle comment and follow actions. Now let's talk about the interview types specifically for this section. In an interview, you should cover 8 to 10 representative endpoints, not all possible APIs because that will be too much to cover in a 45-minute interview. But try to go for at least 8 to 10. Show request and response formats for each. Explain your authentication strategy, describe your pagination approach, and discuss error handling. Common mistakes include returning entire database objects instead of carefully selected fields, using offset-based pagination instead of cursor-based, making expensive operations synchronous instead of asynchronous, and forgetting API versioning, which causes breaking changes to affect all clients. Now let's talk about register and login endpoints. So let's start, as you can see here, we have described our registration endpoint, which shows us how a new user is created in the system. It's a post request to /v1/user/register with content type application JSON. The request body includes username, email, password, and full name. For example, username could be mukul/abc, email could be mukul@example.com, password could be secure p@password123, and full name Mukul Raina. The response is to one created, which is a JSON body containing user ID, username, email, created at, timestamp, and an access token for immediate authentication. Now let's talk about the validation rules. Validation rules are super important. Username must be 3 to 30 characters, alphanumeric plus underscore. Email must be a valid email format. Password must be a minimum of 8 characters with complexity requirements. Full name is optional with maximum of 100 characters. If the username or email already exists, we return a 409 conflict error with the JSON body saying error, for example, username taken, and messages username Mukul_Oxford is already, for example, registered. Or Mukul ABC, any username that has already been in the system, we just mentioned that it's not available, it's already exists. So now let's talk about the login endpoint, which is represented by /v1/users/login. The request body includes username and password. The response is 200k with the 200 OK with the JSON body containing user ID, username, access token, refresh token, and expires in seconds. The access token is a JWT token that expires in 1 hour. The refresh token is used to get new access tokens. If the credentials are invalid, we return 401 unauthorized with error, let's say invalid credentials and message username and password are incorrect. So let's talk about the get profile endpoint. To get a user profile, send a get request to, for example, /v1/user ID with the authorization header containing the bearer token. The response is 200 OK with JSON containing user ID, username, full name, bio, profile pic URL, follower count, following count, post count, is private flag, is verified flag, and created at timestamp. Important implementation details like follower count, following count, and post count are pre-aggregated and not calculated on the fly. Profile pic URL points to the CDN, not database blob. This is private flag controls the visibility of posts to the non-followers. Now let's talk about the update profile endpoint. To update a user profile, we need to send a pull request. Let's say we endpoint we call as /v1/user ID with the authorization header. The request body includes fields to update like full name, bio, profile pic URL. The response is 200 OK with the user ID and updated at timestamp. For authorization, users can only update their own profile. We check the JWT token user ID matches the path parameter user ID. If someone tries to update another user's profile, we will return them 403 forbidden. Now let's talk about the create post API endpoint, which is represented by /v1/posts with content type multi-part form data. The request includes an image binary file with max 10 megabytes, caption like beautiful day in, let's say, Toronto, or location like, let's say, New York, United States. And the response is 200, 200 or 202 accepted or 201 created. The body includes the post ID, user ID, status, processing, and messages. For example, post is being processed and you will be notified when ready. Now let's talk about the flow where create post is being completion. So one approach we could do is that later via WebSocket or polling, the client can receive the completion notification. The JSON includes post ID, status, published, image URL, thumbnail URLs with small, medium, and large variants and created at timestamp. So why do we return 202 accepted instead of 201 created? Because image processing is async, taking 5 to 10 seconds for a compression and thumbnail generation. We don't want to block the client. We return immediately with the job ID. We notify the client when processing completes via WebSocket or a push notification. And now let's talk about the get users post. To get users posts, send a get request to endpoint. For example, we have is v1/users/user IDs /posts with the query parameters or limit and cursor. The response is 200 OK with the JSON array of posts. Each post includes the post ID, user ID, image URL, thumbnail URLs, caption, location, like count, comment count, created at, and importantly, liked by me flag. This is also a pagination object with next underscore cursor and has underscore more flag. Now let's talk about the cursor pagination. The cursor-based pagination is very critical for our use case here. The cursor format is base64 encoded combination of last post ID plus timestamp. The flow works like this. The first request has no cursor, getting the most recent 20 posts. The response includes next cursor, which is encoded. The second request includes that cursor to get the next 20 posts. So why cursor based instead of, let's say, offset based, which is also another approach? So offset based pagination has a problem. If you request offset equal to 20, limit equal to 20, but the new posts are created between requests, the offset shifts and you will see duplicates. Cursor based pagination uses the last post ID as a reference point that helps avoiding the duplicates. Now let's talk about the get single post endpoint, which is represented by get to endpoint /v1/post ID. The response includes the full post object with an embedded user object containing user ID, username, and profile pic URL. This avoids requiring a second API call to get the user info. Comments underscore preview shows the first 2 or 3 comments The liked underscore by me flag is personalized for the current user. So now let's talk about the embedded data. The embedded data pattern is pretty important for our performance here. We embed the user object in the post response to avoid the n+1 query problem. Without embedding, clients would need to make one request per post to get the user data. We include a comments preview to avoid another API call. The liked by me flag provides personalization without requiring the client to check separately. Now let's talk about the delete post endpoint, which is represented by /v1 post /post ID. The response is 204, no content for success, and if you try to delete someone else's post, we return a 403 forbidden with error forbidden and a message. Let's say you cannot delete your own other people's posts. And the authorization check verifies the post belongs to the authenticated user. Only the post owner can be able to delete their own post. The cascade effect happens automatically. Then deleting the post metadata from the database triggers deletion of the associated likes and comments via foreign key cascade that we covered earlier. Media files are marked for async cleanup in S3 rather than deleting synchronously. Now let's talk about the request and response for the feed API. The feed retrieval endpoint is get/v1/feed with query parameters, limit, and cursor. The response is 200 OK with JSON array of post. Each post includes a post ID and embedded user object with user ID, username, profile pic URL, and is verified flag. The image URLs include a large image and thumbnail URLs for small, medium, and large sizes. Each post has a caption, location, like count, comment count, created at timestamp, liked by me flag, saved by me flag, and a score field. The pagination object includes an X cursor and has more flag. The metadata object includes cache boolean indicating if there was a served from cache and generated at timestamp. Now let's talk about the design decisions that we took as part of building our feed API. First, we embed the user object to avoid the n+1 query problems. Clients get all the data in one request. Second, we provide multiple image URLs so clients can choose appropriate size based on the screen size and network conditions. Mobile and cellular uses small or medium, desktop and Wi-Fi uses large. Third, we included the personalization flags. Liked by me tells if the current user has liked the post. Saved by me tells the user if they have saved it. This avoids additional calls, API calls. Now let's talk about the metadata and pagination for the feed API. Fourth, we included a score field for debugging. So what it does is that this is a ranking score from our feed algorithm. It's useful for A/B testing and debugging. In production, we might remove this to avoid exposing algorithm details. Fifth, we include the metadata. The cache flag tells if the feed was served from a cache. Generated at tells us whether the feed was computed when the feed was computed. This is useful for monitoring and debugging purposes. For pagination, the first request is get feed query parameter limit equal to 20 with no cursor. It returns the 20 most recent or relevant post with the next cursor. Subsequent query requests include the cursor get feed limit equal to 20, cursor equal to let's say ABC 1 to 3, and the cursor encodes the post ID, timestamp, and user ID to maintain the consistency. Now let's talk about the performance. Performance characteristics vary by scenario. So for a cache hit, which is 80% of the request, latency will be 50 to 100 milliseconds served from the Redis. For a cache miss with no celebrities followed, latency will be roughly 300 to 500 milliseconds requiring database queries and ranking. For a cache miss with the celebrities followed, latency can be 500 to 1000 milliseconds in the worst case due to additional queries. Now let's talk about the social APIs like and unlike. So to post, you have to send a post request to v1/post ID/ the response will be 201 created with success true, post ID, like count, and like at timestamp. Importantly, this operation is idempotent. If you send a second like request, we return 200 OK with success true, the same like count message already liked. The database uses insert, ignore, or on conflict do nothing to handle the duplicates. Clients can safely retry without double liking. So now let's talk about the unlike and get likes. To unlike a post, send a delete to the request to /v1/post id/like. The response will be 200 OK with success true, post ID, and updated like count. To get users who have liked the post, send a get request to /v1/post ID/likes with limit and cursor parameters. The response includes an array of objects, like objects with user ID, username, profile pic URL, and liked at timestamp. It also includes a total count and pagination information. Now let's talk about the comment. To comment on a post, send a post to v1 post request to v1 post ID/comments with text in the request body. The response is to one created with the comment ID, post ID, user object, embedded text created at like count starting at 0. The validation ensures that the text is between 1 and 2200 characters. We also implement rate limiting of 10 comments per minute per user to prevent the spam. Now let's talk about the get comments. To get the comments on a post, you can send a request to, let's say, get request to v1/post ID/comments with limit and cursor. The response includes array of comments with each comment ID, embedded user object, text, like count, created at, and liked by me flag. It also includes the total count and pagination. Now let's talk about the follow and unfollow API endpoints. So to follow a user, we'll send a post request to /v1/users/user ID/follow. And the response we expect we are going to return here is 201 created with success true, and follower ID, followee ID, following true, and followed at timestamp. The side effects are important. We increment the followee's follower count, we increment the followers' following count, and we invalidate the followers' feed cache because they will now see new posts in their feed. To unfollow, send a delete request to post/user ID/unfollow. /follow. The response is 200 OK with success true and following is false. Let's talk about the get followers API request. To get a user's followers, we can send a get request to, let's say, the API endpoint /v1/users/user ID/followers with limit and cursor. The response includes an array of users, each with user ID, username, full name, profile pic URL, and 2 personalization flags, followed by me, indicating that if the user is already following this person and follows me, is indicating if the user follows the current user. It also includes the total count and pagination. So now let's talk about the summary and the conventions. So over here, we're going to summarize the key takeaways as part of API design. So we follow the RESTful conventions. We use resource-based URLs with nouns, not verbs. We use appropriate HTTP methods, get for read, post for create, put for update, and delete for delete. Our API is stateless with authentication via JWT tokens. We version our API with the v1 prefix, and we use standard HTTP status codes like 200 OK, 201 created, 202 accepted, 400 bad request, 401 unauthorized, 403 forbidden, and 404 not found, 409 conflict, and 500 internal server error. Now let's talk about the pagination and auth. Our pagination strategy is cursor-based, not office-based, that as we just earlier discussed. The cursor format is base64 encoded combination of the last post ID, timestamp, and the salt. The benefits are no duplicates when new data is inserted, stability across concurrent modifications, and more efficient database queries using seeks instead of scans. For authentication, we use JWT tokens in the authorization header. The format is authorization bearer followed by the token. The token contains user ID issued at the timestamp and the expiration timestamp of 1 hour. We use a refresh token mechanism with short-lived access tokens of 1 hour and long-lived refresh tokens of 30 days. Clients refresh access tokens before expiration. Now let's talk about the rate limiting in this scenario. So the goal of rate limiting is to essentially prevent abuse and fraud and protect our systems for bad actors. For post, and we allow 10 requests per hour per user. For post comment, we allow 60 requests per hour per user. For post likes, let's say we allow 100 requests per hour per user. For get feed, let's say we allow 120 requests per hour per user. And for all the endpoints combined, we allow, let's say, 10,000 requests per hour per IP address. Again, these numbers you don't have to memorize, you don't have to know it off your top of your head, but these has to be a good, reasonable, educated estimates that you share with the interviewer, and they should make sense. For example, likes will be very easy to execute, so that's why likes are like 1,000 requests per hour per user, whereas which is the maximum error. This is not the average number, this is for the absolute maximum. And for post is like 10 requests per hour, which is okay. The user can, how many user posts can they post in 1 hour? But the goal here is not to understand unusual behavior. It's more like to rate limit that, okay, on average, a user probably will post like 1 hour, one post per day, but per hour. But we can definitely, we don't rate limit a user until they cross a certain threshold, which in general is the maximum limit here is 10 requests, which is again a lot of buffer, but we are just being on the safe side here. Now let's talk about the error handling. Error handling uses a consistent format as we have proposed here. So as part of that, every error response includes error code, a human readable message, a timestamp, and a request ID for debugging. For example, a rate limit error would show error rate limit exceeded, message API rate limit exceeded for post/post, timestamp, request ID. Now let's talk about the common mistakes folks do, when they're trying to design an API system as part of the interview question. And these mistakes that you should definitely avoid making in your interview as well. So one of the first thing is returning entire database rows instead of selecting specific fields and creating API specific DDOs. Using offset pagination instead of cursor-based pagination. Making expensive operations synchronous instead of asynchronous processing to accept it. So these are a few of the mistakes, but more mistakes are like, for example, not versioning your API from day one, exposing only database IDs without denormalized data, like embedding user info in the post response, and for example, not making operation idempotent where possible, especially potently. Now we tackle step 5, the feed generation algorithm, which is the most complex component of Instagram. So the challenge is significant. A user follows 500 people. Each person posts about one post per day. We need to generate a personalized rank feed. It must be fast with a target of under 500 milliseconds, and it must scale to 500 million daily active users. So one way to do it is the naive approach, I would say. We would say is that which won't scale. You might try, for example, select post from post join follows on post.user ID equal to follows.followee ID, where follows.follower ID equal to, let's say, 1, 2, 3, 4, 5, order by post.created at descending limit 20. This query joins all the posts from people you follow. The problems here are severe. If a user follows 500 people, this joins 500 users' posts. As scale, if each person has 1,000 posts, this scans 500,000 rows. Sorting 500,000 rows is very expensive, and 500 million users doing this simultaneously would basically really put a lot of strain on your database, which we definitely don't want. So now there are two fundamental approaches to feed generation. So fan out write, or the push model, works by pushing posts to all followers' feed immediately when a user posts. Reading is fast because feeds are pre-computed, but writing is super expensive, especially for users with high follower counts. The second approach is fan out on read, or the pull model, where queries in real time when a user requests their feed. Writing is fast because you just insert the post, but reading is super expensive because you must merge and rank posts on every request. So Instagram solution is actually a hybrid approach combining both, optimized based on the user characteristics. Now let's talk about how it works using this diagram as we can see here. Let's explain the fan out on write. When Alice creates a post with post ID 123, the post service stores the post metadata. It triggers a fan out worker. The worker fetches Alice's followers, which might be Bob, Carol, Dave, and many others. The worker then fans out to all the followers in parallel. It inserts the post ID 123 into Bob's feed cache, Carol's feed cache, Dave's feed cache, and so on. The feeds are now pre-computed. When Bob requests his feed, he queries his feed cache, which is pretty instant. The feed cache returns pre-computed post IDs like 123, 120, and 115. Now let's talk about how we could implement the fan out on write approach. The feed cache structure is ideally stored in Redis in a sorted set. The key will be, let's say, feed user ID. The value is a sorted set of post IDs with scores based on timestamp. For example, feed 12345 contains the post ID 123 with score 17369, like this number, with post ID 120 with score, another score, and the post ID 115 with score, specifically for the post ID. Now, when Alice posts, we store the post in the post table. We fetch all of Alice's followers, say 10,000 users. For each of the follower, we execute ZADD, ZAdd feed follower ID, timestamp, post ID. If the follower is online, we send a push notification. Now let's talk about the pros and cons of this approach. The pros are essentially other fast reads. The feed is already computed. You must read from the cache. So you just read from the cache. So it's simple for the users. There is no merging or sorting on read, and performance is pretty predictable. Read latency is consistent. However, the cons are pretty expensive writes. If a user has 10 million followers, you must write to 10 million caches. That's wasted work. Many users never check their feeds, so the writes are pretty wasted in this case. Here, the celebrity problem is severe. Cristiano Ronaldo, for example, has 600 million followers who would require 600 million writes per post. And storage requirements are high because each user's feed cache can be large. So now let's talk about when this approach ideally works. This approach works for normal users with fewer than, let's say, 10,000 followers. This is 99% of the Instagram users. This approach fails for celebrities and influencers, however, who have like millions of followers. The write cost becomes very big. Now let's talk about the fan out read approach and how it works. So Bob requests his feed. The feed service queries the follow database, asks who does Bob follow. The data returns Alice, Carol, David, and others. The feed service then queries the post database, select post where user ID in Carol, Dave, order by, created at, descending limit 100. The database returns post IDs like 123, 123, 120, 115. Now the feed service merges and ranks these posts using a ranking algorithm. It returns the feed to the Bob. Now let's go through a SQL example for a fan out on read approach. So step 1 is select followee ID from follow, where follower ID is 12345. This returns user IDs, let's say 999, 888, 777. The step 2 will be to select all the posts from where user ID is in these three numbers, 999, 888, 777, and order by created at descending limit by 100. And step 3 happens in the application code actually. We rank the post using an algorithm. Step 4 is returning the top 20 posts to the user. Now let's talk about the pros and cons of this approach. The pros are fast writes. You just insert the post with no fan out needed. There's no wasted work. You only compute the feeds when requested. There's no storage overhead for your pre-computed feeds, and it works for celebrities as well. It doesn't matter if the user has 10 million followers or 10,000 followers. The disadvantage or the cons are slow reads. You must query, merge, and rank on every request. It is expensive at scale. If Bob follows 1,000 users, you query 1,000 users post. The database load will be heavy. 500 million users doing this creates a massive database load, and there is no caching benefit initially, though you can definitely add caching. So now let's talk about the caching optimization here. Even with the fan out on read, aggressive caching is needed. The flow is basically a user requests a feed, check the Redis cache with the key feed user ID. If cached, which is typically 80% of the request, let's say, and return the cache feed in 50 to 100 milliseconds. If not cached, which is let's say 20% of the request, compute feed from database in 300 to 500 milliseconds, store in the cache with 5-minute TTL, and return to the user. So when does this work? This works well for celebrities with millions of followers. It's appropriate for write-heavy scenarios, and it makes sense when storage cost is higher than the compute cost. Now let's talk about the caching optimization we can do here. Even with fan out and read, aggressive caching is needed. The flow is user requests the feed and we check the Redis cache with key, let's say feed user ID. If cached, which is we estimate 80% of the request, we return the cache feed in roughly 50 to 100 milliseconds. If not cached, which is 20% of the request estimated, computed feed from database will take roughly 300 to 500 milliseconds. And then we store it in the cache with 5-minute TTL and return to the user. This works well for the celebrities with millions of followers. It's appropriate for the write-heavy scenarios, and it makes sense when the storage cost is higher than the compute cost. Now let's talk about the hybrid approach. So our hybrid approach strategy essentially uses the best of both worlds. The core idea is using different strategies for different types of users based on the follower count. For normal users with fewer than 10,000 users, we use the fan out on most users fall into this category and write cost is acceptable. For influencers with 10,000 to 1 million followers, we use the fan out on write method with async batch processing to moderate the cost. For celebrities with over, let's say, 1 million followers, we use the fan out on read. Write cost would be otherwise very high and pretty disruptive to our system. So now let's talk about the hybrid approach in a flow diagram. So this graph over here, it shows the implementation, how we can implement this for our system. So when a user creates a post, we check their follower count. If they have fewer than 10,000 followers, we fan out on write, pushing to the follower feeds. If they have more than 10,000 followers, we add it to the celebrity posts pool and store it separately. When a user requests their feed, we check if they follow any celebrities. If no, we read their pre-computed feed from the cache. If yes, we merge their normal feed with the celebrity post, combining the cache data with the fresh queries. Now, let's talk about when normal user posts, like for example Alice with 500 followers, we store the post in the post table. We check the follower count, 500 is less than 10,000, which is our threshold, and we fan out to 500 followers caches, executing the zadd feed, follower ID, timestamp, post ID for each. That 500 writes is pretty acceptable. Now let's talk about the celebrity posts. When a celebrity post like Cristiano Ronaldo with 600 million follower post, we store the post in the post table. Then we check the follower count. 600 million is greater than the 10,000 threshold we have, so we do not fan out. 600 million writes would be very expensive. We mark it as a celebrity post with a flag in the database. We store it in the celebrity post pool, and then just one write, which is very cheap. So now let's talk about the user's read feed. So when a user like Bob requests his feed, we check if the Bob follows any celebrities. We query, select follower ID from follow, where follower ID is equal to Bob and follower ID in celebrity IDs. We fetch the Bob's pre-computed feed from normal users he follows using the zrange feed Bob 0, 50. And then if Bob follows celebrities, we fetch the recent post from those celebrities. Let's say select all from post where user ID in celeb IDs order by created at descending limit 20. We merge both lists, combining normal feed and celebrity post. We re-rank our algorithm and we return the top 20 posts. Now let's talk about the performance comparison over here for both approaches. So for example, for write cost per post for a normal user, fan out on write only would require 500 cache writes. Our hybrid approach only requires 500 cache writes. For write cost per post, for a celebrity, fan out on write only would require 600 million cache writes. A hybrid approach would require just one database write. For read latency with a normal feed, fan out on write only provides 50 to 100 milliseconds to execute. Our hybrid approach takes 50 to 100 milliseconds as well. For read latency with celebrities in the feed, fan out on write provides 550 to 100 milliseconds, whereas the hybrid approach provides 150 to 250 milliseconds. So for storage required, fan out on write only is very high, pre-computing all feeds. Our hybrid approach is medium, only pre-computing for the normal users. So now let's talk about why this works. So 99% of the users have fewer than roughly 10,000 followers, so fan out is cheap for them. 1% of users are celebrities, where fan out would be expensive. So most users follows few or no celebrities, so they use the fast read path. A small percentage pays a slight latency cost for celebrity content, which is pretty acceptable. Now let's talk about the objective and factors for our feed ranking. And essentially, how do we order our posts? The objective is, given the 100 candidate posts, rank them to show the user the 20 most relevant posts first. So now our ranking factor are recency with 40% weight. Newer posts are ranked higher than exponential delay. A post from 1 hour ago ranks much higher than a post from 1 day ago. The formula is recency score equal to E to the power of negative age in hours divided by 24. Again, different companies can come with different feed algorithms, ranking algorithms, and the example that we are given here, this is just like one of the many ranking algorithms. So you don't have to go with this, but again, you have to provide a specific implementation as part of your interview. So now coming back to it, for example, a post from 1 hour ago scores 0.96, a post from 12 hours ago scores 0.67, and a post from 48 hours ago scores, let's say, 0.14. Now let's talk about the engagement. Engagement carries 30% of the weight. Posts with more likes and comments rank higher. The formula is engagement score equal to log 1 plus like count plus 3 times the comment count. So why logarithm? To provide diminishing returns, a post with 1000 likes isn't 10 times better than a post with 100 likes. The log function compresses this range. And why 3 times the weight for the comments? Comments indicate deeper engagement than likes. Someone who takes time to comment is much more invested than someone who just presses the like button. Now let's talk about the relationship and the content in terms of feed ranking. Relationship strength carries 20% of the weight. We prioritize posts from users you interact with frequently. The formula is essentially relationship score equal to likes given by user divided by total likes given plus comments on user's post divided by the total comments. For example, if Bob likes 50% of Alice's posts, there is high affinity. If Bob never interacts with Carol, there is low affinity. Content type preferences carries 10% of the weight. We personalize based on user preferences for photos versus videos on certain topics. So the formula for the content score will be user photo preference times is photo plus user photo preference times is video. And this is learned from the user behavior. If Bob skips all the videos, we'll lower his video preference. Now let's talk about the combined formula for the feed ranking. We could say that essentially for our use case, final score will be 0.4 times the recency score plus 0.3 times the engagement score plus 0.2 times the relationship score plus 0.1 times the content score. Now posts are sorted by the final score in descending order, so the top 20 are returned to the user. Now let's cover an example calculation of feed ranking. Post A has recency 0.95 for 1 hour ago, engagement 0.70 for 50 likes, relationship 0.80 from a close friend, and content 0.90 for a photo. So the final score comes down to 0.82. Post B has recency of 0.60 from 12 hours ago, engagement 0.90 from 500 likes, relationship 0.20 from rarely interacting, and content 0.50 for a video. So the final score is 0.59. And post C has recency 0.90 from 2 hours ago, engagement of 0.40 from 10 likes, relationship 0.95 from a best friend, and content 1.0 for a photo. So the final score comes down to 0.78. So then the ranking essentially becomes A, and then C, and then B. And now let's talk about the production complexity for feed ranking. So in real Instagram production system, the system is much more complex. They use machine learning models, not simple formulas. They incorporate hundreds of features like time of the day, user location, and post topic, and they run A/B testing of different models. And personalization is also per user segment. For an interview, my answer would be, for this interview, I'm using a simplified weighting scoring model with 4 factors: recency, engagement, relationship strength, and content type. However, in production, there would be much more sophisticated machine learning models, which is essentially trained on user interaction data, but the concept is pretty similar. We're essentially trying to predict which posts a user is more likely to engage with. Now let's talk about the caching strategy and the architecture for it. So for that, as you can see, the caching strategy for feed performance uses multiple layers as shown here. So a feed request first checks L1, which is Redis cache with pre-computed feeds. If there is a cache hit, which is 80% of the time, we return the feed in 50 to 100 milliseconds. If there is a cache miss, which is 20% of the time, we go to L2, which is a database and with posts and follows, and we compute the feed and rank post. We update the L1 cache and we return the feed in roughly 3 to 500 milliseconds. Now let's talk about the hit rates. So cache rate hits are essentially cumulative across layers, and these are the different layers. So L1 client cache on the device has roughly 30% individual hit rate and zero network latency. L2 CDN cache has 50% of the remaining 70%, which is 35%, giving 65% cumulative. Network latency over here is 20 to 50 milliseconds. And then L3 Redis cache has 15% of the remaining 35%, which is about 5%, giving 70% cumulative. Network latency here is 10 to 30 milliseconds. And now L4 database query cache has 4% of the remaining 30%, which is about 1%, giving 71% cumulative. Network latency here is 50 to 100 milliseconds. Now the database handles the remaining 29% of the latency of 250 milliseconds, and in practice, over 70% of requests never hit the database. So now let's talk about the Redis structure. Redis structure uses a specific key pattern here. So the key is feed user ID, for example, feed 12345, and the value is a sorted set with post IDs as members and timestamp and scores. We execute ZAD feed 12345, and then with the post 123 to add the post, we retrieve with Z rev range feed 12345 019 to get the top 20 posts, and that's how we try to get the top 20 posts from the Redis. And now let's talk about the parameters for the caching strategy here. So our cache parameters are carefully chosen. So TTL, or time to live, is actually roughly, we start with 5 minutes. This balances freshness versus compute cost. Max items per feed is 100 post IDs, which is more than a user will score. Eviction policy is LRU, which is least recently used, removing inactive users' feeds. Cache size is 15 gigabytes per Redis instance, supporting millions of cache feeds. Now let's talk about the invalidation. Cache invalidation happens in specific scenarios. When a user unfollows someone, we delete their feed cache with delete feed, let's say Bob, and the next feed request will regenerate without Alice's posts. So when a post is deleted, we have two options. Option A is to remove it from all the feeds, which is expensive and not worth it. Option 2 is actually doing nothing and filtering out on read, which is lazy invalidation. Instagram uses option B. So when a user changes settings like muting someone, or we delete their feed cache with delete feed Bob and regenerate without Carol's post. Now let's talk about the hit rate targets. Our cache hit rate targets are very specific. We target 80% cache hit rate with a typical actual performance of 75% to 85%. For P50 latency on a cache hit, we target under 100 milliseconds with typical performance of 50 to 180 milliseconds. For P50 latency on a cache miss, we target under 500 milliseconds with typical performance of 300 to 400 milliseconds. And for P99 latency, we target under 1000 milliseconds with typical performance of 800 to 1200 milliseconds. Now let's talk about the TTL trade-offs. So why should we have 5 minutes TTL? Let me explain the trade-off here as part of the analysis. With 1 minute TTL, you get very fresh feeds but high cache miss rate and heavy database load. With 5 minute TTL, you get good freshness and high hit rate with slight stateless that's still acceptable. With 30-minute TTL, you get very high hit rate but the feeds are too stale, resulting in poor user experience. The decision is that 5 minutes balances freshness and the performance. Now let's talk about the memory requirements for our feed caching strategy. And let's start by calculating the memory requirements here. So average feed cache size per user is, let's say, 100 post IDs times 8 bytes per ID equals to 800 bytes plus solid set overhead equals approximately 1 kilobyte per user. For 500 million active users, that's 500 million times 1 kilobyte equals to 500 gigabytes in total. We split this across multiple Redis instances, perhaps 100 instances at 5 gigabytes each. Now let's talk about the diagram over here as part of the feed generation flow diagram. As you can see here, so let me describe it end to end. So the user requests their feed, we check if the authentication is valid. If not, we return 401 unauthorized. If yes, it is valid, then we check if the feed is in the Redis cache. If there is a cache hit at 80% probability, we return the cache feed in roughly 50 to 100 milliseconds. If there is a cache miss at a 20% probability, we get the user's followees from the follows table. We separate the users into normal users and celebrities. We get the pre-computed feed from the feed cache for normal users. If there are celebrities in the followees, we query celebrity posts from the post table. We merge normal and celebrity posts. We apply the ranking algorithm, scoring each post. We hydrate the post details, getting full objects from the database, and we update the Redis cache with the 5 minutes TTL. And we return to the feed to the client after this. Now, let's start with steps 1 to 3, and let me detail the steps with a bit more timings. So step 1, authentication takes roughly 5 to 10 milliseconds. We validate the JWT token, extract the user ID, and check rate limits. Step 2 is cache check, taking 10 to 20 milliseconds. We execute the Z rev range, feed user ID 0 to 19 in Redis. If it exists, we return immediately as a cache hit. If not, we proceed to generation as a cache miss. Step 3 is getting followees, taking 20 to 30 milliseconds. We query select followee ID is celebrity from follows, where follower ID is equal to the user ID. The result might be follow ID 999 is not a celebrity, whereas follow ID 8888 is not a celebrity. However, followee ID 7777 is the celebrity. Now let's talk about steps 4 to 5. Steps 4A is getting normal users post, taking 30 to 50 milliseconds. And for non-celebrity followees, posts are already pre-computed in their feed cache. We merge from the multiple caches using Redis commands zunion temp feed 999 feed 888 and then zrev temp feed 099. And then step 4B is getting celebrity posts, taking 50 to 100 milliseconds. We query select all from posts where user ID is in 777, then the range and created at greater than and now interval as 7 days, ordered by created by at descending limit by 50. And here step 5 is actually merge and rank, taking 30 to 50 milliseconds. We combine the normal posts and celebrity posts. We calculate the score. We calculate the score for each post using a ranking algorithm. We sort by score descending and we select the top 100 candidates. Now step 6 is hydration, taking 100 to 50 to 100 milliseconds. We query select posts all from user. We select the posts users.username user.profile URL from posts join users on post.user_id equal to users.user_id, where post.post_id in, and then we provide the range. For each post, we check if the current user has liked it with the select one from where the user ID is equal to the current user and the post ID is the post ID. Step 7 is updating the cache, taking 10 to 20 milliseconds. We execute z add feed user ID timestamp 1 post ID 1, z add feed user ID timestamp 2 post ID 2, and so on. And then we expire the feed user ID 300 for 5 minutes TTL. Step 8 is returning to the client, taking 5 milliseconds. We serialize to JSON and then we return HTTP 200 OK response. Now let's talk about the latency breakdown. And the latency actually breakdown varies with the scenario. For cache hit, authentication takes roughly 10 milliseconds, cache check takes 20 milliseconds, generation takes 0 milliseconds, hydration takes 0 milliseconds, cache update takes 0 milliseconds. So roughly total is 30 to 50 milliseconds for the cache hit. For cache miss scenario with no celebrities, authentication takes 10 milliseconds, cache check takes 20 milliseconds, generation takes 50 milliseconds, hydration takes 80 milliseconds, cache update takes 20 milliseconds. So the total for this comes down to 280 to 300 milliseconds. For cache miss with celebrities, authentication takes 10, cache check takes 20, generation takes 250 milliseconds, hydration takes 100 milliseconds, cache update takes 20 milliseconds. So the total is 400 to 450 milliseconds. Now let's talk about the optimization tips. And so the performance optimization tips actually include several techniques. So number one is use parallel queries. Fetch normal posts and celebrity posts in the parallel sequentially. The second is use connection pooling to reuse the database connection instead of opening new ones for each query. Number three is batch hydration. So fetch all posts detailed in one query, not n separate queries. Number four is lazy loading. So don't fetch comments in the feed request. Load them separately when the users expand the post. Number five is compression. So you have to use compression, protocol buffers, or message packets smaller than JSON, which reduce the network transfer time. So now let's talk about the media store challenge. What is the problem here? We need to first now tackle step 6, which is the media storage and the delivery. The scale problem is very significant. For storage requirements, photos updated daily are 100 million. Average photo size is, let's say, 2 megabytes after compression. Daily storage growth is 200 terabytes, which is 100 million times multiplied by 2 megabytes. Annual storage growth is 73 petabytes that we discussed earlier, which is 200 terabytes times 365 days. So the 5-year storage would be 365 petabytes. Now let's talk about the delivery requirements. For delivery requirements, daily photo views are 10 billion, which is 500 million users times 20 views per day. The egress bandwidth, as we previously discussed, is 231 gigabytes per second, which is 10 billion times 2 megabytes divided by 86,000 seconds, and the peak bandwidth is 3 times the average, is 693 gigabytes per second. And now let's talk about the failed approaches for the media storage challenge. So why do traditional approaches fail? Approach 1 is storing in the database, which is bad. You would create a table with photo ID and image blob at, let's say, 2 megabytes per row. So the problems with that will include is that databases are not designed for large binary data. Backups become massive and slow. Queries slow down because you must keep large blob columns. Replication is very costly when replicating 73 petabytes per year, and you cannot leverage CDN because data is locked in a database. Approach 2 is generally storing on web servers, which also fails because it's actually a lot of challenges here. So you store files at, say, one of the folders. The problems that will include is that web servers have a limited disk space. You cannot scale horizontally because which server has its photo. There is no redundancy. Server crash equals data loss. And serving 231 gigabytes per second from origin servers is pretty hard. It's pretty much impossible. So now let's talk about the requirements. So for requirements for a solution is actually pretty clear. So number one is massive scale. We must handle petabytes of data. Number two is high durability. We cannot lose users' photos. We really need to have 11 nines durability. Number three is global delivery. So we need to serve users all over our world, and that too with low latency. So all the geography, pretty much all the continents, specifically for the Instagram use case. Number four is cost effectiveness. So essentially storing 365 petabytes at $25 per terabyte per month equals to actually $9 million per month, which is pretty expensive. And then fast upload. We need to make sure that users won't wait 30 seconds to upload. So we need to make sure that the upload is pretty fast as well. And multiple formats. So for example, we definitely need the original format as well as we need three thumbnail sizes as we discussed earlier. So for small, medium, and the large. So now let's talk about the solution architecture. The solution architecture has four components. Sorry. Object storage for durable, scalable storage like S3 and or Azure Blob Storage. CDN for global edge caching like CloudFront or Akamai. Processing pipeline for async thumbnail generation and compression. And tiered storage for hot recent data versus cold data to optimize the costs. So now let's talk about the features. Why do we need the object storage? And what are the benefits of it? The object storage like AWS S3 or Azure Blob Storage, they are first and foremost designed for scale with exabyte scale storage capacity. Second, high durability at 11 nines means you lose one object per 10,000 years, which is amazing durability. Third, built-in redundancy automatically replicates data across multiple data centers. Number four, it's cost effective at 23 cents per gigabyte per month for S3 standard, which is and with even cheaper tiers for let's say AWS Glacier, for example, for long-term archive purposes. And then fifth is HTTP accessible with direct URL access, so no custom protocol is needed. And sixth is that lifecycle policies automatically move from old data to cheaper storage plans. So now let's talk about the hierarchy. The storage hierarchy is organized pretty carefully actually. So as you can see in the image here, the bucket is named, let's say, Instagram Media Production US East 1. Under the post, we have original containing 2025, then the date 01/15 with files like 789456, original at 2 megabytes. Under the thumbnails, we have small, medium, and large, with each with same data hierarchy. For example, under small, we have dates like 2015, 1/5, we would have the name of the file at 20 kilobytes. Now let's talk about the naming and the URLs for the object storage. The file's naming convention follows the format post_id underscore size.jpg. Example includes 789456 underscore original and then same ID underscore 150 by 150 JPEG, ID underscore as 640 by 640 JPEG, and so on. And benefits include predictable URLs, so you can easily construct them without the database lookup. It's easy to identify which post it is, and the size is included in the file size, the file name right there. And the URL structure varies. The original S3 URL is https s3.amazonaws.com/Instagram media prod /post/original /2025 115 7946 underscore original.jpg. However, after CDN, it becomes https.cdn.instagram.com/post/78946 underscore 1080 by 1080.jpg. In the database, we store the shortened relative path, which is underscore post/7946 underscore 1080 by 1080.jpg, and the application constructs the full URL by prepending the CDN domain. Now let's talk about the partitioning. The database partitioning provides several benefits. The number one is easy lifecycle management. So you can move all of the 20 photos and code to cold storage at once. The second one is better S3 performance by avoiding the hot spotting a single prefix. Number three is simple reason about the growth with X terabytes per month. And the number four is by compliance support. You can delete all the data before date Y, let's say, if required. Now let's talk about the different tiers, storage tiers in Amazon AWS S3 specifically, and how it can be used to optimize the cost. So S3 standard is for recent photos less than 30 days old, costing 23 cents per gigabytes per month with instant retrieval. S3 intelligent tiering is for photos 30 to 90 days old, costing between 23 and 12.5 cents per gigabytes per month with instant retrieval. S3 standard IA or infrequent access is for photos 90 days to 1 year old, costing 12 cents per gigabytes per month with instant retrieval as well. S3 Glacier Instant is for photos 1 to 3 years old, costing 4 cents per gigabytes per month with instant retrieval. And S3 Glacier Deep Archive is actually for photos for over 3 years old, costing less than 1 cent per gigabyte per month. However, the retrieval time here is 12 hours. Now let's talk about the lifecycle policy for the object storage. The lifecycle policy automatically transitions the data. Day 0 to day 30 uses S3 standard, day 30 to day 90 uses S3 intelligent tiering, day 50 to day 60, day 90 to day 365 it uses S3 standard infrequent access, and day 65 365 plus it uses the S3 Glacier instant retrieval. For 5-year storage, the calculation will look like something like year 1 with 73 petabytes cost 73,000 terabytes times $23 equals about 1.6 million per month. Year 2 will be mostly in IA tier, costing 73,000 times multiplied by $12 equal, which is roughly $900K per month. Year 3 and beyond, mostly in Glacier, costs 73,000 times $4, which is equal to $300K, $300,000 per month. So now the total over 5 years is approximately $200 million versus over $500 million if all the data has stayed in the S3 standard. That's why it's very important to know in which tier we're storing the data for the object storage. Now, if we talk about Azure Blob storage, it has equivalent tiers. Hot tier is equivalent to S3 standard, cool tier is equivalent to S3 instant IA, and the archive tier is equivalent to the S3 Glacier, which with similar pricing and the lifecycle policies. Now, let's talk about the diagram here for the image processing pipeline. So if we go over here, as you can see the image here, let me describe how the image upload and the processing pipeline works. So the user uploads the 5 megabytes photo to the API gateway. The API gateway then forwards to the media service, and the media service then enqueues a job in the processing queue, which could be AWS SQS or it could be Azure Service Bus. The media service then immediately returns the 202 accepted with the job ID, let's say ABC123 to the user. Now, meanwhile, an image processing worker picks up the jobs from the queue. The worker compresses the original from 5 megabytes to 2 megabytes JPEG at quality 85. Then the worker generates the thumbnails, small at 150 by 150 at 20 kilobytes, medium at 640 by 640 at 150 kilobytes, and large at 180 by 180 at 500 kilobytes. Now, all the files are uploaded to the object storage, either S3 or Azure Blob Storage. The metadata is stored in the POST database. Images are served through the CDN. Finally, the system notifies the user, let's say via WebSocket or push notification, or it is that the client has been polling. So we notify them through that. Now let's talk about the steps 1 to 3 in much more detail. Processing steps here. So the client sends host/v1/post with content type multi-part form data. Part includes the image as a 5 megabyte JPEG file, caption let's say beautiful day, and location let's say somewhere in the UK. And the client behavior shows an upload progress bar displaying as processing message and not blocking the UI. Now step 2 is API gateway. It receives the upload taking 50 to 200 milliseconds. The actions in this step will include validating the authentication with JWT token, check the file size is under 10 megabytes limit, validate the file type is JPEG or PNG only, and generate the unique post ID and job ID and forward that to the media service. Now let's talk about the step 3, which is when the media service enqueues the job taking 10 to 20 milliseconds. The media service stores the original file in the temporary storage, perhaps an S3 bucket. It creates a job in the queue with JSON containing job ID ABC123, post ID let's say 789456, user ID let's say 12345, original URL and operations to perform. And then it returns the 202 accepted to the client. Now let's talk about steps 4 to 6. So step 4 is when the worker picks up the job, happening 5 to 10 seconds later. The worker pulls the queue for jobs, receives the job message, downloads the original image from temp storage, and begins processing. Step 5 is image compression. That takes roughly 2 to 3 seconds. Using ImageMagick or similar tools, we convert the original to compressed format with quality 85 and strip X the metadata for privacy and apply chroma subsampling. The result is 5 megabytes reduced to 2 megabytes with 60% reduction and minimal quality loss. Now, step 6 is the thumbnail generation, taking roughly 3 to 4 seconds. We generate 3 sizes in parallel, small for profile and grid views. Let's say convert, which will be 150 by 150, and then that will be roughly 20 kilobytes. Medium will be for the feed mobile, which will be 640 by 640, and it will be outputting roughly, it will be in size 140 kilobytes. And large will be for feed desktop, which will be 180 by 180 for outputting for the 500 kilobytes. The caret symbol forces exact dimensions and gravity center and drops from the center. Now let's talk about the steps 7 to 10. So step 7 is essentially the upload to the permanent storage. That takes roughly 2 to 3 seconds. And then for the use case here, we upload 4 files to the S3. The original add S3, media original with the name or JPEG at 2 megabytes, and 3 thumbnails at their respective paths. And parallel uploads complete all of this in roughly about 3 seconds in total. Step 8 is creating the post metadata, taking 50 to 100 milliseconds. We insert into the post table with the post ID and the user ID and the image URL for all the sizes, caption, location, and create at the timestamp. Step 9 is the CDN invalidation, taking 100 milliseconds. Optionally, we pre-warm the CDN cache by sending requests to cache the images at edge locations. For most cases, lazy loading where cache populates on the first request is sufficient. Now step 10 is to notify the user, which takes 50 milliseconds. We send a WebSocket message with event bus, let's say post published, post ID 79456, status is success, and URLs for the large original and the large images. Then the client updates the UI from processing to posted. So the total processing time is the compression is at 2 to 3 seconds, thumbnail generation is at 3 to 4 seconds, S3 upload is at 2 to 3 seconds, and database insert is at 0.1 second for the total of 7 to 10 seconds. The user sees posted after about 10 seconds, but the upload API returned in under 1 second. So now let's talk about the error handling. So if the processing fails, we retry the job 3 times with the queue auto retry. If it's still failing, we mark as failed and notify the user that the upload has failed. Please try again. And then we log the error for debugging and clean up the temp files. Now let's talk about scaling workers. So scaling workers is very important for handling the load of our system. Worker pool configuration starts with 100 workers initially. Each worker processes 6 jobs per minute, which is roughly 10 seconds per job. Capacity is 100 times per 6, which is equal to roughly 600 jobs per minute, equal to 36,000 jobs per hour. Now, peak upload rate is 3000 QPS from our capacity estimation that we did earlier in this video. And then there's 3000 jobs per second times 60 equals to 180k jobs per minute, which is we need 180k divided by 6 equals to 30,000 workers at peak. The solution for this is auto scaling. During normal hours, we run 1000 workers. During peak hours, we scale up to 30,000 workers based on the queue length. Now let's talk about why do we need the CDN and why it's needed. So CDN, the content delivery network, is absolutely mandatory at our scale. The problem with the CDN is severe. User requests images from origin S3 in, let's say, US East 1. A user in Tokyo to US East 1 has 200 milliseconds latency. A user in Sydney to US East 1 has 250 milliseconds latency. A user in London in US East 1 has 100 millisecond latency. And 231 gigabytes per second egress from the origin is just impossible and super expensive. Now the solution is with CDN is much better. Images are cached at the edge locations worldwide. A user in Tokyo to Tokyo edge has 20 milliseconds latency. A user in Sydney to Sydney edge has 15 milliseconds latency. A user in London to London edge has 10 milliseconds latency. Only cache hit misses hit origin, which is roughly 20% of the requests as per the estimation. Now let's talk about the CDN architecture and how it works. So as you can see in this flowchart diagram, we've tried to try to explain how the CDN works. So user in Tokyo requests an image. The request goes through the CDN edge in Tokyo on a cache miss. The edge request from the origin history from origin history in US East 1, and the origin returns the image. The edge caches and serves the image to the user. When the user in Tokyo requests the same image, the request goes through the CDN edge Tokyo on a cache hit. The edge serves from the cache immediately without contacting the origin. Now let's talk about the request flow as part of the CDN architecture. The CDN request flow for the first request, a cache miss, works as follows. The user request, let's say CDN jobs post, large JPEG, DNS resolves to the nearest CDN edge, which is Tokyo for a user in Tokyo. The edge server then checks the local cache. On a cache miss, the edge requests a request from the origin S3. The edge receives the 2 megabyte image taking 500 milliseconds from the origin. The edge caches the images locally, and then the edge serves the image to the user. The total time here is 520 milliseconds. Now for subsequent requests, cache hit works as follows. Another user in Tokyo requests the same image. DNS resolves to Tokyo edge. The edge server checks the local cache. On cache hit is served immediately. So the user receives the image. The total time is 20 milliseconds. Now let's talk about the CDN metrics. So the cache hit ratio targets are roughly 80% with typical actual performance of 75 to 85%. Now the latency on a cache hit targets are under 550 milliseconds with typical performance of 20 to 40 milliseconds. A latency on cache miss targets are under 500 milliseconds with typical performance of 300 to 600 milliseconds. The original bandwidth saved targets 80% with typical savings which is 75 to 80%. Now let's talk about the configuration for the CDN architecture. The CDN configuration uses specific cache headers. So the cache control header is public max age 3153600 immutable. So the explanation here is that the public means it can be cached by CDN and browser. Max age means cache for 1 year, which is 365 days. Immutable means the file will never change, so it's safe to cache forever. Now, why 1 year? Images, they actually never change. If a user edits a post, we generate a new URL with a new post ID. This maximizes the cache hit ratio and reduces the origin load. Cache invalidation is rarely needed actually. When a user deletes a post, we just purge from CDN. When a user updates the post image, we use a new URL, so with the new post ID, so the old cache version is fine. The API call to CDN is post, let's say purge with a JSON body containing URLs to purge. The propagation time to all edge locations will be roughly 5 to 10 minutes. Now let's talk about the CDN architecture, geographic distribution. The geographic distribution of edge location is strategic. The North America has roughly 50 edge locations serving 200 million users. Europe has 40 edge locations serving 180 million users. Asia Pacific has 60 edge locations serving 300 million users. South America has 20 edge locations serving 80 million users. Middle East and Africa have 30 edge locations serving 100 million users. So the total, as you can see, is that 200 edge locations all over the world serving 860 million users for the R use case, which is to design the Instagram. Now let's talk about the cost analysis and in context of the CDN architecture. So the cost analysis shows why CDN is absolutely essential. So without the CDN serving from the S3 origin, egress bandwidth will be, as we calculated earlier in the course, is 231 gigabytes per second times 86,000 seconds per day times 30 days per month, which equals to 600k terabytes per month. S3 egress cost is 9 cents per gigabyte equals $90 per terabyte. Monthly cost is 600 terabytes times $90, which equals to actually $54 million per month. Now, with the CDN, the origin egress at 20% of traffic is 120,000 terabytes per month. S3 egress cost is 120,000 times $9 equal to $10.8 million. CDN egress at 80% from cache is 480k terabytes per month. CDN cost is 8.5 cents per gigabyte equals to $85 per terabyte. And CDN cost is actually 480 times $85 equal to $40 million, which total is $51.6 million per month. Savings are roughly $2.4 million per month, or which is roughly 4.4% reduction. However, but more importantly, user gets 10 times faster load times, and origin servers are not overwhelmed, and the system can actually handle the load. So these are actually the bigger benefits here. So the cost saving is definitely good to have, but the much more bigger benefit is like the ones we just listed. Also know that in practice, CDN providers offer volume discounts for community use, so the actual costs are 50 to 70% lower than the list price. Let's talk about the different CDN providers, including the options currently in the market. So Akamai is used by Instagram and is the largest CDN with the most locations. CloudFront is the AWS native option. It's pretty good if you're already using AWS. Azure CDN is Microsoft's option. It's pretty good if you're using Azure already. And Cloudflare is a popular choice with good performance and DDoS protection. Now let's cover the summarize the architecture decisions we took as part of building our media storage architecture. So the object storage like S3 and or Azure Blob storage designed for petabyte scale with 11 nines of durability. Async processing doesn't really block users during the 10-second thumbnail generation, as we just covered. Multiple thumbnail sizes are needed for optimizing the bandwidth for different devices and their networks. CDN for delivery is mandatory at 231 gigabytes per second egress, providing the 10 times latency improvement. The lifecycle policies move old photos to cheaper storage tiers, saving millions of dollars annually. The date-based partitioning enables easy management and better S3 performance. Now let's talk about the storage breakdown. So the storage breakdown per photo includes 4 files. The original is 2 megabytes. Let's say we start with that. And the large thumbnail will be 500 kilobytes. Medium thumbnail will be roughly 150 kilobytes. Small thumbnail will be roughly 20 kilobytes. So the total per photo storage becomes 2.67 megabytes. And that's a good estimate to share in the interview. Again, the real world scenarios and real world numbers could be definitely different, but this is a good starting point for us. Now, the annual storage is roughly, as we discussed in the capacity estimation section of our course, which was 100 million photos per day, which is multiplied by 2.67 megabytes now times 365 days, which is equal to 97.5 petabytes per year. Now let's talk about the cost of optimization. So the cost of optimization through lifecycle policies provide significant savings over the 5 years. So as we recently covered, and just to recap here as well, the year 1 in hot tier cost $1.7 million per month. Year 2 moving to the IE cost $1.2 million per month. Year 3 moving to Glacier cost $0.8 million per year. Year 4 moving mostly Glacier cost $0.5 million per month, and the year 5 mostly Glacier cost $0.5 million per month. So without lifecycle policies, the constant cost would have been $1.7 million per month equals $102 million over the 5 years. But with lifecycle policies, the total is approximately $60 million over the 5 years. So the savings for us are roughly $42 million, which is 41% reduction, which is pretty significant. Now let's talk about the common mistakes that generally candidates make as part of this section. So number 1 that they propose that storing images in the database instead of using object storage and storing and user URLs in the database. The second mistake they do is that they propose that we can do synchronous image processing, which is absolutely not good. instead of doing the async queue-based processing, because synchronous submit processing is just going to add so much latency. The third mistake that they do is that they do not propose CDN as part of the interviews. So, for example, no CDN is proposed, so everything is going to be a burden on the origin servers, which is pretty bad, and that's going to add a lot of latency as well as the cost as well. The serving origin images instead of generating thumbnails and serving appropriate sizes, another mistake, because then for specific use cases like mobile and things like that, you don't need the full blown image. And then not having lifecycle policies and not implementing them in storage, is actually, you're just avoiding the cost savings. So just by applying the lifecycle policies would have been really beneficial to the company by saving the cost. And then also proposing a single storage region is also, instead of multi-region, is actually very bad for disaster recovery. Now let's talk about the interview talking points and how you should mention this as part of your interview when it comes to the media storage section. So you can start with the conversation about this section with the interviewer by saying that, okay, let's, for example, for media storage, I'm going to use object storage like AWS S3 because it's designed for a petabyte scale and offers 11 nines of durability, which is losing one image over 10,000 years. So it's pretty durable. Images are processed asynchronously now in the system that you are proposing as part of the interview to avoid blocking the user. And then you also propose that you'll be generating multiple thumbnail size for different use cases. CDN is mandatory given the 231 gigabytes per second egress bandwidth requirements. It reduces latency by 10 times that we just covered in a few videos ago, and the origin load by 80%. For the cost optimization, we use the lifecycle policies to automatically move the old photos to cheaper storage tiers, saving millions of dollars annually. Now let's talk about the scaling overview and how, in terms of the flowchart, we can cover that. In terms of scaling to the Instagram scale, every component scales differently. That's one very important thing we need to understand. The application tier has a stateless API service that can be replicated. The database tiers they have shards with primary and replica instances. The cache tier has Redis clusters partitioned by key. The media tier uses object storage that auto scales and CDN with global distribution. And the queue tier has multiple queue partitions for parallel processing. Now, a load balancer routes the request to the API servers. API servers connect to different database shards, different Redis clusters, object storage, and queues. Now let's talk about a few of the strategies we can do for each of the tiers. So the application tier uses horizontal scaling by adding servers. The bottleneck here is the CPU and memory. The solution is auto-scaling based on the load. The database tier uses sharding plus replication. The bottleneck is the storage and QPS. The solution is shard by user ID with read replicas. The cache tier uses clustering. The bottleneck here is the memory. The solution is Redis cluster partitioned by the key. The media tier is a managed service. There is no bottleneck from our side. S3 and Azure Blob storage auto-scale automatically. The queue tier uses partitioning. The bottleneck here is the throughput. The solution is essentially having multiple queue partitions. We'll cover application tier scaling with stateless servers and load balancing, database tier scaling with sharding and read replicas, caching tier scaling with Redis clusters, ASIC processing with queue-based workers, and rate limiting to protect the system. Now let's talk about the stateless architecture when it comes to application tier scaling. Scaling application servers require horizontal scaling but also them being stateless. The key principle here is that the servers themselves, they store no session state locally. The user's first request goes to server 1, which handles the request with no state stored. The user's second request that could go to server 2, which can handle it without needing the server 1 state. And the user's third request, it will go back to server 1 or maybe to a different server, which will work fine without the memory of the first request. So now let's cover that why being stateless here is very important. So any server that can handle any requests, and then by being stateless, servers are interchangeable. You can add or remove servers dynamically, and server crashes, they don't really lose user sessions. So that's why being stateless here is super important. Let's talk about the session storage for our application tier scaling. So where does the session data live? In Redis, which is centralized, where we'll be storing the session data. So we won't be storing it on the application servers. And when a user logs in, a JWT token is issued. The token contains a user ID issued at timestamp and expires at timestamp. The client includes the token in every request so that the server can then, any of the servers in the application layer can then validate the token request. When a server receives a request, it validates the JWT signature stateless with no database lookup needed. It extracts the user ID from the token, processes the request, and returns the response. No server-side session storage is needed here. Now let's talk about the load balancing when it comes to the application layer. Application tier, the scaling part for it. So as you can see in the graph here and the flowchart, so the load balancing distributes the traffic across multiple servers. Millions of users connect through DNS to Instagram.com, and DNS will resolves to a load balancer providing layer 7 HTTP load balancing. The load balancer will then route to the API servers using either, let's say, round robin or other algorithms, and multiple API servers at different IP addresses can then handle the incoming requests. Now, health checks should be running at every 10 seconds for each of the servers. Each server responds to, let's say, get/health with a 200 OK and JSON body containing the status, uptime, connections, let's say memory use percentage. Server responds, it doesn't respond or actually responds with 503. That means the load balancer can then mark it unhealthy and remove it from the pool and then send automated alerts to the operations team. And when the server actually recovers, health check succeed and it's added back to the pool and it resumes start receiving the traffic. Now, to add to that part, a different way of doing infrastructure will have different implementations of this concepts. For example, if you do Kubernetes, it has its own way of checking pods. If any of the pods are not responding or they're unhealthy, there's a way to take them out of the pool and then adding back the healthy pods. So this is the overall concept that you shouldn't mention the interviewer, but then you can briefly cover the implementation as well. For example, how would this work in a Kubernetes scenario? Now let's talk about the load balancing algorithms that you should ideally briefly cover in the interview process. So the load balancing algorithms contains multiple several options that could be considered. So the round robin actually distributes the requests sequentially. I use this when servers have equal capacity and you just want to have a simpler solution to get started with. The least connections approach send requests to the server with the fewest active connections. Use this when the request duration varies quite a bit. And then the weighted round robin gives some servers more traffic by weight, and use this when there's like mixed server capacity. IP hash ensures the same client IP always go to the same server. I use this for sticky sessions and if that's the scenario is needed, though we generally tend to avoid this approach. For Instagram's choice, it's mostly preferred to have the least connections because the requests vary in duration. Feed requests, they take much more longer than the like requests. Now let's talk about the health checks. So health checks are very critical for reliability. The load balancer pings each server for every 10 seconds with the get health request. A healthy response is ideally 200 OK with JSON showing status is healthy, uptime in seconds, active connection counts, and memory use percentage. If the server actually doesn't respond or returns a 503, the load balancer of the system can mark it unhealthy, let's say Azure front door, and then remove it from the load balancer board and stop this sending the traffic and alerts the operations team. And just to cover that, Azure front door is one way, but the actual load balancer in Azure ecosystem would more likely be application gateway, for example, or a different way to do in the Kubernetes, which we'll cover in a bit. Coming back to it, when the server actually recovers and the health checks are performed in it and they succeed, it's added back to the pool and then it will start resuming traffic just like any other normal servers in the pool. Now let's talk about the auto-scaling part. So the auto-scaling responds to load changes that are happening dynamically. So scaling triggers to add servers includes generally average CPU, let's say over 70% for over 5 minutes, average memory over 80% for 5 minutes, or request queue length for more than, let's say, 100. The scaling triggers to remove servers that would include like average CPUs under 30% for 15 minutes, or average memory is, let's say, under 50% for 15 minutes. The configuration generally sets to add 100 servers always running, or maximum instances at 10,000. Scale up by adding 20% more servers, or scale down by removing 10% of the servers gradually, and cool down of, let's say, 5 minutes between the scaling options. Now let's talk about the server specs and the capacity. So the server specification per applications per server are, we can go with, let's say, 8 core CPU with 32 gigabytes memory and 10 gigabytes per second traffic, with capacity of, let's say, around 1000 concurrent requests. For 300k peak UPS, assuming 100 milliseconds average request duration, concurrent requests are 300k times 0.1, which equals to 30,000. So the server needed are 30,000 divided by 1000 equal to 30 servers at the minimum. With the redundancy at 2 times, we need 60 servers. So with headroom, we deploy roughly 100 to 200 servers. Now let's talk about the deployment part. Deployment strategy should aim to achieve roughly zero downtime through the rolling, deploying to 10% of servers, which is 10 out of 100. Monitor the error rates and latency. If the metrics are good, deploy to the next 10%. Repeat until all servers are updated. If the issues arise, you can always roll back the affected servers, so it's better to do it in parts of rings by 10% as 10%. The total deployment time should be roughly 30 to 60 minutes with ideally no downtime, because 90% of servers that way are always available. Now let's talk about the read replicas diagram here. So as you can see, database read scaling uses replication. The problem is that the feed reads at roughly 100k QPS. A single database primary handles maximum at 10,000 QPS. So we need definitely 10 times more the read capacity. The solution is read replicas. Write requests like post go to the primary database for both read and write, and read requests like get feed or get post, get feed, for example, go to read replicas 1, 2, and 3 respectively, which are read only. The primary database asynchronously replicates to replicas with, let's say, approximately would be 100 to 500 milliseconds lag. Now let's talk about how replication works and involving both read and write paths. So the write path, the application would send, insert, update, or delete to the primary. Primary will execute the query. Primary writes to the transaction log called WAL, write a head log, and then the primary send the log to replicas asynchronously. Replicas apply the log entries to their local copy. Replicas catch up, typically under 100 to 500 milliseconds behind the primary. The read path uses the application routing logic. If the query is write, like insert, update, or delete, they send it to primary. If the query is read, like select, send to, let's say, replica using a round robin approach that we just covered for the server routing as well. Sorry. So now let's talk about the replication lag. Replication lag typically ranges from 100 to 500 milliseconds. And let's talk about a scenario that demonstrates a lag in our scenario. So let's say user creates a post, it writes a post to the primary at time 0. A replication happens at time, let's say, 200 milliseconds. So user immediately requests their post, reading from replica at, let's say, time 100 milliseconds. The replica has not received the write yet due to the lag. So, sorry, the user won't be able to see their new post. So what is the solution here? The solution is a read after write consistency. After a write, a read from the primary for that user's data would be for a short time window. So let's talk about the read after write pattern. The read after write consistency, actually the pattern works as follow in the code. So this is a Python code, but you can do a similar thing based on how your application is coded, whether it's C# or JavaScript. So when creating a post, we write to the primary database, then mark the user as a recently wrote in cache with the 5-second TTL. When getting user's post, we check if the user recently wrote. If yes, then we read from the primary for a strong consistency. If no, then we read from the replica because eventual consistency should be okay. This ensures users see their own writes immediately, while most reads use replicas for better performance. Now let's talk about the replica configuration. A replica configuration per shard includes one primary handling writes plus some reads, and three read replicas handling the most reads. The read distribution should be as follows. The primary will handle 10% of the reads for read after write cases. Replica 1 will handle 30% of the reads. Replica 2 will handle 30% of the reads. Replica 3 will also handle the 30% of the reads. For example, shard 0 has primary handling of let's say 10,000 QPS plus 1,000 read QPS. Replica 1 will be handling 3,000 read QPS. Replica 2 will be handling 3,000 read QPS, as well as replica 3 will also be handling the 3,000 read QPS. So as you can see, the total capacity now is 100,000, 10,000 read per QPS per shard, which what we needed. Now let's talk about the failover. So the failover provides a disaster recovery when a primary fails, and this is a very important thing you should cover as part of your interviews. So let's say the monitoring detects that the primary is down for let's say 10 to 30 seconds. The system promotes replica 1 to primary. The application config is updated to redirect writes to the new primary. A new replica spins up to replace the promoted one, and the total downtime should be ideally 1 to 2 minutes. The total database infrastructure should be ideally 1000 shards times 4 instances, which is 1 primary plus 3 replicas equals to 4000 database instances. The cost per instance will be roughly $500 per month for let's say R5.2x large equivalent on AWS, and total database cost will be roughly 4,000 times $500 equals to $2 million per month. This is pretty significant, but actually, unfortunately, this isn't necessary at the Instagram's level of scale. So now let's talk about why do we need to shard, and what is the business requirement, technical requirement for sharding. The storage limits. So number one is like single PostgreSQL instance, for example, has about 10 terabytes of practical limit. Instagram data is 36 terabytes megabyte per year plus historical data. So we definitely need multiple databases. Write throughput limits. That's the second reason. Single instance handles about 10,000 writes per second. Instagram's write load is roughly 1200 writes per second, which is manageable now, but with growth, we need the headroom and the buffer. The read throughput limits are solved by the replicas, but even with replicas, a single primary becomes a bottleneck for the writes. Now let's talk about the schema details. A sharding schema that we are proposing here uses 1000 shards from shard 0 to shard 999. The shard determination uses a formula. Let's say we go with shard ID equal to user ID modulo 1000. And the example would be, let's say we go with user ID 12345 goes to shard 345, user ID 67890 goes to shard 890, user ID 99999 goes to shard 999. Each shard will contain roughly approximately 2 million users, which is 2 billion users divided by the 1000 shards, and approximately 200 million posts, which is 100 billion posts divided by the 1000 shards, assuming equal distribution. It also contains follow, likes, and comments for those users. Now let's talk about the data co-location. So data co-location should work as follows. The user table is sharded by user ID directly. The user 12345 should go to shard 345, and the post table is sharded by the user ID. So specifically the post owner's user ID, not the post ID. So a post created by user 12305 will go to post shard 345. Now let's talk about why. Because the query get all posts by the user should ideally stay on a single shard, which will be much more faster for the query performance. Now the follows table is sharded by the follower ID. The record user 12345 follows user 67890 will go to the shard 345. Why? Because the query get users I follow stays on the single shard. Now, likes and comments are sharded by the post owner's user ID. So a like on a post by user 12345 should also go to shard 345. Why? Because the query like get likes from my post will this way stay on the single shard, and which will be good for the query performance. Let's revisit the query patterns we just discussed. The query patterns typically fall in the two categories. So the single shard queries are pretty fast. To get a user's post, it will be like select all from post where user ID is equal to 12345. This routes to shard 345 only. To get the users I follow, it would be like select all from follows where follower ID is equal to 12345. This will also route to shard 345 only. Now to get likes on my post, it will be like select all from likes where post ID n select post ID from post where user ID is, let's say 1205. This will also route to the single shard 345 only, which is again will be good for the performance. So the cross shard queries are actually slow and should be avoided. To find out who follows me, in this case would be like select all from follows where follow ID is 12345. This problem is followers could be on any shard. You must query all 1000 shards. The solution for this is to either denormalize or cache this data. Now let's talk about the shard router. The shard router ideally lives in the application layer. So in code, we create a class called shard router. It will initialize with 1000 shards and maintain the shard connections mapping shard ID to the database connection. The get shard method takes the user ID and returns the user ID modulo number of shards. The execute query method then takes the user ID and query and get the appropriate shard and execute the query on that specific shard. So again, this will be all part of the application layer code. The usage is pretty straightforward. We create a router instance and execute queries like post equal to router.execute query with user ID 12345 and query select all from post where user ID is 12345. Now let's talk about resharding. Adding new shards to resharding becomes pretty necessary over time as the number of users grow, number of usage grows. So when to reshard? So individual shards exceed, let's say, 10 terabytes. The write throughput, let's say, it exceeds the capacity on a shard, which is typically every 2 to 3 years. So now let's talk about how to reshard. You can start with doubling the number of shards from 1000 to 2000. For each user, calculate the old shard ID as a user ID modulo 1000 and the new shard ID is user ID modulo 2000. If a different shard, migrate then the data. Some users will stay on the same shard. For example, user ID 0, 2000, 4000 will all stay on shard 0. Some users, they would need to move to the new shards. The migration strategy uses a background job that will migrate one person of users, let's say per day, taking roughly 100 days per role. The application reads from both old and new shards during the migration, and once the migration is complete, then we decommission the old shards. Advanced techniques like consistent hashing reduce the data movement during the resharding, so they should definitely be considered when you're doing this in the production. Now let's talk about the multi-layer overview for our caching strategy. So the multi-layer caching strategy provides performance at each of the different levels. The cache hierarchy starts with the client request. L1 is client cache in the mobile app local storage. L2 is the CDN cache at the edge locations worldwide. L3 is allocation cache in the Redis for feed and user data. L4 is the database query cache in the PostgreSQL internal. And finally, the end database itself. On a request, we first check L1. On a hit at let's say 30%, we return with 0 network latency. On a miss, we check with L2. On a hit here at 50% remaining, we return with 20 to 50 milliseconds of latency. On a miss, we check then the L3. On a hit at 15% remaining, we'll return with either roughly 10 to 30 milliseconds latency. On a miss, we check L4. And on a hit at a 4% remaining, we return with 50 to 100 milliseconds latency. On a miss at 1% remaining, then we'll query the database with 200 to 500 milliseconds latency. Now let's talk about the L1 client cache. The L1 client cache in the mobile app caches several things. And again, this could be mobile app or a front end React.js app. So now what should be cached? The user's own feed for the last 100 posts, the user's own post should be cached, recently viewed post, and user profile they have visited. What would be the ideal storage location? Okay, that will vary by the platform. On iOS, it should be either core data or NS cache. On Android, it should be, let's say, room database or shared preferences. TTL is until the app restart or explicit refresh. Now, the benefit will include instant load with zero network latency, offline viewing capability, and reduced data usage. The invalidation happens when the user pulls to refresh, or the app is restarted, or the user explicitly clears the cache. Now let's talk about the L2 CDN and L3 Redis cache. So the L2 CDN cache for media files was covered earlier in the media storage section for this course. And over there, what is cached, just to recap, will be image and videos with TTL of 1 year because URLs are immutable. So the hit rate over here will be 80 to 85%. For the L3 application cache in Redis will be caching several data types. The user feed with key pattern field, let's say user ID, has 5 minutes TTL, 1 kilobyte of size for pre-computed feeds, and user profile with key user user ID has 1 hour of TTL with 500 byte size to avoid the user table queries. For post metadata with key post ID has 1 hour of TTL, 1 kilobyte of size to avoid the post table queries. Follower count with key like count followers user ID will be having 10 minutes of TTL, 8 bytes of size for aggregated counts, and the like count with key will be like count likes post ID will be having 1 minute of TTL, 8 bytes of size for the real time counts. Now let's talk about how we should structure our Redis cluster. The Redis cluster configuration uses roughly, we can propose for this use case 100 Redis instances, each with 32 gigabytes of RAM. So the total cache capacity will be 3.2 terabytes. Data is partitioned by, we can do it by key using the consistent hashing algorithm, like concept that you should definitely cover for the interview, and we'll cover in a separate video just in a short while. So replication should use 3 replicas per master. The total will be 100 masters plus 300 replicas equal to 400 Redis instances. And now, how would the failover work? The failover is pretty automatic. When a master fails, automatic promotion of replica occurs. Redis Sentinel monitors the health, and failover completes in roughly sub-second time. Now let's talk about the eviction and warming. So the cache eviction we are proposing here, it uses LRE policy, which is to least recently used. So what happens when the memory is full? We identify the least recently accessed keys and we evict those keys to make room for the new data. Then, for example, if a user hasn't loaded the app in let's say 6 months, their feed cache hasn't been accessed, so it gets evicted to make room for more active users. Cache farming preloads the data for VIP users like celebrities. We pre-compute their feed every 5 minutes before the cache expiration. This ensures that the feed is always cached. They never experience cache miss. And they should, because these are the celebrities, so they will make the most amount of noise if they have a bad experience on our platform. So we should definitely try to avoid the cache miss for them. A background job should be running idly every 5 minutes for each VIP user. If a cache is expiring soon, recompute their feed and update the cache. Database cache. So the L4 database query cache, it will be in the Postgres internal caching. And the Postgres SQL cache query plans for past queries, shared buffer cache for frequently accessed pages, and OS page cache at the file system level. Configuration is PostgreSQL.count sets shared buffers to 32 gigabytes for frequently accessed data and effective cache size to 96 gigabytes for total RAM cap for caching. The benefit here is that the repeated queries will be much more faster with no disk I/O required. Now let's talk about the invalidation strategies. So cache invalidation uses different strategies that we will be covering now. So the first one is the write-through cache. The write-through cache updates both the database and the cache. In code, when updating a user profile, we first update the database with, let's say, update user set bio equal to, and then where user ID equal to X. Then we delete from the cache with, let's say, cache or delete where user ID to invalidate the old cache. And optionally, we also pre-warm the cache by fetching fresh data and storing it. Now, the lazy invalidation approach is relatively simpler. So when deleting a post, we just delete from the database with, let's say, delete from post where post ID is equal to this. We do not invalidate the caches immediately. Which would be pretty expensive. So what we do actually is that we let them expire naturally by TTL. So on a cache hit, we check if the post exists. If not, we treat it as a cache miss. Now let's talk about the async processing and why do we need it and what are the use cases for it. So the main benefit of async processing is that it improves the user experience pretty significantly. So if we compare the synchronous versus asynchronous approaches, synchronous is pretty bad for expensive operations. Like for example, user uploads a photo, server processes for 10 seconds, user waits and then gets a response. This is not ideal. Asynchronous is pretty good, where user will upload a photo, server queues the jobs in 100 milliseconds, user will get a response in 202 accepted. The processing, now it will happen in the background. So the UI is not blocked. And then, at least the experience is still much more better than the complete blockage in the synchronous programming and synchronous approach. Now let's talk about the use cases for asynchronous processing. This includes several operations. The number one will be the image processing for thumbnail generation, which is very CPU intensive, which takes roughly 5 to 10 seconds. Then the second operation is feed fan out, which involves writing to millions of follower caches, which roughly takes 10 to 60 seconds. The third operation is the email notifications, which require calling slow third-party APIs, let's say Mailchimp, which take roughly 1 to 5 seconds. The analytic events aren't very time critical, so we can use batch processing for them. The push notifications, they also call third-party APIs, let's say UrbanShip or FCM or APNs, which also take roughly 1 to 3 seconds. And again, these are the very good examples where async processing should be considered. Now let's talk about the architecture for async processing. So as you can see in the flowchart, to start off with the API server, for example, can queue the jobs to 3 different queues. Image queue using the AWS SQS to handle the image processing, feed queue which handles the feed generation, notification queue which handles the notifications. Now the worker will start consuming from these queues. Image worker 1 and 2 consume from image queue, feed worker 1 will consume from feed queue, notification worker will consume from the notification queue. The worker will start performing their tasks. The image workers will process and store in AWS S3. Feed workers will update the caches in the Redis. The notification workers will send push notifications to APNs. Now let's talk about the technology options we have. So the message queue technology includes several options that we can consider. So the number one is AWS SQS, which is a general purpose and managed handling of up to 10,000 plus messages per second per queue. Azure Service Bus is also an Azure native solution, which is very similar to SQS, and it also handles roughly up to 10,000 plus messages per second. RabbitMQ is a self-hosted with flexible routing. It can handle up to 20,000 messages per second, but again, for this now you have to do the whole self-hosting yourself and involves more operations. Apache Kafka provides a high throughput streaming, handling up to 1 million messages per second, but again it comes with more operations and more operation costs that will be for your dev team. Now for the Instagram choice, we'll recommend that you use a combination of these. So SQS will be ideal for the most jobs because it's managed by AWS and reliable, so you don't have to do the DevOps part yourself. And Kafka could be considered for very high throughput analytical events where you're just collecting a lot of high throughput analytical events from different events that is happening in your architecture. Now let's talk about sample message format as part of the asynchronous processing. So the queue message format structure should be pretty clear, and this is one of the examples. So any image processing job will be including job ID, let's say APC123, job type, let's say process image, post ID 789456, user ID, let's say 12305, original image URL, and let's say S3 temp bucket, operations array containing the compress and generate thumbnails, callback URL, let's say API v1 post 78946, upload complete, and created a timestamp and the priority as normal. Now let's talk about the worker logic. So worker processing follows a standard pattern. And again, this code example is in Python, but it'll be similar in C# and Java. So it's pretty code agnostic. Consider this as a pseudocode for now. So the worker will run in a continuous loop. It pulls a queue for messages with max messages, let's say 10, and wait time for 20 seconds. For each message, it tries to parse the job from JSON, process the image, and delete the message to mark it as complete. On exception, it logs the error and leaves the message in the queue. The queue will then retry after the visibility timeout. Now let's talk about the retry logic. The retry logic should be ideally using high visibility timeout, ideally for 30 seconds. So if we talk about the normal flow, the worker will receive a message will become invisible to other workers for, let's say, 30 seconds timeout. The worker processes in 10 seconds and the worker then deletes the message, marking it as complete. Now if we talk about the failure flow, the worker will receive the message will be invisible for 30-second timeout. Worker, let's say, it crashes without deleting the message. After 30 seconds, message becomes visible again. Another worker will then pick it up for an automatic, let's say, retry. So the max retry should be ideally 3 attempts. After 3 failures, we should move the message to the deleter queue for manual inspection. Now, let's talk about the scaling and the priority. So the worker auto scaling should be responding to the queue length. For example, if the queue length exceeds 1,000 messages, you should scale up to the worker's batting 20%. If the queue length is under 100 messages for 10 minutes, scale down the workers, let's say, by removing the 10%. The configuration should be, let's say, set minimum workers at 100, which is always running, maximum workers at 10,000 with target to process, let's say, all the messages within 1 minute. And then if we talk about the priority queues handle urgent work first. So the high priority queue handles the celebrity posts and verified users processing first so that they have better user experience, at least the ideal user experience, so that because they are very important to our business. So the normal priority queues can handle regular users. Processing after high priority queue is empty. Now if we talk about the implementation, it will have the workers that pull high priority queue first and then the normal queue. Now let's talk about the rate limiting, why it's necessary for the business, for our architecture, and what are the different tiers for rate limiting. So rate limiting and throttling can definitely are ideal for protecting our system from abuse. So what is rate limiting and why is it needed? So it protects against abusive users like bots scraping data, buggy clients with infinite loops making requests, DDoS accounts, and unfair resource usage where one user tries to maybe consciously or subconsciously overwhelm the whole system. Now the rate limit tiers will include per user limits. Post allows, let's say, for 10 per hour to prevent spam posting. Post comments will allow, let's say, 60 per hour to allow engagement while also preventing spam. The post likes will, let's say, around 1,000 per hour. Let's say user can keep liking, but which is still high for normal usage. But at the same time, we have to balance highly engaged users with also not just doing spam behavior. So now for the get feed, we'll ideally do, let's say, 120 per hour, which is roughly 2 per minute. And the get user ID will allow 300 per hour for profile browsing. Post follows will be around, let's say, 200 per hour to prevent aggressive following so that people are just not blindly following everyone. And all use should be rolling 1 hour windows. It's for rate limiting. So per IP limits provide broader protection for rate limiting. So all the endpoints will ideally combine. The rate limit should be for around 10,000 per request per hour in a rolling 1 hour window. For authentication endpoints, allowing 20-minute attempts per minute in a rolling one-time window. The sign-up allows should be ideally 10 accounts per day in a rolling 24-hour window. So now let's talk about the token bucket algorithm. So this is how essentially the token bucket implementation algorithm works. So for our specific use case, the bucket should ideally hold tokens with capacity equal to the rate limit. The refill rate adds 1 token per minute for a 60 per hour limit. When a request comes in, if a bucket has a token, consume 1 token and allow the request. If the bucket is empty, reject the request for 429 too many requests. Now, for example, with the 10 requests per hour limit, bucket capacity will be 10 tokens. Refill rate is 10 tokens divided by the 60 minute equals to 1 token every 6 minutes. User make 10 requests rapidly, all will succeed consuming 10 tokens, and when the user makes 11 requests, rejected will be happen because no tokens will be left. After 6 minutes, 1 token is added back, so user can then make 1 more request. Now for rate limiting, let's talk about how we can implement this in the Redis. And this is a sample implementation code given for Redis. So the function code will be the function check rate limit takes, let's say, user ID, endpoint, limit, and window. The key is the rate limit, user ID, endpoint. We get the current token count from Redis. If the current is nil, it's the first request. So the initialize the bucket with, let's say, set ex key window limit -1 and allow the request. Now, if the current is greater than 0, tokens are available, so decrement with the DECR key and allow the request. If the current is 0, no tokens remain, so get TTL with TTL key and reject the message. Rate limit exceeded, let's say retry after TTL seconds. Now, how is it usage used in the API? So if not, check rate limit for user ID, endpoints, let's say n/post, limit is 110, window 3600, then we'll return the response 429 with error, rate limit exceeded, and message you can only create 10 posts per hour, and retry after will be in the seconds. So now let's talk about the sliding window for rate limiting. So as you can see in the code, the implementation is much more accurate than the token bucket implementation that we just covered. So the sliding window, it actually counts the actual request in a rolling window using a Redis sorted set with the timestamp as a score. The function sliding window rate limits here takes the user ID, endpoint, limit, and window. And the key is rate limit, user ID, endpoint. The current time is now, and the window start is now minus window. We use Redis pipeline for atomic operations. We remove the old requests outside the window with Z rem range by score, key 0, window start. We count requests in the current window with Z card key. We add the current request with Z add key now, now, and we set the expiration with expire key window. Then we execute the pipeline and get the results. Request count is results or results 1. If request count is less than the limit, we allow, otherwise we reject. Sorry. Now let's talk about the response headers and bypasses. So the response headers inform the clients of the rate limit status. And the clients here could be our mobile application, our desktop application, or web applications. So the successful request returns HTTP 200 OK with headers like X rate limit, limit 60, X rate limit remaining 42, X rate limit reset 1376956 Now, when the rate limit is exceeded, we return HTTP to 429 too many requests with headers, retry after 1800, X rate limit 60, X rate limit remaining 0, X rate limit reset 136956800. So body will contain the error, which should be ideally something like rate limit exceeded, with the message like API rate limit exceeded for the specific endpoint, let's say post, and then we have a retry after seconds, which will be 1800. So now let's talk about the bypasses for trusted clients, including VIP users, verified accounts, and Instagram staff, which are getting higher limits at 100 times, let's say normal limits, with separate rate limiting pools. So the internal service should have ideally no limit pools for these special use cases, and then we authenticate them with the service tokens. Mobile app gets much more lenient treatment than the web app because with 2 limits for much better user experience. Yeah, now let's talk about the key trade-offs here. So the key trade-off as part of the step 8 will find the design decisions. So the trade-off one is the consistency versus availability, which is a pretty famous CAP theorem that we should definitely should cover in the interview. So for feed consistency, we choose the eventual consistency. Feeds don't need real-time perfect accuracy. For likes and follows, we choose strong consistency. You cannot double without the reasoning. Critical operations need ACID. So our availability target is 4 of 9s, and we prioritize availability over perfect consistency. So what are the implications of it? So the users might not see their own post immediately in the feed due to replication lag. This is pretty acceptable, better than the system actually going down. Critical operations involving money or security would definitely need stronger consistency. Now, the second trade off is SQL versus NoSQL. So, for SQL versus NoSQL, for data models, SQL was chosen as it provides relational structured data. NoSQL alternative will provide flexible schema. For relationships, SQL has native support with joins. NoSQL is providing us denormalization, which actually requires denormalization. For transactions, SQL provides asset guarantees, whereas NoSQL provides the eventual consistency. So for scaling, SQL uses vertical plus sharding. NoSQL uses horizontal, which is easier in implementation. For query flexibility, SQL enables complex joins, whereas NoSQL is limited to primary key value lookups. So now let's talk about why SQL is ideal for some of the use cases for Instagram. For example, user post follow relationships are inherently relational. So we need transactions for likes and follows, as well as complex queries are needed for the feed generation. Team expertise and tool maturity also favors SQL since it has been there for decades. We had a lot more expertise, education content available, and more training for the folks available for SQL. So now let's talk about when NoSQL would be better. So NoSQL would be better when unstructured data like logs and events would be needed to be stored, and extreme write throughput at millions of writes per second might be needed. And another use case where NoSQL would be better than SQL would be, let's say, simple key value lookups. So the trade-off 3 is essentially fan out on write versus fan out on read. So the fan out on write has pros and benefits as it has fast reads because the feed is pre-computed, whereas the cons is that it's expensive writes for celebrities with the high fan out. And fan out on read has pros like fast writes with no wasted work, and the cons is that it's slow reads requiring the expensive queries. Now let's talk about why would we prefer hybrid. So hybrid has pros like best of both worlds. At least we try to do that. And cons is that it's much more complex to implement. And let's talk about when should we try to use hybrid. So normal users, as we covered, with under 10,000 followers will use fan out on write, whereas celebrities with over 10,000 followers will use fan out on read. Now let's talk about why we should consider hybrid. So for 99% of the users, ideally like Instagram, will benefit much more from fast reads. 1% from celebrities, they don't really cause system overload. So that slight latency increase for the users actually following celebrity is acceptable here. Now let's talk about trade-off 4, which is synchronous versus asynchronous processing. And just to recap, actually, any system design interview, actually, and even when you're working as an engineer, in the industry, which you already probably are, you should always be talking about trade-offs. Like any design decision you do, any project you're doing, you should always be talking about the trade-offs as part of this. For example, one of the operations will be image upload. It uses async because user gets immediate response. It must wait for the processing notification. Feed generation also uses async pre-compute, and if feed may be slightly stale with 5-minute ETL, it will load fast. Like action uses synchronous. The user sees immediate feedback, which is critical for the user experience, and the post creation uses async, which is needed for the faster API response. The post appears after the processing. So the philosophy behind this is that async by default, unless immediate feedback is needed, which might be critical for user experience in some parts. Now let's talk about the trade-offs for trade-off number 5, which is the denormalization for performance. So the normalized approach is generally slower. For example, the select count from users where follower ID equal to 1, 2, 3, 4, 5 is slow for users with millions of followers. However, denormalized approach is generally faster. The select follower count from users where user ID equal to 1, 2, 3, or 5 is pretty instant, but it must maintain the count with eventual consistency. So the decision here is that we denormalize count for followers, likes, and comments. And the trade-off is that the storage space and consistency complexity for 1,000 times are for the faster queries. Now for part 6 is monolithic versus microservices. So the benefits of monolithic is that it has simpler deployment, easier debugging, whereas the cons is that it cannot scale components independently. And microservices have pros and benefit is that you can independently scale the services. Every team has their own autonomy, what services they're working on. And the cons is that the operational complexity. The more services you have, it just gets very hard to maintain production. There is more DevOps involved, more operations, more people you need to actually support the services. So why is microservices we are proposing for Instagram scale? So the reason is that, for example, the feed service needs 100 times more resources than, for example, the user service. The different teams can work on different services independently at such a big company scale, as well as the fault isolation, which means the media service being down does not mean equal to that this feed service has to be down as well. So now let's talk about when does the monolithic make sense. The startup with under, let's say, 100,000 users, like smaller startups, smaller systems, smaller scale systems are ideal for monolithic, where it's also a single team and where they're still trying to figure out the product market fit. So for those use cases, monolithic would make much more sense. So now let's start talking about alternative architectures that we could have considered that we may not propose as part of the solution, but at the same time we should be aware of them and we should definitely discuss with the interviewer that given the trade-offs, these approaches could have considered, so that you signal to the interviewer that you have broad knowledge of the space. And then you also show them that why you did not go with these alternate architectures. The reason of not going with something is pretty important to showcase why you didn't go with someone, because that showcases to the interviewer that okay, you can identify a problem with potential decisions and then you can stay away from them in your team. So that is super important. So the number one is NoSQL database and like Cassandra and DynamoDB, and not using it for the use case here. So how would that work if it had to be? So for example, post table in Cassandra would have been with the partition key user ID and the cluster key created at descending. So the benefits would have been the native horizontal scaling by just adding more nodes easily. It would be able to support high throughput and there would be no need for manual sharding. However, the drawbacks will be limited query patterns. For example, the must query by partition key, it has to be, all the queries has to be the partition key, and then it doesn't support joins as well. So you would have to denormalize everything. And then it will be much more complex for relational data for, let's say, user follow graph. And also the eventual consistency would be much more harder to reason about. Now, let's talk about the query examples and how they show the limitations here. So for the reason of the query, for example, the query select all from post where user ID is equal to 1, 2, 3, or 5 is efficient because it's a single partition. The query select from all where post where caption contains sunset is impossible here because it just won't be able to do as performant as SQL, and because it requires a full table scan, which essentially is not supported. Now let's talk about why we didn't choose this for our Instagram scale. So the thing is, Instagram's data is inherently relational with users, posts, follows, and likes. So the complex queries are needed for, especially for the feed generation. ACID transactions are definitely needed for the critical operations. And SQL, it just fits the problem domain more in terms of the reasons we just explained, like the complex queries, ACID transactions, and just like the native SQL support. Like for example, the knowledge the existing industry has about the SQL, the ecosystem. Now let's talk about when NoSQL would have been better. So, for example, situations like where we just need simple key value lookups, or where there won't be no complex relational relationships in the data, then we should have ideally considered NoSQL. And then extreme write throughput requirements, like for example, we have a huge amount of write throughput requirements. For that, NoSQL could have been considered for sure. And now another alternative that we could consider, at least discuss, is like why don't we use GraphQL APIs instead of REST, as like Facebook is pretty big on GraphQL, for example, in some use cases. So how it would have worked? So essentially it works is that a single endpoint where client just specify exact fields is needed. For example, example query gets feed with post containing ID, image URL, caption, user with ID, username, and profile pic URL, plus the likes count, comments count, and liked by me flag. So the benefits of this is that the client specifies exact fields needed, preventing overfetching. The single endpoint instead of separate endpoints like feed, post, users is better for mobile, reducing the data transfer, and it's strongly type schema as well. However, it has multiple drawbacks. For example, it's much more complex to implement. It's very hard to cache because queries are dynamic. The learning curve is super high for teams because it's not widely adopted. And then overfetching can become underfetching problem with N+1 queries. Now let's talk about why didn't we choose this for the MVP. So the rest is much more simpler for initial implementation. Caching is much more easier with REST because endpoints are fixed. Teams are generally super familiar with REST, and we can always add GraphQL layer later for specific use cases if we need. And Facebook and Instagram, they actually do this in production for specific use cases. So now let's talk about when does GraphQL make sense. Mobile first applications, for example, where they need bandwidth optimization, that could have been a good use case for GraphQL. Many different clients type, for example, you have to support web, mobile, third party, and then that could have been another reason for using GraphQL. Mature product, like for example, very stable API, for example, Facebook. So it has much more established product and very established API pattern. So over there again, it could have been considered GraphQL. So now let's talk about considering serverless architecture. So serverless architecture typical will be based on, if we had chosen this alternative, would be like AWS Lambda or Azure functions. And to start off with, how it would have worked. So essentially, it would have been like API gateway would have routed to Lambda functions that are stateless, and these Lambda functions then they talk to the database. So the benefits of this would be that okay, there's no server management. It's fully managed by AWS because they take care of all the operations, the DevOps part of it, at least most of it. The auto scaling is actually built in theory at least. Like for example, it scales from 0 to millions of requests, and it's pay per request. So it's not like per hour server hours. So like you actually just pay what you consume, and it's faster iteration as well because you can deploy individual functions. Now let's talk about the drawbacks. So the drawbacks is like the cold start problem, which is a latency of 100 to 500 milliseconds when the function hasn't been run recently. And then the limited execution time, for example, it's 15 minutes per max per request, even though now there are new advancements to my knowledge. I think Azure durable functions, they've been around for a while actually. And they can go much more than 15 minutes, but still it's one of the considerations. And stately design requires external state management, so it's another thing to consider with this. And these are always harder to debug with distributed logs. And again, with the cost, it's become very unpredictable at extreme large scale. So now let's talk about why we didn't consider a serverless for our use case. So the thing is, a cold start latency is actually unacceptable for user-facing APIs. It's very complex for maintaining stateful operations, like for let's say WebSocket connections. It's also very less control over performance optimization. We can't really control that much in this use, and if we go with the serverless route. And Instagram scale, we do just dedicated servers. They just makes much more sense when it comes to cost effectiveness. So now let's talk about when does serverless make sense. So serverless makes sense when we have spiky workloads. It's not a constant high traffic. When we have to do background jobs, let's say like image processing, or that could use Lambda, or for example startups who want to quickly iterate and quickly experiment. So now let's talk about another alternative we could have considered is the event-driven architecture, which is considered called event sourcing. So this involved building architecture and how around events. How it would work is that all changes are events in a, let's say, a Kafka stream. Events would include, let's say, user created event, post created event, post liked event, and user followed event. So the service will consume events and they update their own state. So for example, feed service will listen for post created event and it updates the feed. Analytics service will listen for all events and update the dashboards. Notification service listens for post liked event and sends the notifications. So the benefits of this is that it's loose coupling, means services they don't need to call each other directly, so that's pretty good. The event history provides audit log and replay capability just by default. And then it's very easy to add new consumers just by having new service listen to the events. So these three are pretty big benefits when it comes to distributed systems and like Instagram scale platforms. But it does have some drawbacks. For example, it is much more complex with eventual consistency everywhere. Second is that it's also it gets a bit harder to debug with distributed event flow because you have to do distributed tracing and logging. And then it's also state rebuilding requires like if service crashes, then it gets a very hard. That's something we need to think about it as well. Now let's talk about why didn't we choose this for MVP, the event-based architecture. So the thing is, it at least for the scale of interview, it's good that you're mentioning it to the interviewer, which is good. But proposing it, the problem is that it has significant complexity. And the one thing with interviews is that you shouldn't propose complex solutions just from the get-go because that signals to the interviewer that okay, you are overcomplicating things, which is also not a good thing for from an engineering standpoint. So you should always try to keep things as simple as possible because even simpler things in architecture will eventually become pretty complex. So if you start with complexifying everything from the get-go, it just won't be able to be grow into a bigger architecture. So that's why one of the things we care here is that not adding significant complexity. And coming back to it, eventual consistency is pretty hard to reason about when it comes to event-driven architecture. And the third thing is it's a overkill for initial launch. Let's say when you're just starting a platform, not establishing Instagram after let's say 20 years, but when you're just starting it, it might not be the best thing to start with. So now when does it make sense to use event-driven architecture? So one thing is when you have a mature product with huge amount of traffic with a lot of services, then it does make sense. Okay, then like you start event-driven architecture. Second thing is when you're working in the spaces where audit log is pretty important, let's say like compliance or like just with like huge amount of user traffic that you're part of the government scrutiny and you're just very responsible to the public. So audit logs are very essential and this architecture really helps with that. And then just like analytics heavy workloads. So that would also be because by design it just tracks events. So it really works well for this use case. So now let's talk about failure scenarios. So the thing is, in any system design interviews, you should also mention the failure scenarios. Like for example, how do you design for failure? Because the thing is, failure will always happen to some extent. We can't just assume that our architecture or system won't fail. So for that specific reason, you should always keep in design have mitigation strategies, but to how mitigate the failures, but at the same time have contingency planning, which is if failure happens, how to avoid it or how to quickly mitigate it, but at the same time when it happens, how to recover from it. So it is a lot of planning around failures is like a very big part of engineering. To start off with the first scenario is let's say okay, a database shard goes down, then how we should plan for that failure. So to start off with the impact that way, the users on that shard, let's say about 2 million users, they won't be able to read or write their data. So that will be approximately 0.1% of the total users affected, which at the Instagram scale is actually a pretty high in absolute numbers, even though it might sound less in percentage, but we still need to consider about the absolute number of users. So how do we detect this? So the detection process will essentially have health checks that is failing in 10 to 30 seconds. Monitoring might be alerting, sending automated alerts to ICM like on call. Incident engineers will be getting paid. So these things will be how the detection process would ideally work. So the automation mitigation should follow these steps. The primary database fails, let's say the monitor detects failures in 30 seconds. Automatic failover should kick in to read it replica, and then one of the replicas should be promoted to the new primary in, let's say, 30 to 60 seconds, and the application config updates in 10 seconds, and the traffic start flowing to the new primary. So the total downtime will be only 1 to 2 minutes. Now let's talk about the recovery. So the recovery will involve things like, okay, we have to investigate the root cause, let's say a disk failure or a network issue, or like provisioning new replica to replace the failed primary, catching up on the replication, returning to the normal configuration. So that total recovery time could take 30 to 60 minutes. Now let's talk about the second failure scenario, which is, okay, a CDN region failure. So to start off with, the potential impact would be that the users in that region will see slow image loads, because now it has to either go to the origin server or to different farther edge locations. So that will increase latency, and that will be like degraded experience. It won't be complete outage, but it will be slightly worse experience. So how would the automatic mitigation strategy work in this? So for example, CDN edge location fails. The CDN automatically routes the request to the next nearest edge location. The users then sees a slightly higher latency, perhaps from 50 to 100 milliseconds, and then ideally no manual intervention should be needed here. And the total impact, which is like transferring to most users, that okay, the images are loading slightly a little bit with delay. Now, if we talk about the third failure scenario, will be, let's say, what if the feed service crashes? So the impact for that would be that okay, the users are not able to load their feeds, and the other functionality like posting, liking, or individual post, that might still be working. So what is the automatic mitigation in this? For example, the feed service instance crashes, the health check fails in 10 seconds, load balancer removes the instance from the pool, traffic routes to healthy instances, then the autoscaler detects the high load, new instances spin up in roughly 2 to 3 minutes, and the total downtime in this situation will be 10 to 30 seconds for the affected requests. Now let's talk about the fourth failure scenario, which is Redis cache cluster failure. So what could be the potential impact of this? The impact will be like, okay, the feed generation becomes slow with no cache, and the second will be the increased database load. So the deviation mode will be, how it will work is that the Redis cluster fails, all the cache reads fail, application switches to database only mode, latency increase from 50 to 50 to, let's say, 500 milliseconds to 10 times slower. The rate limiting kicks in to protect the database, and the user experience becomes slower feed loads, but it's still not complete outage at this point. So how does the recovery work in this case? So the recovery would be essentially that restoring the Redis cluster in, let's say, 10 to 30 minutes. Cache will slowly start rebuilding through the cache misses, and then gradually it will return to the normal performance. So the total degraded time here will be 30 to 60 minutes. So now let's talk about the failure scenario when, let's say, there's a total data center outage. So what happens in that case? So let's say the impact could be, let's say, a environment event happen, let's say like a cyclone or hurricane, and the whole data center is shut down, and then it will affect all the services in that region. And multi-region mitigation could be one thing. Could be is that sorry. Then that's why we should propose that a system is designed to be deployed to multiple regions, multiple geographies. So, for example, the primary could be US East 1, Virginia, secondary could be US West 2, Oregon, and then there are another third one could be US Western Ireland. So that way, the more geographies we have, sure, it will be expensive, but at the same time, at the scale of Instagram, we need to have very good disaster recovery measures. So now for disaster recovery, how would that work? So let's say the US East one completely fails due to an earthquake or a power outage, and then the automatic failover to US West 2 occurs in, let's say, 10 to 30 minutes. And then the DNS updates to points to US West 2, and then some data loss is acceptable, but due to the replication lag of, let's say, 1 to 5 minutes, but eventually the service is restored. So in this case, the total downtime will be in such a big event will be 10 to 30 minutes, and the data loss will be roughly 1 to 5 minutes of writes. So now let's talk about another failure scenario is like monitoring and alerting. That is actually this is more about the how do we use monitoring alerting as part of tracking the key metrics. For example, metrics mentioned monitored every 10 seconds include the API latency at P50, P95, and P99. And the error rates would be, for example, 500 next responses like server internal response 500. And then we also will be tracking our database query time, cache hit rate, query length, queue length, in case we know we are using multiple queues, and then also the service. So now let's talk about when do alerts get triggered. So for example, when the P99 latency asset exceeds 1 second for more than 5 minutes, or when the error rate increases greater than 1% for let's say 2 minutes, and then it could be the database becomes unavailable and it's not responsive to the health checks, or the cache hit rate becomes less than 50%. So these are like some of the scenarios when we can configure the alerts to be triggered. And the alert channels, ideally, it will include some platform like PagerDuty for on-call engineers, Slack for team notifications, and the email for the whole team and management. So now let's talk about the graceful degradation and how it handles the system stress and what the role it plays as part of any system design. So when the system is under stress, one thing we should do is we should have measures that actually disable the non-critical features first. For example, turning off the explore page while keeping the feed working, disabling the recommendations while keeping the basic feed alive, or turning off the stories while keeping the main posts alive. So like services which are more required for the critical features, we try to prioritize them rather than services that might not be for that critical services in case we have to choose between those two. And the second measure would be to reduce the quality. Instead of outright failure, one thing we could be doing is that reducing the quality. For example, instead of serving no images at all, we could serve lower resolution images. Instead, we can reduce the feed size, let's say from 10 posts instead of the 20 usual posts. We can even disable the real-time updates for temporarily while we recover from the impact. And the last resort could be considered just like a read-only mode. So we can disable posting to our services and system. People are only able to consume things. So this will protect our database from writes. But again, these measures are only when we have to make trade-offs. We have to make choices between what do we do if there's like multiple failures happening, and we have to make choices which service to prioritize and which service to keep up while we, for example, work on auto scaling and spinning up more servers, things like that, or recovering databases from failures, etc. So now let's talk about cost optimization. So cost of optimization at Instagram scale is very important, and it has a huge impact in terms of financial savings. So monthly cost estimate is here in rough order of magnitude. Again, these are very rough numbers. You don't need to memorize them. You don't need to know them on top of your head. But at the same time, you need to be able to make an educated guess as part of your interview. So the compute for API servers actually uses, let's say, 1,000 instances at $200 per instance, which roughly equals to $200K. Database, let's say, uses 4,000 instances, as we covered earlier, which is 1,000 shards times 4, which is like $500 per instance. That is equal to $2 million. And now, so if we talk about Redis cache, as we discussed earlier, it uses, let's say, at our scale at 400 instances, which is 100 masters plus 300 replicas. So that is like $1,000 per instance, which is equal to 400K for our Redis and cache infrastructure. And then if we talk about the object storage on S3, so that uses 100 petabytes, as we discussed earlier in the course, at $23 per terabyte, which is equal to $2.3 million. And the CDN egress uses 600 million petabytes per month. As we discussed earlier, at $85 per terabyte, it would come down to $51 million. Load balancers at our scale, as we discussed, it will use 100 instances at $200 per instance. That is equal to $20,000. And the message queues cost again as $50,000, and monitoring and logging itself will cost $100,000 roughly at such a large scale and monitoring so many things. And the network interoperability zone transfer roughly will cost $500K, which is a transfer between different, being able to replicate multiple availability zones between the same region, and then having multiple regions, and all of them have availability zones inside them. So The total approximately for this scale will be roughly $56 million per month, which is huge, but again, it's understandable at the scale of Instagram. And the annual cost will be $680 million. It's huge again, but at the same time, we have to be realistic that supporting Instagram at this scale, it does come at a cost. So now the thing is like how we can do cost optimization strategies and how it can save significant money when you're spending a $680 million per year. So one strategy, as we briefly covered earlier in the course, is the storage tier optimization, which will save us roughly $30 million per year. So without lifecycle policies, all photos would have stored in S3, standard costs and 100 terabytes times $23 million. And that is roughly equals to $27.6 million per year. So now if we use with the lifecycle policies, that will be year one photos at hot tier cost 20 petabytes times $23, which is $460K per month. Year two photos at a warm tier will cost us roughly $250K per month. And then year three photos at a cold tier storage will roughly cost us $250K per month. So that comes down to total is $950K per month equals to $11.4 million. And now we compare the savings compared to if we had to store everything in S3 will be like $16.2 million per year, which is 60% reduction, which is quite a good job if you propose this during the interview. So now let's talk about the strategy number 2, which is the CDN optimization, which will over here with this optimization we aim to save roughly $10 million per year. So increasing the cache ratio from 80 to 85%, it will reduce the origin egress by 5% of 600 petabytes, which equals to 30 petabytes per month. So the cost saving here will be 30,000 terabytes times $9 per terabyte, which is equal to $2.7 million per month, which is equal to $32 million per year. And now let's talk about how to achieve this cost savings. So one thing we could do is that we use longer cache TTL of 1 year instead of 1 day. We could do pre-warm cache for popular content. We could also use image compression so the smaller files are much more cacheable. And now let's talk about strategy number 3, which is reserved instances, so which could save us roughly $5 million per year. So reserved instances that instead of doing auto scaling, I know just requesting everything in the cloud at the specific time, we kind of reserve it and book it in advance in cloud providers like AWS and Azure. So the on-demand pricing for 1,000 servers, which we proposed earlier, will be at $200 equal to $200K per month. The reserve 1 year commitment for 1,000 servers will be roughly $120 equal, which is $120K per month. So the savings will be $80K per month times 12, which is equal to $960K per year, which is like for 1,000 servers. So for the entire fleet of 5,000 instances, we'll be saving $5 million, roughly $5 million, which is like $4.8 million per year. And also one thing to note is that if you're at the scale of Instagram, you can always go to cloud providers like Azure and AWS, and you can actually negotiate with them that, okay, it's like bulk pricing. So you can even get even much more benefits than just using reserve instances. So I really hope all of you, if you do guys start a startup, I hope it grows to Instagram scale, and then don't just go pay what the Azure or AWS bills you straight up. Negotiate with them because you are definitely driving a lot of traffic to them. Your bills are pretty huge, and they will also appreciate you talking to them before moving to other cloud providers right away. So now let's talk about the next cost optimization strategy, which is image compression. Over here, we aim to save roughly $3 million per year. So the current average we have is 2 megabytes per photo. With the improved compression, we can achieve 1.5 megabytes per photo, which is a 25% reduction. So the storage savings here will be 100 million photos, as we discussed earlier in the course, per day times 365 days times 0.5 megabytes equals 18.2 petabytes per year saved. So that is cost is 18 terabytes times $23 per terabyte equals to roughly 420K per year. Storage plus the CDN bandwidth savings are approximately $2 million per year. So the total over here becomes $3 million per year. And the implementation for how we implement this, we could use, for example, WebP format instead of the JPEG format to start with. Another strategy we could do for the cost optimization is that we can do database right sizing. For example, this would essentially save us roughly $8 million per year. For example, over provision cost for 4,000 instances and at $500 equal would be like for each of them would be $2 million per month. So if we actually do right size based on the actual usage, we can reduce the instances by 30% in off-peak hours. We can use small instances types for low traffic shards. The savings over here will be our 6,600K per month equal to $7.2 million per year. Now, if we talk about strategy number 6, which is the spot instances of workers, this will be savings over $2 million per year. So the image processing workers are essentially non-critical and they can tolerate interruptions. So these are not like business critical services compared to other services. So the on-demand cost would be 5,000 workers times $100 equal to 500K per month. Spot instances cost 5,000 workers times $30, which comes down to 150K per month. The savings here would be 350K per month, which equals to again $4.2 million per year. So as part of the cost optimization, total potential savings are $40 to $50 million annually, which is 7 to 9% cost reduction, which is actually pretty significant. So now if we talk about the ROI and the engineering effort, so for example, 2 engineers for 3 months and optimization costs, let's say 100K, but the annual savings are $40 million. The ROI is 400 to 1. Now let's talk about the cost per user metrics. So the total monthly cost is $56 million. And the monthly active users are, let's say, 500 million, as we discussed earlier. So the cost per user is actually 11 cents per month. So for example, for comparison, it's generally estimated that Twitter costs approximately 20 cents per user per month. Facebook costs roughly 15 cents per user per month. Instagram roughly approximately costs 11 cents per user per month. So our goal here is that the lower is better, indicating that we have much more efficient operations. Now let's talk about the interview timing breakdown that we should follow. So essentially, the main thing is that the interview will be 45 minutes. So you have to structure a lot of these things in those 45 minutes, but also you have to prepare if the interviewer decides to go in a specific direction. Because the thing is, I completely understand that we can't cover all of these things in 45 minutes, but in this course, but the thing is what all of this information gives you, that it prepares you for all the possible follow-up questions the interviewer can give you. And the second thing is that, let's say if they try to deep dive into something very specific, let's say a feed service, so that you're much more prepared, or some interviewer might be just like want to stay at a very broad level, so then you are prepared for that scenario as well. So now this is the proposed time allocation strategy that I personally follow, and I would suggest you should follow as well. And feel free to pick and choose what works better for you. So ideally the requirements should take 5 to 7 minutes, covering the functional, non-functional, scale requirements like scale requirements and out of scope things. And then you should skip in detail justification unless they really press you on it and ask more details. But so you should be prepared for that. But don't start with the detailed justifications right away. And the second thing is the capacity estimation. So capacity estimation should roughly take 5 to 6 minutes. And for storage, for bandwidth, and for QPS, using rough calculations as we discussed earlier. And you can skip the precise math, but you should be able to do high level math to show that, okay, for example, you can round up like seconds in day from 86,000 to, let's say, 100K, like things like that. The high level architecture should roughly take 8 to 10 minutes. So for example, that would be to draw the diagram, explain the main components, show the overall data flow, and you can skip the implementation details of too many things unless they really press you on it, but you should definitely be ready for it. And then the deep dive one. So for example, interviewers can choose this deep dive. So you should be prepared to spend roughly 8 to 10 minutes on this. So the most likely deep dive into either the database, so they might choose the feed or they might choose the media architecture. So you might be ready for these three if they haven't. So if they don't specify a specific topic, then you can skip, then you can do the deep dive any one of these and skip the other ones but you should definitely mention that, okay, these are the other areas that should be considered ideally when designing a system. And deep dive 2 will be again for 5 to 7 minutes. If you have time, you're running good on time, we can cover it as well. You can, out of the three topics, let's say database, feed, or media architecture, you can cover another deep dive topic number 2. So now trade-off should ideally take 3 to 5 minutes for key decisions and alternatives considered. And the thing is, it might seem like, oh, there's so much content, and if we're just proposing 3 minutes to 5 minutes. But one thing that you will realize during the interview is that even the smaller 2 minutes, it sounds less, but you can fit a lot of content when we're just spreading out during the interview. So don't worry about that. Uh, it's always like the thing with interviews that I will suggest my approach would be that you need to drive the conversation. You should need to control the narrative. You need to control the interview. So, for example, you need to completely own those 3 minutes. So, don't worry about driving it. It's just that once you have the go button, okay, just keep going. So, for example, yeah. And then the scaling part should take, like coming back to it, scaling should roughly take 3 to 5 minutes as well. Like, for example, how we aim to scale each of the tiers, application layer tier, database tier, caching tier, things like that. And then you should always keep Q&A and buffer roughly takes 5 minutes for clarifications and follow-ups. So you should keep that in the end as well. So the total is roughly 40 to 50 minutes. Again, this is like a typical interview time, but again, just try to keep 5 minutes as a buffer in the end. So now let's talk about interview tips and things that you should definitely do in your interview. The number one thing is that you should be thinking out loud. The interview essentially wants to hear your reasoning, so make sure you do that. Number two is asking clarifying questions before diving in. So let's say you are actually, when you're designing the system, you need to first ask clarifying questions at the very first step. That's so that you understand the business problem completely. One thing is, as part of your diagram at the whole stage, you should be drawing diagrams. Like for example, the architecture diagram, the high level diagram, data flow diagrams, or this data schema diagrams. So make sure that you are adding the visual element to it. It's just like part of your daily, for example, how teams works in general in production. So we're just trying to follow that approach. And also any design decisions that you make during the interview, like for example, why you chose SQL versus NoSQL, why you chose caching, why you chose Redis for caching. Any design decisions that you make, you should be actually providing the rationale in addition to that so that your interviewer knows about it, your thinking and your thought process. And one very important thing is that you should be always talking about trade-offs. Like for example, anything you do, it always comes with a caveat. Like for example, let's say having SQL database, right? It's essentially for relational data, but the thing is now it's definitely is a bit harder to do horizontal scaling compared to NoSQL option where like the horizontal scaling is taken part of, but then it has other drawbacks. So anything any design decisions that you do, you make sure that you're talking about the trade-offs as well. And the next thing is that the based on so your solution you should be always adapting based on the interviewer feedback. Like some interviewer like interviewer A could really one thing and we would like to deep dive on, let's say, feed generation service. So you have to then model your upcoming answer around that. Some interviewer could be like, oh, they're really interested in stories or DM direct messaging features on Instagram. So then you have to model your answer based on that. So that's why I always keep listening to the feedback and make sure you adapt to it. Now let's talk about things that you should not be doing in the interview. So the very first thing is that you should definitely don't jump to the solution without defining the requirements. So in the interview, actually on purpose, they will be giving you ambiguous problems. So there will be something like a very broad design histogram. So it's a very ambiguous problem because there's so many ways you could do that, right? So that's why as an experienced engineer, as a senior engineer, it's your responsibility, even at the workplace, when you come to know you in the company, you'll realize that a lot of times you get very unclear requirements. Not that people want to, it's just like the nature of business, right? Like we don't have clarity at all the time, but that's the need part of our business of our career, right? That's why we get paid, that we bring clarity to things. So for example, before jumping to any sort of solution architecture or system design architecture, you should be asking exact requirements and by clarifying them. So let's say they say design Instagram, ask them, okay, what are the function requirements do you really want to prioritize? Let's say posting images, posting videos, things like that. Just and the one way to like clarifying is essentially just asking questions. So make sure you do that. So another thing is that you shouldn't be spending too much time on capacity estimation. So like one thing I've seen that with folks is that they spend like 15-20 minutes on capacity estimation, because the thing is it's very heavy math oriented. So the thing is this section is very super important, but at the same time you have to be mindful of the time. It has to be between 5 to 6 minutes max. So how do you do that? So one approach I would always say is that it's just something that comes with practice. There's no shortcut for it. So the more you do capacity estimation for different problems, you just get be better at math. Then you just start remembering things. For example, okay, what is a petabyte, terabyte, exabyte, things like that, and then you just start rounding off numbers as well. For example, you don't have to say 86,000 seconds per day. You can just say 100K seconds per day. Anything that helps you makes your life easier. You should definitely do that, because the thing is you're trying to show the interviewer that you can do this estimation, but you have to do this in 5 to 6 minutes. In production, in real job, you'll be doing like, let's say 1 hour, right? Because there's no time limit. But now you're being tested, now you're being interviewed, so these are just the constraints we have to deal with. The third thing is designing every single feature. So that's definitely not you should be doing. For example, let's say there's function requirements, right? And then if you don't ask clarifying questions, you could be just like, okay, I'm going to design everything. Let's say I'm going to design images, videos, stories, DM, feed, ML, everything. That's another mistake I've seen, that people that try to do too much, which is not good at all, because that is just going to derail your interview. So definitely don't do that. And bring the MVP, most valuable product mentality, to interview questions as well. Be very proud. There's no shame in doing the bare minimum. When I say bare minimum, you should definitely focus on the core requirements first. Only if you have time, then you do the extra things, right? Sure. That's why you should do less things, but you need to do them really well. And then there's the fourth thing is ignoring time. So one thing I've seen that people, they don't look for the time in the interviewers. So that's why you need to be always be mindful of the time. Maybe sometimes you might not even have access to the clock on the computer screen. Let's say there's a full screen window, right? So that's why always wear a watch to the interview. Don't be rude that keep looking at it multiple times, but just have a basic idea every 5 to 10 minutes, okay, where I am standing. And the way to just be better at it is just to doing practice. Like I would just say, do more mock interviews with your friends, just by yourself, look in the camera, record yourself, and just time it every time with yourself. Like in one of the interviews, I remember early in my career, I did 27 mock interviews for one of the companies, because I was so nervous. I was like, okay, I really need to make sure I'm doing well in time, because one of the challenges that I was running into, that I was always bypass the time. I was going like 70 minutes and stuff, which was very bad. So then I have to be very quick. So we have to be fit into like 45 minutes at the end of the day. The next point is being defensive. So what I mean by this is that, so sometimes some interviewers, it's a reality, it's very rare, but it could happen that they might try to test you under pressure. They might ask you a lot of follow-up questions in very short amount of time. So this is try to simulate stressful environment. So I don't personally agree with this approach, but I've seen it happen. So that's why I just want you to prepare for it. So if that happens, there's no reason to be mad or take it personally. It's not that, it's just like the other person is also doing their job, and now it's our job how we adapt to it. The solution in my assessment is just that always listen to your interviewer and then just adapt to it. So they can ask you. I remember one of the interviews I had, it was actually object-oriented design. And when I was doing the object-oriented design and we had crossed the requirement stage already, the interviewer kept asking me follow-up questions while I'm designing it every 30 seconds. Okay, why do you do this? Why do you do this? Why do you do this? So after a while, I realized that they're trying to simulate this environment, that like they're trying to. So one thing I realized, so how I pushing back in a nicer way is part of your daily job as well. Is like I answer him, and before they could dive deep, I'll be like, okay, I'll come back to it. Thank you. I just took a note. So as it was like a code sharing session, right? So I put the thing on the right side. I put like questions, and I started writing down his questions, and I will answer them. By the same time, won't go too deep down, because the thing is now we have to unfortunately play their game as well. So when they have to share the screen with their team, they will see that okay, these many questions were asked to them, right? So that's why when I started documenting questions, they stopped asking so many questions, because even they realized that okay, I have realized that this stressful environment is being created to simulate the stress. So that's why I would say do that, because then you're documenting everything, right? So when I had time, actually, I did go back to those questions to address them. So in the end, so that was one of the approach. But the reality of life is that you just have to be also you have to stand your ground as well sometimes. And the last point is the memorizing solution. So thing is like memorizing not Tricky. It doesn't often work because let's say if someone quizzes you on something and they will quiz you, right? That's the problem in system design. That's the neat thing actually about system design, that they will really want to see what have you learned, right? So I would say, yeah, don't memorize that. Something you just need to remember, right? And it will just come with practice. But at the same time, just don't blindly remember something. Okay, yeah, we use Redis, we use Redis. Like, why do we use Redis? Try to remember that. And once you digest it, that will be really helpful. So now let's talk about what interviewers are looking for in terms of scoring. What's a typical scoring rubric in terms of interview? So this is just like an example one, but generally this is rubric every interviewer gets when they're doing system design interviews for their companies. Yeah, so to start off with the problem, it's very typical across the companies to have different categories. So generally, problem understanding carries 20% of the weight. It's more like evaluating: did you ask good questions? Did you clarify the requirements? Did you identify the constraints? The second thing is system design itself. So that's like roughly 40% of your mark, which is the proposed architecture. Does it make sense? Is it viable? Is it able to scale given the requirements? How are the components like well separated? Are they well managed? Are they well independently designed? And the third thing is communication. Like, for example, even if you can build the best thing ever, the best design ever, the one thing that they really want to see is that can you communicate the design across to multiple audiences? Let's say there's a technical audience, there's a management audience, there's a PM audience, there's a design audience. So the thing is like you should be able to, as an experienced engineer on the team, you should be able to communicate your ideas, your design decisions. And one thing I really want to point out there is that communication doesn't really mean that, okay, sometimes I've seen, okay, a lot of people, like for example me myself included, that okay, I used to think when I was early in my career that like having an accent can hold me back and that means bad communication. I won't say that's not the thing. Don't hold yourself back. Like regardless if you have an accent or any way you speak, that's totally fine. The communication just comes with, you just need to make sure that any design decisions that you take, it should be made aware to the needed audience, and that is my definition of communication. So everyone who should be knowing, should be aware of the things that you're doing, they should be aware of it, right? At the right time. So that's roughly 20%. And then the last 20% is trade-off analysis. So this is very neat because one thing in real life and in general and career as well, nothing is perfect. No, there's no perfect solution and there's no perfect technologies, answers. So that's why like one thing they want to see is that you can think about the alternatives. Let's say they do SQL. Okay, even the SQL, why did you go with PostgreSQL? Why did you not go with SQL Server? Or why did you not go with Aurora SQL on AWS? Things like that. They want to see that you're open-minded when it comes to system design, and you can be fluid. At the same time, you can stand your ground. Like for example, you can stand behind your design decisions, but at the same time, as an experienced engineer, you should be open-minded enough that when someone gives you an alternative approach, that you generally consider it. And it's totally fine if your solution is not the most ideal one or you're wrong in a situation, that's totally fine. But then being able to pivot and being able to change, that's a very important skill to have as well. So let's talk about what does interviewers look for in terms like what is a strong candidate looks for. Let's talk about some examples. This is one of the scenarios what a strong candidate could look like. For example, if the candidate asks like things like, should we support stories or should we support reels or should we focus on main feed? Or for example, things like asking questions about, okay, what is more important to this specific scenario? Is it consistency? Is it availability? Or is it even scalability? Or like things like that. More insightful questions. For example, are we designing for the current Instagram in 2025 scale or Instagram that was in 2012 when it was just launched and it was still growing fast? What exactly we mean by Instagram? And then things like more granular things like, can the feed have staleness, and or does it have to be completely real time? Because the thing is, depending on these questions, the rest of the interview, the rest of your answer will completely change. So that's why you need to ask these questions. But in these insightful questions, like you have to ask good questions, right? So it signals to the interviewer that okay, this is a strong candidate. They understand the problem domain itself before they jump to things, to designing things. So then and this is a sample answer that an interviewer can give you based on a question. Like for example, okay, so we're designing core feed functionality for 500 million daily active users. So that they have answered your scale question. They have talked about the core feed functionality, prioritizing the availability over consistency. So they answered your third question with less than 500 millisecond latency target. So they have also given you the answer on performance. So that's a answer that you should be expecting from your interviewer. Now, now what's next that a strong candidate would be doing in this situation? For example, they'll start with a good strong candidate. They'll start with like architecture diagrams with the components. They will explain the data flow for key operations, like for example, upload feed, like how does upload work end to end, how does the feed work end to end. They will actually show the database schema. As you can see in the earlier part of the course, we were actually showing like SQL schema, like different databases. So the more you can do, that's even better. And then discussing sharding with the specific strategy. So basically, the strong candidates expect that they won't just do hand wavy, oh, we're going to do some sort of sharding. No, they go one step ahead and then they give a more specific sharding strategy. Let's say, for example, user ID modulo 1000. So you just have to be more specific without diving too deep. But at the same time, you can't just be way too high level, because then it kind of is like you don't really fully deep diving in, which is not good either. And then you have to mention caching and multiple layers. So like for example, as we talked about caching, it has to be at the client level. For like example, mobile applications, web application, they have their own caching. Then the second layer of caching is the application layer caching. Then there's a Redis caching itself, the whole caching layer. Then there's a database level caching. So you need to be able to explain different level of caching, what are the different TDLs for them, and when and how do we evict the cache, how do we keep the cache fresh as well. And also any of the designs, any of the components that you propose, you need to be able to point out the bottlenecks and like how do you address them. So like for example, this shows that you're aware of the limitations of your design. So that is super important as well. Another good showing of the candidate is like a strong candidate is that they think out loud. So when you're trying to think of something, feel free to just talk out your mind. Like you should be able to brainstorm it like you're just brainstorming with your team member or something. So that's a very important thing, because the interviewer will be able to see exactly your thought process. Ask for feedback. There's another point, so you have to be very careful with that you can't just be straight up as, hey, is it a good answer or not. You can't just straight up ask like that. So you have to be like very subtle in things like, do you think this is a good direction to go in, or is it like, do you want me to deep dive in it? Like you have to ask in a very good way that you're not really asking for answers to help to solve the problem, but you just want to make sure that you don't go in a wrong direction. And any good interviewer actually will help you prevent that you stay on course. Even they want that. And listen to hints. Like for example, a lot of interviewers will keep drop these hints that to make sure you're on the right track. For example, they'll ask, okay, what about celebrities with millions of followers or things like that? And then you jump on it. Then you see that, okay, that's an indication of that, okay, that's where the interviewer wants me to focus and to include in my answers. So then you're like, okay, good point. Let me adjust the fan out strategy. And yeah, use the whiteboard pretty effectively, whether it's a digital whiteboard if you're doing remote interviews or you're doing in-person interviews. Make sure you stand up, you do the interview on the whiteboard, not necessarily just talking while you're just sitting. When you're drawing the diagram, sure, you can take a chair and you can discuss with the interviewer, but for the most part of the interview, you should just be able to draw it on the whiteboard. Now let's talk about the trade-off analysis. So a good candidate would be like, for example, okay, I'm choosing SQL or NoSQL because of the data relational, or we need transactions. These are like good reasons for using SQL, right? But then you also back it up by, okay, the trade-off is that the horizontal scaling is harder. So that's why we'll need sharding. So that you showcase to the interviewer that, okay, you do know the ecosystem pretty well. And then good candidate would say that, okay, NoSQL would be easy to scale horizontally, which is true, but then we will lose joins and transactions, which are critical here. So these last 2 points of joins and transactions is super important, because it showcases to the interviewer that, okay, this person knows about like what is needed for this use case. And same thing goes for the feed generation scenario. Let's say like you say that, okay, I'm using a hybrid approach for fan out on write for normal users and fan out on read for celebrities. This does add complexity, but at least it handles both use cases well, because at Instagram scale, we do need to do that. So now let's talk about what are some red flags that you should definitely not be doing it in the interview. So asking no questions. So for example, if you just start designing right away as they give you the problem and without asking any clarifying questions, so that's bad, because it honestly shows lack of real world experience. Because in any of the real world jobs that like Even when given a spec by a PM or any problem that is just being described to you by engineering manager, the in the first few days you'll just spend on asking questions, defining the technical spec. So that's why like asking questions is super important, and not doing this is like a big red flag. The second point is the hand waving part. So let's say a candidate say that okay, we'll just cache it, right? There's no details on what they're going to cache. There's no details on like how they're going to cache, what data they're going to cache, what data store like Redis if they're going to use to cache, what is the TTL. If they don't add these specific details, that means that's like is going like hand waving it. So that's bad as well because it just shows like there's no depth and it's like it's theoretical knowledge only, and even that at very early level. So that is not good. The third thing is the ignoring scale part. So for example, if they somehow suppose suggest that okay, just having a single server, or for example, suggesting a single database without sharding, so that's bad as well because that means that either they forgot to mention scale, which is bad as well, but at the same time, the bigger red flag is that they're not considering scale at all. So that's a pretty red flag as well. So please don't do that. And then the fourth thing is that they don't talk about trade-offs at all. Like for example, if they claim, if a candidate claims that okay, this is their solution and this is the perfect and this is all they need, so that's not good either. So that's why you need to be able to self-criticize, self-assess your own solution, own system design as well. And the next thing is the can't adapt part. So for example, if the interviewer does give you follow-up questions or they just change you or ask you to deep dive into a certain aspect of the interview question, then you should be able to adapt your answer, adapt yourself so that you can go in that direction. And then don't over complicate things. For example, don't mention like things like blockchain or quantum computing, like some really fancy technologies, because that is definitely not needed here. And what is the green flags, right? So for example, having a structured approach, like for example, as we talked about in this whole course, like going from requirements, then capacity estimation, then design, then deep dives. So it shows that okay, the user, the candidate is they have prepared, they have thought about it deeply, they have a proper structure that they follow in the interviews, but they're most likely going to follow at their workplace as well. And this shows like more analytical, more structured thinking, which is highly desired in candidates. The second thing is a production mindset. So, for example, if you mention things like monitoring or failure scenarios, or like, for example, how you're going to do distributed tracing, distributed logging, these things, or like distributed asynchronous transactions, these things are very important. So, this shows like a production mindset. So, it shows, okay, you do have real world experience. Third thing is the justifying decisions. So any choice you say, it should be backed up by rational, right? So it showcases a critical thinking. Like for example, if you say, okay, we're going to use Redis, right, for caching, and then you back it up that okay, because Redis has good caching features. Like for example, it's a very fast key lookup. It's in the RAM, so it's very fast, and it's like otherwise if you suggest like for example Postgres for caching, that'll showcase that that's not a good decision to make, and there's no justification for it. And you should be ready to. The fourth one is going able to go in deep when needed. So, for example, showing actual SQL schema for database. That's the amount of depth they expect that because then okay, you can draw SQL databases, okay, SQL tables that's super needed as well. Or it is asking you to go deeply into one specific area, and you're able to adapt quickly and actually go into that area deeply. That showcases that you're adaptable, which is super important in real world jobs because in real world jobs things are moving very fast, things are being prioritized, deprioritized continuously, so you should be adaptable. And breadth awareness as well, so you should be definitely be suggesting your alternatives, what different alternatives are there. For example, if you suggest PostgreSQL for SQL, you mentioned that okay, there are other SQL options in the market as well, because any decision you do in a real world job, you'll always consider multiple options, and then you'll do a comparative analysis, and then you'll say okay, why you went with this option. And just being collaborative in general, right? Because it's super important as part of the job as well. They expect the good candidates to be able to collaborate with their team members. Same way, you should be looking at the interviewer as a team member as well. So you're collaborating on a system design problem, and it's like a healthy discussion going on. Sure, you're leading it, but at the same time, you should be a good team player. Now let's talk about common interview mistakes to learn and to learn not to make during the interview. The mistake number one to avoid is that to be able to solve if trying to avoid to solve a different problem. For example, if the interviewer says design Instagram's core feed functionality, and if the candidate, if you respond with let's say designing focusing too much on the stories, reels, DMs, e-commerce, or ads feature. So that's an example of not focusing on the problem that they were asking you to focus on. The problem is that you're focusing on out of scope, and it's actually also you're wasting your time on things that they're not being asked for. So the solution for this is always, as we mentioned, that confirm the scope explicitly. So focus on the core problem that that they're asking for. Like for example, if they said core feed functionality, then you have to focus on that. And then you mention specifically that okay, the other features, stories, reels, DMs, e-commerce, they are explicitly out of scope. So that you have this like contract with the interviewer that what things you won't be covered as part of the interview, and that just brings clarity so that both parties are on the same page. Now, the second mistake to avoid is that you should avoid doing premature optimization. So, what it could look like. So, for example, a candidate might say that, okay, we'll use machine learning for feed ranking with, let's say, deep neural networks trained on user behavioral data, let's say, using distributed TensorFlow on Kubernetes. So, if the scale as part of your question that they are being asked is fits on MVP, if it's for the interview scale, then you don't need to go that deep just from the right away, right? You're already optimizing. Even if you do decide to mention any of these things, you still need to go from 0 to 1 to 10, like level 10, for example. So that's why you need to start with simpler engineering, and then you move to much more, you can move to smaller optimizations, and then you can move to the bigger optimizations. So the current approach here will be to just start simple. Initially, just you can say that, okay, we'll just do chronological feed. Later, we can add ranking by, let's say, engagement. And then you can mention that ML as a future enhancement, and scale complexity is going to come with the user growth. So that could be different problems that you need to work on. So yeah, keep things simple in the beginning. You can definitely mention based on how much time you have, how much other things you still have to cover, and what the interview actually wants you to focus on. The mistake number 3 is that is you also need to avoid just hand waving the complexity. Like for example, if the interviewer asks you, okay, how do you generate the feed? You can't just say, okay, we're just going to cache it in Redis. So that will be like pretty bit low on details. So for example, the details that will be missing will be like, okay, what exactly is cached? Is it post IDs? It is full objects? Then one question that is missing is that, okay, how exactly is the cache being populated? Is it fan out on read, or is it fan out on write? And then the third important thing that would be missing if you just like hand wave through this is that, okay, when is the cache invalidated? What is the TTL? And the fourth thing is that will be missing if you don't cover, which is that, okay, where is the cache stored? Is it cluster config, or like, so you need to be more specific on that. So one way of correct approach to be able to do this would be like, you can say that, okay, you can give specific details like, okay, we are going to cache post IDs in a Redis sorted set with the 5-minute TTL populated via fan out on write for normal users, which, as we discussed earlier, will be users less than 10,000 followers. So now let's talk about mistake number 4. So one mistake that you need to avoid is that, okay, ignoring numbers. So what does that mean? For example, if a candidate says, if you say, okay, sorry, if the interviewer asks you, okay, can a single database handle this, right? And if the candidate, if you say that, oh yeah, the database can handle a lot of data, right? That is pretty vague with no calculation. There's no number, there's no data. So that is not a good answer. You shouldn't be saying that. So what you should be saying, actually, the correct approach will be, okay. So for example, if the interviewer asks you, okay, can a single database handle this? So your answer should be something like, okay, so let me check. 100 million posts per day times 1 kilobyte per post equal to 100 gigabytes per day metadata, plus 2 billion users times 2 kilobyte per user equal to 4 terabytes of users. So 1 year we will have roughly 10 to 50 terabytes of total metadata. Then you can relate it back to the database. So essentially it will be like a single PostgreSQL instance practical limit is approximately 10 terabytes. So yes, initially we might be able to support, but we will need sharding for growth to 50 terabytes with time. So it shows you that you can reason about scale and you can give concrete numbers, which is pretty important when you're interviewing for experience more senior roles. So now the mistake number 5 is not adapting to hints. So for example, if the interviewer asks you, okay, what if the user has like 10 million followers? So this is a classic celebrity problem that we discussed earlier. So candidate in this case, let's say you ignore the hint and you just say, oh yeah, the feed generation still works as it was working for normal users. So the thing is, the interviewer is actually trying to guide you towards the discussing the celebrity problem. So this is actually a sign of a good interviewer that they're guiding you in the right direction. So the correct approach here would be that you can start by saying, oh, good point, okay, great, okay, with 10 million followers, let's say fan art on Write would be super expensive. So 10 million cash rights per post has to be, that'll be better approach, right? So let me revise the approach to use find out don't read for users above a follow threshold. So essentially you need to be able to adapt on the hints that the interviewer is giving you. And again, it shows you that you can listen and adapt, which is a pretty good skill, pretty needed skill as part of the interviews. Now let's talk about mistake number 6, which is being the architecture astronaut, which is like just throwing out too many buzzwords. So what it will look like? So you might say a candidate might say, "Oh, we'll use blockchain with immutable post storage. We'll implement event sourcing with CQRS, or we'll deploy on serverless Kubernetes with service mesh. We'll apply quantum algorithms, for example, like for feed ranking, like things like that, which is like way too buzzword focused. And this is it's not really backed up with logic or rational, right? So that's not a good thing. So correct approach will be to essentially to be sticking with use proven patterns, right? Let's say like microservices, caching, sharding, or mention advanced topics only by when you if they're relevant. And the second thing is you understand them. Like you can't just say like blockchain. No, no, no. If you say blockchain, then you have to justify like why blockchain might be relevant in this use case and how you back it up with your knowledge, right, or your experience. Only do that when it's needed, and if you do, then you have to back it up with a rationale or like a justification, and that too a valid one. So now let's talk about the mistake number 7, which is no error handling or monitoring. Let's say if you design a system and candidates can design performance system and they never mention what happens when a database fails and how to detect issues or logging and monitoring. So that's not a good thing. That's a pretty big red flag. So you should not do that. Yeah, every system it will fail in production at some point. So you need to mention error handling and monitoring and failure scenarios and disaster recovery. So what would be the correct approach here? So one way to correct approach to do this is that okay, you mentioned the failure scenarios. Like for example, you mentioned that okay, if the primary database fails, okay, auto failover will kick in to the replica database. And then like one thing to mention is the second thing is to discuss the monitoring, which is okay, we'll track latency, we'll track error rates, we'll track CPU and memory usage, and then any of the anomalies, sorry, that's being detected, then we'll send out automated alerts as part of on call to our teams, either as SREs or SDEs on our team. It shows the production mindset that you should be following. Mistake number 8 is essentially poor time management. So let's say you start the interview and 30 minutes and you're still discussing requirements. So that's a bad thing, right? So 10 minutes left, then you'll be rushing through the architecture and no time for deep dive, and there's no time for discussing trade-offs, and then somehow then the interview will end before you even showed the technical depth. So that's why you need to be really good at time management. So one correct approach to do this will be like okay, check time at 15, 25 and 35-minute marks so that you know exactly where you're currently standing, and on the requirements spend 5 to 7 minutes maximum. Leave 10 to 15 minutes for deep dive because that's where you really want to showcase the skills. And if the interviewer asks you deep question at less than minute 40, that's okay because that means they're interested actually. It's a good two-way conversation is happening. So that's pretty good actually. Now let's talk about the practice recommendations. How to prepare for system design interviews, which requires let's say a study plan for 6 to 8 weeks. So this is just a sample study plan you can follow. Let's say if you have interviews in next 2 months, 6 to 8 weeks. So week 1 to 2, you can start focusing on the fundamentals. So in this part, you should focus on things like horizontal versus vertical scaling, load balancing, whether it's L4 versus L7, caching strategies, which is including write through, write back, cache aside, database sharding and replication, which covers consistency, availability, partition tolerance, and then SQL versus NoSQL trade-offs, and message queues and asynchronous programming processing. That'll be like your concepts you should probably cover within your first 1 to 2 weeks. I'd say do as soon as you can, but that's like a good estimate. One thing I would say that don't just start mock interviews just yet. Focus on right now in this stage, week 1 to 2, just understanding the concepts very deeply. Take notes on each of the design pattern and each of the trade-offs. because the right time for doing mock interviews will come a bit later. So for week 3 to 4, you start covering the practice problems. So for example, these are the very popular design system problems that the whole industry kind of covers at some point. I know in the interview process. So like problems to practice will include designing a URL shortener, which covers hashing, database design, caching in let's say 45 minutes. Designing Twitter, which will cover feed generation, fan out, and graph data in 45 minutes. Designing WhatsApp, like for example, that will cover real-time messaging, WebSockets, consistency. Designing Uber will cover geospatial indexing, real-time matching. Designing YouTube, that will cover things like video streaming, CDN, storage tiers, and designing Instagram, the one problem we just covered in this course. So the thing to note is that all of these problems are supposed to be covered in the same amount of time, which is roughly in 45 minutes. But one thing that they all have, and the framework that we covered in this course, like starting with requirements, then doing capacity estimation, then doing high level architecture, then doing database design, then doing API design, then doing service design. This whole framework, it will apply to each of the questions. So that's a good thing. You can follow the same framework in each of the problems. But the thing is, where it will differ is that the deep dive concepts, like for example, in the URL shortener, hashing, caching would be the deep dive topics. For WhatsApp, the deep dive topics will be real time messaging, WebSockets, consistency. For Uber, the deep dive topics will be geospatial indexing, real time matching. So each of the problem will have a different deep dive, but the 70% of the interview, I would say, it follows the same structure, which we cover, like starting with defining requirements, asking clarifying questions, establishing your problem, doing capacity estimation, doing high level architecture, doing the database design, doing the API design, designing the services, doing the trade offs, all those things. So, yeah. Now, let's talk about week 5 and 6. So, this is the time when you should be doing mock interviews. So, how you should approach that? For mock interviews, I would say that schedule 2 or 3 mock interviews per week. So, for that, you can do, for example, you can ask your friends and you can do mock interviews for them. They can do it for you. Things like that. You can rotate problems. Don't repeat the same problem because you shouldn't be memorizing things. You should be completely ready to encounter a problem that you may have never seen, which will most likely will happen in the interviews. Ask for very raw, honest feedback from your friends that okay, what exactly where did I screw up? And focus on time management first, honestly. One thing is communication, that what you think you're able to communicate clearly to the interviewer and to the listener. And the second thing is the time management, that you're always ending within 40-45 minutes range. You're never going overboard. So that's a very important thing. And after each mock, just do a retrospective. Like, for example, what went well? What mistakes did you make? What concepts you still need to do better on? And practice with specific areas. So I would say, like, one thing when I was doing mocks early in my career as well, either I'll ask friends to spend time with me, but when I was not able to get someone to do mock with me, what I would do is actually I'll just record my mock interview just doing like this, like in a camera. I'll do an interview that imagining the interviewer is asking me this question, and then I just do a mock myself, and then I'll watch the video recording after that. So that's one way to do as well. Now, for week 7 and 8, what you can do is that you can start with the company specific preparation. Every company does it slightly differently, and I would say don't do this until you have completely mastered all the first 6 weeks, and only then after you move to company specific if you have extra time. So, for example, if you're interviewing at Meta or Facebook, they build Instagram, so it's better if you read the architecture blogs, you read their just like their announcements, so deep dive, so because they will really appreciate you knowing more about their technical stack, their technical documentation online. I know Cassandra because they created it, and Tau, GraphStore, and Memcache because they heavily use it. And expect graph heavy problems about friends, feeds, and groups because that's Facebook's bread and butter. If you're doing at Google, I would say know their technologies pretty well, like Bigtable, Spanner, MapReduce, and expect a lot of questions on large scale data processing and search related problems, again, which is their domain. If you're doing an Amazon, I would say suggest knowing their technologies like DynamoDB, AWS S3, Aurora, and consider e-commerce problems and highly available systems because that is something that is very important to Amazon. And if you're doing it Microsoft, again, it's very similar. Since I'm a former employee of Microsoft, I won't say much due to avoiding conflict of interest, I would say just follow the public guidance that is out there. And how to read, how to prep is that okay, read company engineering blogs, know their open source projects, tailor solutions to their tech stack, for example, C Sharp or Java, and whatever company is more into, and mention the technology and relevance, but don't force it. So again, do all this optimization only if you have mastered all the other first 6 weeks of system design, and then only then you go for company specific things. Now let's talk about things you can do day before interview. For example, the preparation is pretty crucial. So just a day before the interview, you make sure you review the key numbers. For example, 1 million seconds per day. How much is that? 1 million is equals to 10 to the ninth. And then just drawing architecture diagrams very quickly. So you're very good at doing that on either digital whiteboard or physical whiteboard. It depends on how you're doing the interview. Keep reviewing your past mistakes, notes from your own mocks, so that you can make sure you focus on them and make sure that doesn't happen. And the most important thing I would say is to sleep well. You need to sleep 8 to 9 hours. You need that mental clarity on the final day of the interview. So make sure the day before that you sleep very well. And make sure, I would say, don't do these things in just one day for the interviews. I would say don't cram new concept. You don't want to confuse yourself with something last minute. And don't actually practice new problems just 1 2 days before the interview, because again it'll just stress you out. It just might confuse you more. So don't do that. And again, don't stay up late few days before the interview. Get good sleep. The fatigue will show up in the interview, so you don't want to do that. And now in the interview day itself, for the materials, make sure they will have these things as well, like whiteboard markers. You have it. If you're doing it remotely on your own whiteboard, make sure you have the markers and have a small things like pen and paper for notes. Just seem very eager that you're ready to take notes when you're trying to learn about the team, about the product. Just have water bottle, just because you have to speak for 5 rounds the whole day. Like even me doing right now the video course, like I have water bottle with me on the side, because sometimes after when you're speaking, so like it's a privilege. If I'm very grateful that I'm able to speak and do interviews, but like at the same time, it's your throat kind of start drying out, so you need to have water bottle and just relax yourself so that you're able to speak for the whole 5 interviews, the whole day loop. And just for the interview, small tips like arrive early, I would say 30 minutes early. Again, deep breaths, calm your nerves, just stay calm. You're just trying to learn the team, about the team and the company just as much as they are. And don't put pressure on yourself. Don't do that. And during the interview, just ask if you can take 30 seconds to organize your thoughts. Again, you have to share your thinking. You have to think out loud, but at the same time, don't be afraid to be like, okay, can I just take 20 minutes, seconds to think about it? If you're hungry, go ask a protein bar or snack. I have done it myself. Like sometimes when at the lunch was like I was not able to eat, and then so I will just like ask between the interview that, oh, can I just grab a quick snack? And they were always nice enough to say, yeah, please go ahead. And one quick story I'll say, like one of the interviews I had like many years ago, in the lunch round itself, generally the lunch rounds was supposed to be that, okay, you just meet the interviewer. One of the interviewers, they take you to the food court, you have the lunch, and there won't be any technical question. They'll just be like, get to know each other. So we had this lunch for 10 minutes. Within 10 minutes, they said that, okay, like now let's go to the room and let's do a technical problem. And I was very surprised because it has never happened to me before. So make sure you're ready for that as well. Just FYI. Now let's talk about key numbers you should know by heart the day of the interviews. For example, time one day equal to 86,400 seconds, which is approximately 100k seconds. 1 month is approximately 2.5 million seconds. When it comes to data, 1 kilobyte equals to 1000 bytes. 1 megabyte is equal to 1000 kilobytes, equal to 1 million bytes. 1 gigabyte is equal to 1000 megabytes, which is equal to 1 billion bytes. 1 terabyte is equal to 1000 GB. 1 petabyte is equal to 1000 TB. And when it comes to latency, some numbers are like RAM is under 1 millisecond, SSD under 1 millisecond, network same data center is like 1 to 5 millisecond, network cross country is 50 to 100 milliseconds, network cross ocean is 100 to 300 milliseconds. And for throughput, single server handles 1 to 10,000 QPS, database handles 10,000 to 100,000 QPS, where replicas Redis handles over 100,000 QPS. And availability, 3 nines equal to 8.76 hours of downtime per year, 4 nines equals to 52 minutes downtime per year, 5 nines equals to 5 minutes of downtime per year. And now let's talk about some final interview tips for success. So to start off with, for communication best practices, you should consider doing these things. So one thing is to think out loud, so the interviewers exactly see your reasoning. For example, you can say that, okay, I'm considering two approaches, A and B. I know A is simpler, but B scales better, so that you are able to show your thinking to the interviewer. Draw the diagrams. Visual aid understanding is super important because that's just part of everyday work as an engineer. You need to show that you're not just explaining it by talking about things, you're able to draw things, connect the dots, connect the arrows, and this completely make the architecture on the whiteboard. That's super important as well. The third thing is ask questions, not just as part of the clarifying the requirements part, but also when they give you last 5 minutes in the interview that, okay, do you have any questions for us? Make sure you have really good questions prepared for them. Mostly what I do personally, I either ask about their team, about their projects in their team, or the projects that the person is specifically working on. If they're allowed to talk about, I give them a disclaimer. Anything that is public knowledge only. Because it just shows that one thing I'm generally curious about things, you need to be first you have to make yourself believe that you're actually passionate about what you're interviewing for, and then how do you showcase that? The second thing is you ask these questions to be able to be more knowledgeable about their thing, their products, their technical stuff, and confirm the understanding as well. One thing as an engineer, it's very important is that you have to prevent the alignment, and for this, communication is super important. Like, while you're doing things, you should definitely ask small things like, okay, so now we're going to do feed generation like this. We're going to optimize for read performance. That's correct. And a quick check in, and then you just keep moving. And there's some mistakes I would say don't do it. Don't do it for sure. Like, for example, silent thinking. Like, sometimes when you're in deep thoughts, we might just go silent. So don't do that because the interviewer doesn't know. And because one thing about the interviews is that they're always taking notes, because then they share these notes with their team when they're making a hiring decision, right? So that's why don't be silent. Keep talking, keep thinking out loud, because anything of value will always come help you. And then never argue with the interviewer, right? You need to appear collaborative to the interviewer, that you're working on the same team, you're working, it's like working with a team member towards the problem, right? Not like you're working against each other. So don't do that. Don't argue with the interviewer. Even if you sometimes you might find interviewer might be hard to work with for whatever reason, that's fine. Life happens. You might not win, you never win all the battles. That's totally fine. But just maintain the professional positiveness and just keep moving. Third thing is giving up. Never give up. Let's say if you get a problem and you're stuck and you don't go silent, keep brainstorming, keep thinking aloud. And if a good interviewer, they should be helping you, unblocking you kind of problem, because that way you will signal to the interviewer and the team who will read the notes of the interviewer that, okay, this person doesn't give up, which is a very important skill you need to have. Fourth thing is ignoring time. You need to be make sure that you are on time. You are on your way to finish between before 45 minutes. You're completing a request, requirements gathering in 5 to 7 minutes, capacity estimation in the next 5 minutes, things like that. So you need to make sure you're tracking the time, and don't try to memorize solutions. Don't try to just spit it out too quickly, because it will show. And the second thing is you will then break down when they cross question you, when they ask you either to go deep dive into some specific topic, or if they start grilling you or something. Okay, why do you do this, why do you do that? So the best approach is, like, you need to remember the general structure, like what will be step one. Okay, asking questions, clarifying requirements, things like that. What is step two? Okay, it's capacity estimation, or the numbers that we just talked about, the latency numbers or throughput numbers. Those things, yes, you should be remembering, but the solution itself shouldn't be memorized. It should be more like understood, and whatever comes out in the interview, naturally that makes sense, because they are not really looking for the exact correct answer in the interview. They are looking for the thought process that, okay, given a problem, even if you don't know anything about it, how will you break it down to smaller sub problems? And then how will you solve each of the sub problems? And eventually the bigger problem will get solved. And for example, this is for my use case, it's my own notes, but you don't have to follow this. For example, leverage your own experience. Like in any employee you might have worked at, try to connect the dots. Okay, like for example, this is really much more relevant in the behavioral round, but like for example, if you're doing scaling and they might say, okay, why don't you use MongoDB or something, then you can say a lot of things like from experience that, okay, for example, my company, they used MongoDB for a while, but they considered it, but they had multiple issues in the production. Not to say MongoDB I'm sure it's a great database in its own right, but you can basically talk about your design decisions and the trade-offs, these two things, by connecting the dots back to your experience. And then again, talk about your academic experience. Like, for example, this was my use case, but again, you can do it, for example, your grad school experience, like something you encountered in the research or something like that. That, okay, why am I doing this? Like, why am I not using some specific technology? Because then you can connect back to your, like, let's say, academic research that, okay, we did try it there and didn't work out because of this reason. So that's why. And one thing is that you need to start broad, start with the high level architecture, and then, wait for them to see where they guide you towards the deep dive part. And if they don't ask you, then you pick one of the deep dive areas that you're best prepared for. But and then you show them the depth that, okay, if it's feed aggregation, then or if it's multi-region replication, or if it's data sharding, then if they give you a deep dive, which happens, which is good, then you go on that. If they don't give you, they leave it up to you. They can be like, okay, whichever area you want to pursue, go ahead. Then you pick the one that you're most prepared for. And handling difficult moments. So basically, this is more when I sometimes you just hit into roadblocks in the interview and you don't know, okay, damn, what do I do now? Like, for example, if you don't know something, that's totally fine. You just don't say, okay, I don't know. Don't say that. You can start with, okay, I haven't worked with this specific technology. This is how I would approach this problem in similar systems I've worked with. For production, let's say I'll do this X, Y, Z. So what I'm trying to say is that don't just say you don't know. Let's say if they say, have you used Cassandra? So don't say, oh, I don't know Cassandra, so that's it. And then you become silent. Don't do that. So you can say that, okay, I have not used Cassandra, but you can say that, okay, I have used DynamoDB, which is a similar, not exact same NoSQL database, but a similar NoSQL database. And this is how I would design my database, data store as a NoSQL schema. So this will still give you that. Don't block. Don't just say I don't know. Try to find solutions, because as an engineer, as a more experienced engineer, that's your thing. Like, you have to find solutions somehow, one way or the other. And if the interview challenges the design, as we earlier discussed in the course, like if they say that, oh, no, they try to grill you too much or stress you out, sometimes happens, very rarely, but we need to be prepared for it. So in that case, like, be polite, be professional. You should be like, okay, that's a great point. I had not considered. If this is considered true, you can just say that, okay, my approach might have problem. Let me think about an alternative, and then start brainstorming about the alternatives. Like, you need to handle it in a professional way, and you need to do it in a way that you make sure that the interviewer feels welcome. They feel that, okay, you took their feedback seriously, and then you genuinely try to see, okay, if their feedback is correct or not. And if that is correct, then you try to improve your design based on that. Now let's say the scenario that you realize you made a mistake, right? So the wrong response would be to either try to hide it or you shouldn't double down. So don't do that. So the right response would be that, okay, something like you can say that, okay, actually I realize there's an issue with what I just proposed. Let me explain the problem. Let me revise to handle that case. It shows that you have self-awareness, you have honesty, which is very important in the interviews, and you have ability to course correct. So feel free to own up to your problems, correct yourself, and that's totally fine. Scenario 4 is when you're rushing through time. So the wrong response would be to just rush through things incoherently. So try not to do that. So the right response would be like something like, okay, you can say that, okay, I see we have 5 minutes left. I would like to cover trade-offs and scaling. Would you prefer I focus on one of those, or briefly touch both? So try to put their ball in their court, try to see how they guide you, what they prefer more, because the thing they're gonna tell you is that what they actually gonna mark you, assess you more as part of the interview assessment. So you wanna do that. And again, this shows like time awareness, prioritization, giving in the interview controls, which they like. So again, you need to keep them involved. And just like small things, this is more like body language or presence, and it does matter. You need to be able to still, not in a bad way, but you need to be able to own the interview in the sense that you need to be completely involved. It should be learning experience for both of you, right? For example, when you leave the interview, even the interviewer should be like, oh wow, okay, I learned something from this candidate. Or the second thing would be like, okay, I loved working with this candidate. I would really hope we get to work again. So that's why you really need to be involved. You really need to make sure you're highlighting your skills in front of the interview. So the positive signs are like eye contact, for example, showing confidence and engagement, which builds a rapport between the two people, to the interviewers and the candidate. using whiteboard actively, which is, it shows that you're a visual thinker and you're organized, which is and this easier to follow. So that's very important as well. Nodding while listening, it shows that you're attentive, you show respect, you're creating a collaborative feel, which is pretty important. Steady speaking speed shows that you're thoughtful, you're not rushing through things, shows that you're thinking through things, you're complete, adjusting to diagrams as well. It also communicates that you're an engaged communicator, you maintain the interest in the process of the interview. Now let's talk about a few of the negative signals that you should definitely avoid. So one thing is that you should definitely avoid looking down constantly, like shows that either you're unprepared or you're nervous. Don't stress out. Don't signal that. So fidgeting, just being anxious. I know anxious is a very serious thing, but at the same time, don't try to stress yourself. Just calm yourself. Just take it as another conversation you're just having with a team member, with a coworker. Small things like being arm crossed in front of the interviewer, it's like unprofessional. So yeah, please don't do that. I've seen that happen once during the most of the interviews. So that was a bit like, okay, why is this happening? The candidate, but they're a good person. So yeah, it's all, but yeah, not using whiteboards. Sometimes it happens. Person, they talk a lot verbally, and it's very hard as an interviewer for me to be able to like, okay, which part of the system are we talking about now? So that's why you need to use the whiteboard. Now, the final mindset, I would say, just remember that it's a conversation. It's not really integration. It's sometimes it might feel like that you're being grilled, and that's totally fine. They're doing their job. We have to do our jobs. So that's why one thing is the interview is a conversation. It's just not supposed to be interrogation. Ideally, the good interviewers, the most of the interviewers, they want you to succeed because hiring is hard. They are evaluating that if they would enjoy working with you. So be collaborative. Don't be competitive. And then perfect solution doesn't exist. Every design has trade-offs, right? So show awareness of trade-offs is better than claiming perfection. That okay, my design is the best. Don't do that. The keyword to say here is "it depends" is often the right answer when you provide reasoning, and that shows that like this person has been through the trenches. One thing I would say that yeah, please do that, because anytime they ask you, okay, what do you think about this? Should you handle it for more scale or cost effectiveness or availability? It's always depends. Like what is the business requirement currently? Is it compliance reasons? Is it like cost saving measures? Companies going through a downturn? Like it all depends on situations. So there's no correct answer. So now the fourth thing would be like the communication is super important. It actually is equal, I would say, equals to technical skills, because if you're doing great things, but if you're not able to communicate them, that's not good either. So I would say 50% up to 50% of your score will be is how you communicate. Like clear explanation of good design is better than unclear explanation of perfect design. Practice explaining it to your non-technical friends, like for example, someone like more advanced PMs. If they are able to understand your answers, that's even better. The fifth thing is the interviewers are humans too. They make mistakes too sometimes. Sometimes the problem would be too ambiguous. It's okay to ask for clarification, right? Be respectful, even if you disagree, that's totally fine. Now let's do a complete solution summary. Let's do a recap. So now let's start by recapping requirements. So the functional requirements that we considered now in this course was like including uploading photos, following users, viewing the feed, and liking and comment functionality. And the non-functional requirements that we did was having 500 million DAUs, under 500 millisecond latency, feed load, 4 nines availability, and 73 petabytes per year storage. The scope was per core feed functionality, with stories and DMs being out of scope. For capacity estimation, we calculated that it showed that QPS had 115K with peak at 350K. The write QPS was 1 to 1200 with peak at 3600. Storage we calculated was found to be 73 petabytes per year media and 36 terabytes per year metadata. Bandwidth is 2.3 gigabytes per second ingress and 231 gigabytes per second egress. And the architecture we proposed was based on microservices for user, post, feed, and media services. And the load balancer, and we also suggested the load balancer plus the API gateway or API management in Azure will handle the authentication and rate handling, and or like having a dedicated custom API gateway could be done as well. And it has to be stateless application service to enable the horizontal scaling. For databases, we propose that it has to be SQL. We chose PostgreSQL for relational data. We propose 5 tables: user, posts, follow, likes, and comments. We propose that sharding will be used 100,000 shards, and the shard will be a user ID modulo 1000. The replication will use one primary and three replicas per shard. And for indexes, we propose that we'll use composite indexes on common query patterns. For API design, we propose that we'll use like RESTful endpoints version at v1. We propose that we'll do cursor-based pagination instead of not using offset-based pagination for the reason we covered earlier in the course. And we also propose that we'll be using JWT authentication. We'll be using rate limiting using the token bucket algorithm. And for the feed generation, we propose that we will do a hybrid fan out, which will write for normal users, and we'll be doing read for the celebrities, which is like people with more than 10,000 followers. For racking, for the feed, we decided that we propose that we'll do 40% by recency, 30% by engagement, 20% by the relationship, and 10% by content type. And for the caching, we propose that we'll be using Redis with 5-minute TTL at the 80% hit rate. Now, for the media storage, we propose that we'll use object storage, something like AWS S3 or Azure Blob for photos. We'll use CDN for global delivery, which is 80% of cache hit rate. We'll use async processing, compression, plus 3 thumbnail sizes. We'll use lifecycle policies, hot, warm, cold storage tiers, as we discussed earlier in the course, to save money, lots of money actually, by having lifecycle policies. And for the scaling itself, we propose that for the application layer, we'll have to start off with 1,000 plus stateless servers. We'll have auto scaling. For database tier, we propose that we'll have 4,000 instances with sharding plus replication. For cache tier, we propose that we'll use 400 Redis instances partition. And for query queue tier, we propose that we'll use asynchronous workers for image processing and notifications. And for the trade-off that we covered in the course, essentially was eventual consistency, fees versus strong consistency for likes and follows, SQL versus NoSQL. We chose SQL for relationships, for transactions. For fan out on write versus read, we had to choose hybrid approach for the Instagram for the specific use case. And then we also talked about microservices complexity versus the need for independent scaling. And the cost of the architecture we estimated and calculated to be $57 roughly million per month, which comes down to be $680 million per year. And then we also calculated as part of the optimization section that we can save up to $40 to $50 million per year. Now let's cover to recap what you ideally learn in this course. So we covered both technical depth and interview skills with the complete production grade architecture. We talked about the actual database schemas with sharding and indexing strategies. We covered the API design with authentication and pagination. We also covered feed generation algorithm with ranking, and then we also covered media storage and a CDN strategy and scaling patterns for all the tiers. For the interview skills, we talked about how to structure a 45-minute interview. We talked about what interviewers evaluate, what are the common mistakes and how to avoid them, what are the good time management strategies, and what are the good communication best practices as part of this course that we covered. And we also talk about like the business context in this course, like for example, including the capacity estimation and cost analysis and trade-off evaluation, alternative architectures that we considered, and also the real-world production constraints. Now, I would say this is the ideal practice checklist just before your interviewer. So just make sure you go through it while you're preparing as well. So make sure you review the solution in this course like 2 to 3 times ideally. Practice the drawing architecture diagram with goal less than 5 minutes for each of the diagram. Memorize the key numbers: 500 million DAO, the query KPS for Instagram, the 73 for petabytes of storage. Again, you don't need to memorize the exact numbers, but you need to completely understand and digest the exact process, the exact mathematical calculations we did to come up to be able to reach these numbers. And like practice explaining the feed algorithm out loud because that's a pretty complex topic. And review the database schema as well, review the sharding strategy as well. I know like for mock interview preparation, I would say try to complete 3 to 5 mock interviews on 5 different problems. Record yourself, I would say, watch the playback, watch yourself doing the mock in the video, get feedback on communication style, your technical skills, and practice this trick 45 minutes because that's super important. And again, just like practice questions like you need to review notes on past mistakes, practice questions like tell me about yourself because you'll go with the system design interview, but you might be thrown out by completely random questions. So be prepared for the very basic, very common one, even the system design, which will you start with the conversation like, okay, please tell me about yourself. So make sure you keep it very small, a good answer, but a very small answer, so that then you can move to the actual core of the interview. Prepare questions that you want to ask to the interviewer. Like I said earlier in the course, was like ask them about their products, the projects they are working on, their team. Show interest in their team. Show passion that okay, you really not you just don't want the job. You really want to be able to work together. And again, get out of the stage. That's super important. Try to arrive early. Try to log in early. Those things do matter. And again, in this course, you'll see in the resources section there will be one page cheat sheet where summaries notes as well as you'll see a lot more detailed lecture slides I'll be attaching in the notes resource section. So I have currently put on 300 slides I think in this course. So all of these slides, all 300 of them, you'll be able to download and access through the portal. And the architecture diagrams will be there as well in the lecture slides. Please feel free to review them as well. And one of the books that I strongly recommend for system design is Designing Data Intensive Applications. So that's super helpful as well. So please do review that book as well. And there are more sources. I'll mention that in the portal as well and the announcements tab. So, yeah. And again, for what blogs to follow, for example, Instagram engineering blog is a good thing to follow. Meta Zone engineering blog, high scalability blog is a pretty good one. Martin Fowler's blog is pretty good one, especially not just for system design but also for software architecture, which is like pure coding, just like building applications inside out and how to do clean architecture, things like that. So if you are more interested, you can find clean architecture and that topic, those topics like software architecture in my other course in the portal as well. Feel free to check it out. And yeah, if you have any other questions, these are the website, socials, any sort of feedback you can give me, I'll be really grateful. And yeah, I just want to say that thank you so much. If you, I hope you lasted this long in the course.